Yeah, we've got, yeah, correct.
There we go, it's better. Do I have a fold back screen? Or
no.
okay, I can do it, it's fine.
Currently, saying we're not getting an input at the moment.
There we go. So.
Oh, no, hang on. HDMI 3G 1080 60.
That is me.
Is that you there on the
Yep.
screen? That's power, if you want to plug in.
Thank you very much.
So that's Starfield, is that good news, is it?
Yeah. That's the wrong one.
I might just depend on how our audio levels are. If you see me running back to the mixer, don't worry about it.
All right. Almost there. Missing one thing. Yeah.
Just bear in mind that you kind of need to stay by that microphone all right. For the sake of the web stream.
Wonderful. Right, thank you for your patience, everybody. I think we're ready to roll. How long is this slot, incidentally? 45 minutes, okay. Lovely. Right, welcome. Thank you for turning up first thing in the morning-ish. We will be talking about how to hack Kubernetes. This is, to some extent, the talk of the book, and there are books available upstairs on the ControlPlane booth that I'll be signing in an unintelligible scrawl throughout the day. We'll also run a CTF tomorrow, where you can take some of the lessons learned here and abuse infrastructure with them. I'm from ControlPlane. We are cloud-native security engineering. If it is in the cloud or cloud-flavored and it has security to do with it, we are interested. I have done various different things. I'm very proud to be involved with not only ControlPlane, but Security, which is the Linux Foundation's technical advisory group on cloud-native security. As part of that, we help to assure projects that are coming through. For example, at the moment, we're working on Flux and Cert Manager, things like how do you operate safely in a multi-tenant isolated environment for these things, and how do you build out threat models. This is all open source community work. If you are interested, we meet on the UK time zone at 1 o'clock every other Wednesday, and there's a US-centric version of that as well at 6 p.m. UK every other Wednesday. I'm also involved in Open UK, as is Liz. We are an open source advocacy group looking to expand and extend the use of open source safely throughout government and industry, and importantly, to ensure that open source maintainers are paid for their toil, so that this asymmetry between large organizations and individual hobbyists levels out. We end up with higher quality software overall, and people are fairly remunerated for their passion and dedication. Various other things, hacking Kubernetes, books are available, other bits and bobs around cloud-native security and training, all very deep passions of mine. The book is not only available upstairs, but should you wish to download the first half as a PDF, meaning that you don't have to rekey some of the complex one-liners, it is available behind an email paywall on the ControlPlane website. And shout out to my preeminent co-author, Mr. Michael Hassenblas, who was instrumental in the authorship of the work. ControlPlane, we do these things. I've said this to some extent already. And if you'd like to work with us, we have nice people and interesting work guaranteed. Do come and talk to anybody. We are open and transparent. And with that, into the talk. What are we doing today? We'll talk about threat models. What is a threat model and why? How to hack a Kubernetes. What does it look like? What should we do? Into the demos. First of all, the supply chain. So hot right now. We start externally to a cluster and we look at how ultimately we can potentially pwn a cloud account going through supply chain. What is a reverse shell and how does it work? What is a container breakout? We can break out for misconfiguration, but when the kernel has a vulnerability, we will pop a shell, courtesy of one of my colleagues in the room here today. Then we look at enumerating the host. Once we've broken out of a container and we're on a kubelet node, what can we do? What does that expose to us? Especially interested in data multi-tenancy and classification. We should never be mixing things of different levels like development and production or PCI data and cat GIFs. And finally, can we get into your cloud account? And onwards. Huge thanks again, Liz is in this list. People who have helped to educate the container security market, starting from the ground up, looking at how we build things, and some allusions to other talks and live demos that I've done in there as well. Okay, in we go. Security teams do not like Kubernetes. It is generally terrifying, an unknown mystical box into which they cannot see. Cloud native expertise is still a rarefied skill. What are they worried about? Captain Hashjack, dread pirate Captain Hashjack. In any threat model of a system, we must ascertain the nature of the adversary with which we're trying to defend ourselves. And in this case, we have modeled the adversary on a criminal nation-state sponsored gray area kind of actor. These are the most dangerous people that we see generally today that are not, let's say, one of the nation-state official departments, perhaps. Might be analogous to a Fancy Bear or one of those APTs from China or Russia. These are organizations that operate in the shadowy netherworld between sanctioned cybercrime and private online gangstering. And we will look at exactly what that means. This is the treasure map by which I penetration test Kubernetes clusters. It's a DIY security map from the book. It comes up at the end as well. We can take any sort of approach, but this is a slightly methodical way of doing it. So, threat landscapes will also always vary per organization. And our landscape can be made up of various different threat sources. Thank you very much. The difference between attacking, for example, a government intelligence agency, which would require a degree of skill and some financial backing, let's say, and a script kiddie attacking Valve to try and steal the source code for Half-Life, they're reasonably different in how you would consider defending, although the outcomes ultimately are the same, loss of confidentiality or information that's of some value. The important point here is that we need to modulate our defense based upon the adversary that we suspect. And this is the skill and resource and the interest level and motivation. So in order to map our controls and our defenses on a threat landscape, ControlPlane use this adversary matrix. This is how we make sure that we spend the right amount of money on security and don't, for example, just lock everything down in a straitjacket. Why is that? Well, usable security is essential, first of all, for developer retention. There is nothing more frustrating than entering a highly secure environment and being unable to instigate any change despite poor practice that can't be justified for one reason or another. So trying to offset the terror of an individual security engineer taking responsibility for the security of a system by mapping things out in a justifiable, quantifiable way and leaving a paper trail so that future maintainers can understand what the system does and why. So with that, who do we have on the adversary matrix? First of all, the vandal, script kiddie, trespasser. This is where some of us may have started our careers. Minimum viable cloud native security is not shipping CVEs to production. If Metasploit or Kali Linux can pop a shell in your environment, that is professional negligence. We should never allow ourselves to be in that position. Now, 0 days temper this somewhat because there is always a sliding window after which a 0 day is announced that unfortunately Log4Shell would mean that everyone gets popped for a period of time. So ultimately, while this is the goal, as soon as our scanning equipment, let's say, so our vulnerability scanners, notify us that there is a 0-day or a problem, we should have a well-oiled CI pipeline, accurate tests, and integration and acceptance tests that mean that we can patch and ship changes. This is the container pipeline dream, of course. So we should not be vulnerable to a script kiddie. We get into motivated individuals. Once people have a drive or a certain acrimony for a situation, it becomes a little bit more difficult, of course, because then we have to consider, well, how long will they spend repeatedly, potentially attempting to attack us in some way or another? Capabilities, again, are kind of edging up slowly until we get into insiders. This is where things get quite difficult, and actually, if we consider somebody like the Lapsus group, really, their capabilities are at the top level there. And I say the top level and the inverse. They're very unskilled, but they are highly motivated. And the way that they operate is by paying people for VPN access. So that means they come in with the capabilities at the third level. So while this is a useful framework, it doesn't necessarily map everything perfectly. But insiders force us to strongly consider how we separate responsibilities for administrators, for privileged operations, and especially for people who can mint or escalate their own credentials. Then we get into organized crime. This is where Captain Hashjack sits. This is where most of our APT groups sit. This is where large universities adjacent to state institutions in capitals of Russia and China also sit. There is a thinly veiled link here. The organizations are sponsored and educated by state groups, but one degree of separation which is suitable for political Teflon shouldering to pretend they don't exist. As we know, this is not just limited to sort of Western adversaries. Western organizations, of course, perform exactly the same behaviors. We step up one level then to the Cloud Service Insider. This is, for example, the Capital One hack from a few years ago. Somebody took privileged information, which was knowledge of internal IDs for customers, and then was able to gain a server-side request forgery on the web application firewall AWS entity, overprivileged IAM, and they were then able to use that to read S3 buckets to dump all the Capital One customer data. The point is, the segregation of duties was reasonable, they got that right, but then the insider was able to exfiltrate information that gave them a leg up and then exploit potentially. It's not known whether they were aware of the escalation path for those IAM credentials beforehand. And finally, foreign intelligence services. There becomes a point where ultimately the threat of potentially physical violence against an individual or against a family means that we rely on the controls from the previous level to minimize the possibility of access, for example. So these are the ways that an entire organization, or in fact a country to some extent, would consider their own defense. Why are we being so methodical and so fastidious? And why is this so difficult? Because we have to, as defenders, ensure that the entire list of controls is applied and is correct, whereas for an attacker, they only need to get into one place in the system, observe the visible horizon, and pivot throughout it. So locking down each level while not relying on a purely perimeter-based mindset makes things more difficult. The fix for this is using attack trees. This is one that ControlPlane built for the financial services user group. What we do here is we take all the negative outcomes, we then map what an attacker might do and apply controls across the branches. The goal is to apply the minimum number of controls that cover the maximum number of branches so that we have maintainable security controls, so that we're not overcomplicating the system, because this is, as an abstract thought exercise, very difficult to visualize. It's even complex to see when written down. And finally, again, to ensure that we are still applying modern development practices that attract and retain quality engineers in a secure manner that doesn't, again, constrict and put people in a straitjacket. We do training for this. We do it on O'Reilly. There is more coming up soon. Okay, threat models are great and all that, but what about actual cloud native security? Don't panic. And we go for the demo marathon. This talk has crashed my laptop a number of times, so pray for me. Right, so what are we doing here? We have the 4 C's of Kubernetes security. We start with the code. Application code changes quickly. This is important because we want to maintain flexibility and agility in the market. If we don't change our code quickly, our competitors will be able to ship features more quickly, we will lose an edge, they will make more money, security costs money, ultimately we will probably fold as a result of not being fast enough to ship code. So, we have to keep on shipping code, code changes quickly, it is the place that we're most likely to have vulnerabilities. Because we author it ourselves, so to some extent we assure it ourselves. This is just a fact of life. We want this to be this way. However, from a security modeling perspective, that means that we, or speaking as ControlPlane, we assume that the code is already compromised. This means we can then architect our topologies and our system and our controls based upon that potential fact, which impacts the way, again, that we're orchestrating and organizing the rest of our applications. The code sits in a container. So the code is the bundling of dependencies and application code. The container then is the runtime invocation of that code. We're talking our C groups and namespaces and Linux security modules, all that good stuff, capabilities as well. That container should be minimum privilege. We know all these things from standard security adages. The container then sits one of n in a selection of pods in a cluster. The cluster maintains those pods, keeps the availability, service discovery, the networking, volume and data mounting, etc., and the orchestration. The controls that we apply there, we're looking at admission control, we're looking at essentially deep packet inspection for our, the things that we apply into the cluster. And then finally, the cloud and the colo. This is where we should have account segregation. Again, the way that operators interact with these things should be delineated and impossible to transitively upgrade privilege without the correct authentication. Those are the 4 C's. We're going to start in the code with a supply chain attack. We're going to break out of that. We're going to attack a container. We'll break out of that as well. Do the same thing with the cluster, and we'll see if we can pop that colo from outside of the system. Okay, so we'll start in the supply chain. What is a supply chain? Everything is software. Anytime that we produce a library or anything that could be consumed by somebody else, we become a producer. The producer-consumer problem means that supply chains are long and complex. Many organizations don't rationalize themselves as supply chain producers. So we rely on other people's software the whole way through everything. For example, anything installed by our package manager goes in as root on our device. So we have to trust the people who are maintaining those packages. All of the root CA certificates, all their public keys are installed on our devices by the operating system managers, by the people who run our browsers. They now ship their own versions of those things too. The microcode that runs on our chips. Intel has a management engine that's had remote code execution vulnerabilities. There's a huge number of different trusted layers before we even log into our devices. So, what's the problem? If somebody gets in the distribution chain for any one of those pieces of software, we have a potential compromise of some description or another. In this case, Alice, Bob, and Charlie. If Bob can drop malware into the build, it is going to run in production in a CI/CD sense. These things are long and difficult to secure. We'll look at how to attack a supply chain. So, either we get into the source code for the application, we get into the, from the developer's machine. So maybe I've left my machine open, or I've got an implant that gives somebody remote access. I can get into GitHub or the source repository. We can attack the build infrastructure. That's how SolarWinds was popped. We can infect a trusted supplier. So that's looking at maybe infecting something in a module registry, or in the case of Auth0, infecting someone's a supporting function that is leaving plain text credentials in Slack, infecting a trusted package, or the runtime environment, and this is actually attacking the operating system vendor or the person who runs your laptop. Okay, so what are we going to do? We are going to install a theoretical NPM module that I have not uploaded to the registry. it's going to pull this malicious package. The package will install some malware, and we'll look at exactly what that malware can do. Okay, which window is which? Okay, it's probably not quite big enough. Oops. Okay, let's try that. So, first of all, we have an NPM package. All right, it's pretty standard. This is the contents of the Git repository. We have this package.json. Now, not all package managers permit this, but there are scripts available in NPM. They are either used like this, so npm run test, or in the case of the pre-install, that is a hook. So a hook with a specific name will run at that point in the lifecycle. As you can see from the test, we have got our echo welcome to the danger zone executed in a subshell. So we're given a subshell, and we're able to run arbitrary code. You can imagine where this is going. So when I do an npm install, now I'll install the module from inside this repository. If this was hosted on the npm registry, I would just use the path to the actual package. Okay, so we're performing an install, and it's going to run the exfil.sh script, which is installing a keylogger, a miner. What else will it do? Okay, it's going to have a look at all the credentials I've got. So this code is executing in the context of the user performing the install. That's me. My SSH keys, my GPG keys are sat locally. Now, happily, I'm aware that I should always have a password on those kind of things. Nevertheless, this now means that either if I haven't, or if that keylogger can intercept my password, my identity is compromised. And it's not just the SSH and GPG keys, because when we use OAuth flows and authenticate to a third-party provider, we're given a session token. That session token is stored in our home directory so that we don't constantly have to re-authenticate in that flow. It might last for an hour. It might last for 24 hours. Some cloud providers do not allow you to revoke these. So also potentially I've just lost access or gifted access to any cloud accounts I was logged in to. And there, of course, is ControlPlane's logo, just to remind you, we're not malicious. Okay, so what just happened there? Well, stolen identities, we could potentially tamper with code in an automated style, persisting with a keylogger, installing some sort of rootkit or persistence that allows us to get back into what we started at a later date. Where should we go here? There we are. Okay, so we ran a backdoored open source package. Now, it was on my local machine. There is a degree of demonstrativeness in that it's not up on the public registry. However, public registries haven't really accepted their position as security gatekeepers. They prefer things to be the free and liberal open source world that we would like them to be. It's difficult to enforce this maliciousness. Stuff that's on the Docker Hub still doesn't get taken down often because who ultimately is the arbiter of what is malicious and what isn't requires security investigation for each specific case. The pre-install hook has abused its privilege to install exfiltrate and otherwise foobar, abstract profit. Okay, so what does this look like in a Kubernetes production system? First of all, down at the bottom, we sneak malicious code into a library. The CI/CD builds and deploys. It doesn't detect that malicious code. Now, it will do if that signature has been uploaded to VirusTotal, or it has, if the AST, if the abstract syntax tree has a specific signature, like dump all my environment variables and paste them to paste bin, maybe it would do. But when these are newly authored bits of code, for example, that exfiltration script, it's not until that has been detected and added to a scanning something that it gets detected, unless there's a manual review of all code installed in production or on your devices. I won't ask for a show of hands because it's a bit unfair. Okay, then, once that artifact, the container image, is built with the malicious code inside it, off it goes to production. The front-end container is then running our payload. Now, depending upon the subtlety of the implementation, it should be undetectable. The main process in the container should still run, but then the backdoor can run as a secondary process. We'll get to how that can be detected later on. That payload then fires a reverse shell. A reverse shell is an outbound TCP connection from within an estate that broadly will punch through a firewall. What does that mean? We saw when log4shell happened that you could put a JNLP string in that would connect back to somewhere outside the firewall. People do not firewall outbound connections. And we can see that based upon the prevalence of the log4shell attack. Why is that? Well, because often unfettered internet access is granted to the applications that we run. Probably shouldn't be. Is it more security work? Yes, absolutely. And so generally people just avoid doing it. It means that if I, as the malicious and nefarious Captain Hashjack, can sit with an open TCP connection on a public port on the internet, somebody can come connect back with this reverse shell, and I can then gain command and control into that front end pod. So we will demo that. But first of all, the fix here is 2FA on everything, password for all our keys. Plain text credentials suck, as we know. The majority of these attacks so far have been against crypto wallets, hot wallets sat on people's devices. Probably shouldn't do that if you care about crypto. Air-gap development is completely impractical, but it's there as the data point. Signing works as long as the thing has sanctity in the first place. Otherwise, if we're not sure of exactly what we're signing, maybe a false sense of security is engendered right into the reverse shell. So, trusted producers in this case are people pushing code to public registries for us to consume. Captain Hashjack wants to get into that flow. Our developer code, trusted application, similar to before, except this time we're going to fire a reverse shell. So, as I say, a reverse shell is executing code out of context. So we want to run our code on the victim's machine. Once we do that, we have their delegated identity, I suppose, the user that they're logged in as. We then fire that reverse shell, and we have control of their machine remotely as that user. At that point, of course, we can do what they can do. Potentially then we can attack something else. We can escalate our privilege. That's how we then perpetuate the attack within the victim's cluster. Okay, so it's basically the same attack as before, except we're going to we're going to use a malicious image from the Docker Hub, let's say. So instead of going in through the CI system, we will go in through attacking public images. Points 2 to 5 are the same. Point 1 is slightly different. Now, we're going to cheat here slightly and abuse a misconfiguration. We'll do a container breakout next. But in this case, we are setting the host PID to true, setting the security context there, privilege to true. This should never be possible in your clusters because admission control, deep packet inspection for the units, for the applications that we're deploying, should prevent this configuration. This is footgun central. Nevertheless, we will exploit it. All right, so we'll run this backdoored image. The image will fire this reverse shell. I'll show you what that looks like and how we catch that. That is our command and control, and we will use that in the next demo to break out of the pod. Okay, so where are we here? Nothing's crashed so far. I shouldn't say that, should I? Right, okay, so first of all, we're going to start off using this thing called ngrok. Ngrok gives us a public IP and port combination, and we'll use that for catching our shell. So in the bottom there, we're starting this tunnel. This is a public service. At the top, we have the malicious command, which we're kind of cheating, as I say, to open the security context. And in here is where our reverse shell will be caught. So in that middle window there, we're sat with an open bash shell waiting for the other end to be connected to a shell inside the container at the top here. Let's see if we can run that. That looks... Okay, so kubecontrol run reverse shell, dry run because we'll get the YAML and modify it. Subliminal hack, you can imagine what that does. Bin bash, while true, do no hang up, bash. Here we're going to use the bash virtual TCP file system. Not a particularly good idea at the time. This is one of the easiest ways to establish persistence in someone else's computer. It means that we can use dev TCP and then an IP and port combo, and that will magically connect to the TCP endpoint. Doesn't exist in shell, doesn't exist in ZSH. A reasonably bad idea, let's say. And that sits in a loop. So that's just waiting for the connection to hit the other end here, which is our listener. And that IP and port combo is what ngrok has given us to expose a local port, which is a reasonable thing to do. This is for maybe sharing a development website. It's not necessarily meant to be used like this. Then we modify the security context, set it as privileged. Let's see how we go. Okay, that's deployed, and we are connected. So I am now within the context of someone else's Kubernetes cluster and able to run various things. Let's have a look. As you can see, so that's obviously within the the hack container that I've got up there. So because I'm sharing the process namespace, I can now see the contents of everything that's running on the host. This is a misconfiguration. This should not be possible. But as a case in point, if we do allow this kind of behavior in our clusters, we can trivially do an ns enter permissions upgrade, namespace enter. Again, it's a legitimate tool, but here we're going to jump into the mount namespace, the universal time sharing, inter-process communication, network, process. We're going to spawn a shell, and now instead of seeing the contents of our home directory in the container, we're now in the mount namespace on the host. We still have access to all the good things, like we can see the container runtime, container D, shim. As I say, this is a misconfiguration, but this blasts the security of a cluster. Without correct configuration of the pod itself, we have nothing with which to defend ourselves ultimately. Okay, so slightly contrived in order to demonstrate a point. We will now do the same thing with a container breakout. The point is, once we get a reverse shell and we have command and control of a pod, we're then able to escalate, and this is how we start our attack on someone else's infrastructure. It is not a container escape, says Brad. It's a process that wants to be free. What does that mean? A non-secured pod in the middle, that's what we just saw. Incorrect configuration means that we can easily use legitimate controls, legitimate commands to evade the absence of controls. What we're going to do here, the security best practices surrounding the secured pod mean that we shouldn't be able to escalate. We shouldn't be able to just mount a host disk. We shouldn't be able to enter a process namespace with configuration. They should be prevented. However, because a virtual machine is an emulation of the BIOS of a system, so it emulates the hardware, it does a physical bootstrap, if you like, and then boots on a init system. A container runs a process on an existing kernel. It's so fast because you're just starting a process with this different view on the world. We set namespaces to make the process think it's the only process in the namespace, thinks it's the only process in the file system, etc. What that means is that we're relying upon the kernel for the security of the container. This is a sensible thing to do because we get all the bin packing advantages, we get all the speed of startup, etc. However, if the kernel has a vulnerability, that places us in a default compromised position. If that vulnerability can be exploited from within the container, then it is a bad day, and this is what we're going to do. We're going to exploit a kernel vulnerability in order to evade the container security, the correct container security configuration. As I say, CVEs are a fact of life. Do we want fast software, or do we want to do what radios do and sign off a single version of a firmware, distribute it in the IoT sense as widely as possible, and then prevent upgrades because, well, no one's then reassured the thing. Containers are not a security boundary because the kernel is not a security boundary. Relatively contentious. I would argue the kernel may not be a security boundary, but then neither are hypervisors. We've seen escapes from those, neither are air gaps. We've seen people communicating between air gap systems with either electronic properties or audio properties of the systems. things are at the appropriate level of our risk classification. This is why we threat model things. And ultimately, this question of do we run one cluster or many clusters for a specific workload plays into how much we trust what we have underlying it and the cost of each specific breach type to our organization. Okay, we're almost there. Just a reminder that pods share a number of namespaces. As we can see, we've got localhost shared between containers there, but the storage, the mount and process namespaces should be separate for containers in a pod, and our pod configuration security, if you like, hangs mostly around the default pod configuration box at the top. We can also place it lower down around the individual containers. Okay, into dirty pipe. This is a memory-based attack similar to Dirty Cow, which is a dirty copy on write exploit. What this ultimately means is that the kernel has a vulnerability that we can exploit, and by exploiting this vulnerability, we're able to write code into root-owned executable memory. So once we inject code into there and tell the kernel to run it, that bash shell will do the same thing that we did previously. It's a reverse shell back to where we started off. This time we're in a container instead of on the internet with our listener, just saying connect to my shell. Once we inject that code into root-owned executable memory, it then executes the callback, and we've got a shell running as root on the host. That's how we've escalated from inside to outside the container. Okay, and kudos to my colleague James Cleverly Prance for putting together this exploit. Let's rock and roll. So, what will we do? We'll build a container with a run C replacement, let's say, written in assembly. Once the container runs, it takes the proc self exe bypass that is a known assumption in the kernel, we'll talk about that in a second, and writes this binary over it. That then means that the run C binary is compromised because of this exploit. When that's then run the next time, it makes the callback to inside our container, and we are root. Okay, so we're in a virtual machine because I don't want to run a vulnerable container kernel version. Let's go into here. Yeah, thank you. Okay, so let's make sure we're running a vulnerable version, which we are. Okay, so first of all, let's have a look at actually what we've got in the Docker file that is the container we're going to use to break out. Notably, setcomp is executed inside the container, interestingly. But the point here is that we've got this small run C. Let's have a look at the code for that quickly. The exploit code is up here, but the payload that we run is down here. And you'll notice we have the same reverse shell based upon the dev TCP endpoint from bash. We've chosen this arbitrary IP and port combo. We get to choose the port because we're running our listener ourselves. And what are we going to do? First of all, let's build this. So assembling, building the container. When we run this container, the exploit that has gone down here into the proc self exe will overwrite a file on the host that is the run C binary itself. And we should find profit. Okay, so it's non-deterministic, and it might take a moment. But there we go. It actually operated there quite quickly. Okay, so now, who are we? As you can see, before we were the vagrant user. Now we're root. Where are we? Well, that is the file system location on the host that the container image tarball has been unpacked into, and the pivot root file system, the pivot root kernel system call used to start the container. So at this point, we have broken out, and you can see the contents of the image we were running there. What are we doing? And that then is the file system of the host. So just to recap what happened there. From a Kubernetes cluster perspective, we have now gained root on the kubelet. And this is the beginning of a bad day. The goal here, again, is to have fast deployment pipelines, make sure that everything is patched. I love blue-green infrastructure, but that is a personal preference to some extent. Okay, host enumeration. So we're onto the kubelet. what we can see at the bottom is that for any kubelet, we have root-owned processes that are running the kubelet and those creating the containers, system calls and management of the file systems and the containers at runtime. And then for any given pod, we have this combination of things that includes on the right-hand side our container injected environment variables and our secrets and config maps. We don't use environment variables where possible because they leak into the process table and are considered slightly less secure. You can just do an env dump, capture everything, again, base64 encode it and push it off somewhere via DNS maybe or to a public endpoint. It's quite easy to steal, or to automate the theft of environment variables. So what do? We preferentially mount our secrets as a temp-fs file, and then we use an environment variable to point to its location. So it's one degree of separation, if you like, or abstraction, but it makes a tangible difference to drive-by attacks. The important thing to note here is that everything on a container image or everything in a container at runtime must exist on the host. It's not the same as a virtual machine where we have segregation all the way down to the hardware level and interrupts to some extent. Instead, the host root user is omnipotent, omniscient. They can see and do everything. They can maintain the system. There's very little that can't be done by the host user. So all of the secrets mounted into all of your containers on a given node are available to the root user on that node. It's the way containers work. It's the way Kubernetes manages these temp-fs mounts. But, as you can guess, it gives us access to enumerate the file system. So, from a rooted kubelet host, we will have a look at what is on the file system, find secrets and service accounts, and see if we can profit from them. Where are we here? Not that. Oh, yes, we are. Let's jump up into here. So, in order to make this as seamless as possible, this shouldn't broken down. We're going straight into a GKE cluster. We'll escalate to root because that's how we would have done so with the dirty pipe breakout. Now, of course, okay. All right, so I will take my little pen testing kit with me wherever I go, which is this, and this just gives me access to a load of bash functions that allow me to do most things. So from here, let's have a look at the command we're going to run is ksecrets file system dump. So what are we doing? We're going into varlib kubelet pods. Again, everything that exists on a Kubernetes cluster must exist on the host because it's not a virtual machine. Everything is shared by the same kernel. What is in there? Those are the UIDs of the pods running on this host. And so the path in here, we're going into the different types of volumes that they have, and we're looking for files. Then we want to know which of these are service accounts, and from here we will look at which may be overprivileged. Can we use this to then escalate and pivot throughout the cluster in general? Okay, so first of all right, so there's a lot of things in here, and maybe we want to narrow that down slightly. Let's just have a look at everything that's there. Lots of tokens and namespaces. This is the point where we then, for each of those tokens and namespaces, enumerate its permission set, because there's an API call that allows us to do that. But maybe there's something slightly more interesting on this cluster. Ooh, AWS keys. Why might these be here? Well, potentially somebody wants to create an S3 bucket, or they're running their own form of autoscaling, or they want to be able to control the load balancers or the network routing around them. It's generally a very bad idea. We would prefer to use something like workload identity that takes properties of the workload and uses those to exchange for a token with the cloud provider itself. Okay, at this point, we are hoping that these keys will allow us access to something far more interesting. What else do we have here? Okay, the point, of course, is not to multi-tenant data classifications. These are the kittens of Kubernetes traversing between nodes. Obviously, back to threat modeling, everything must be managed, separated, and rationalized about from a post-compromise perspective. So at this point, can we take over the cloud account from a supply chain mistake? Quite possibly. Okay, so what will we do? We've got these stolen cloud account keys. We want an IAM misconfiguration so that in a similar way to the Capital One hack, something that's supposed to be secure actually can be exploited. Let's jump in here. Whoop, that one. Okay, so what are we going to do? Well, whenever we get access to someone else's secret keys, we want to run the AWS, in this case, we know they're AWS keys, simple token service get caller identity. The name that it will return is hopefully something like cluster admin or account admin that will allow us to enumerate the privilege set. Now, enumerating privileges can be noisy, so we'd prefer to do this in a targeted manner. See what we get. Oh dear. This is a canary token. This means that the usage of this token has now alerted somebody that the token, which should never be used, has for some reason been used, as we see, to try and enumerate permissions in this case. This will have lit up somebody's alerts like a Christmas tree. The point here is that nothing is ever entirely secure. We can run intrusion detection, which we actually have on previous clusters, but even then a misconfiguration there might lead us to a vulnerable position. So running the last line of defense with something like this, these are scattered across my infrastructure, my home devices, my laptops, gives us that last indication that actually, despite our best efforts, things can always go wrong. So what does that mean for us here? We didn't get into the cloud account. We detected the attack at the very last moment. Running honeypots and canary tokens can be done in a Kubernetes cluster, can be done externally. There is a great startup called Thinks to Canary, which will do this for you as well. Making attractive names for things that shouldn't be enumerated is a relatively simple way of doing this. And of course, integrating with your security operations center is the mechanism that large organizations can use to ensure that they can detect the attacks that we know a Kubernetes cluster brings. There are lots of different lessons to be learned from Kubernetes breaching. If you want to learn more of them, the CTF tomorrow will go into more detail. But for a short initial list, the levels that we have to consider are multifarious and complicated. The treasure map, again, is a useful way to go through the CTF and any sort of engagement. ControlPlane do all sorts of things. We've just expanded into North America and Australasia. We can help you with any of these things. Please do have a chat to one of my lovely colleagues if any of these things interest you. And with that, thank you for your attention.
Brilliant. We've got maybe 2 minutes for a quick fire question round. I think there's a mic runner. For the next talk? Yes. 2 minutes. Any questions quickly? If not, I'm sure Andy is more than happy to be kind of collared in the corridors or something. I'll probably remember these.
Hey, yeah, thanks for the talk. That was really good. In the other room, there's been a couple of talks about eBPF, right, which is talking about kernel modules and all that. I would just really, what are your views on the security implications of all that from someone that hasn't thought about it at all yet?
That's a very good question. eBPF goes through a triple transpilation style. So it goes through 3 state machines in an attempt to prevent a bypass. There is a new kernel capability called cap-perfmon, and there's a secondary one to do with eBPF in the net or BPF in the name. Because it's running user-provided code in the kernel, it is always a danger zone. And a number of container breakouts have been related to the access to those 2 new key capabilities. Like everything, it's a compromise. The introspection and the speed, because everything's asynchronous with the hooks, although it's changing slightly with the new BPF LSM. There's a really interesting post from Cloudflare about a BPF-based Linux security module that actually allows you to do synchronous enforcement with an asynchronous system, whereas before you would use seccomp and it would just give you an ambiguous, what error would it give you? Basically a segmentation access fault error. eBPF can give you a lot more visibility there. It's a lot faster. But like all things, there's a balance and there's a compromise there. One of the Google, some of the Google Project Zero team hate it and think you should never use it. I think there's definitely a place for it, and the new tooling that uses it gives you such a performance advantage that, again, there is an elevated risk, but like all code, we want things to move quickly and be fresh. So yes, non-committal as I could possibly be. eBPF's really cool. Definitely use it. Just be aware that there are some side attacks.
Great. Cheers, Andy. So the next talk we have is The Dark Side of GitOps, Unanswered Real-Life Challenges by Adam. We do have a little spiel as well. So,
Okay, should I plug this? Or we can switch it to the other side if it's easier.
I'll let you introduce yourself.
Okay. Okay, so... Okay. Yeah. SZUCSITG. T, not D, T.
Oh.
T, like Thomas.
Oh, T.
T, yeah, that's the one.
No wonder.
Sorry, for those that have just arrived, we're running about 10 minutes late. So everything from here will probably be 10 minutes knock on. We'll try and take 5 minutes from the coffee break to make up for that, but we'll see how we go.
Okay. Okay, hello. My name is Adam, or actually, my name is Adam Szücs-Mátyás, and thanks for attending today's session. This is one of my first big conference talks, so please be gentle with me. So I'm working as an architect at LastPass, and basically, if you don't know LastPass, the product is not just a password management solution, but also we have single sign-on and multi-factor authentication for enterprises. And just some small facts about our company. So practically, we have 33+ million users and 100,000+ businesses using LastPass. And we have an App Store extension rating for Chrome and other browsers as more than 4.5. And also, we were the first to offer passwordless login without a hardware key. And also, we have dark web monitoring for every user, so you can get notified if there is a breach with your email addresses that's stored in LastPass. So basically, when I joined the company a year ago, actually tomorrow will be my 1-year anniversary. So we starting from a hybrid model, so we have both on-prem data centers, and we use multiple cloud providers, which obviously grow over the years. So the automation got really fragmented. We have basically when I got there, we joked that if you know a tool, then we definitely have it. So you probably know this type of stuff. So also in this case, we have both containerized and VM-based workloads, because obviously some stuff are already designed for cloud environments and Kubernetes. So when we started this year, we have a big push to move to the cloud. But the decision was just not to lift and shift, but also standardize on top of Kubernetes. And during that time, we actually decided to reevaluate the complete tool chain what we're using, because as I mentioned, the automation was quite fragmented. Also, one of the business initiatives was to use AWS only for production workload. For testing reasons, we keep other cloud providers, but production is AWS only. And also, we agreed that we will move policy decisions for shifting left practically. So these will be introduced as well in the pipelines. So because LastPass was previously a part of LogMeIn, and which now called GoTo, but in last December it was announced that we are spinning off from GoTo. So we are creating a completely new AWS organization, which is good because we start from a clean slate, but also this is terrifying because you have to build everything from scratch practically. So in that design, we use heavily Control Tower for deploying these workloads, and also using a centralized network account following AWS best practices. Besides that, we use also hardened service control policies. If you are not so familiar with AWS, you can basically manage centrally some policies that will be enforced even with administrator privileges within the accounts. Yeah, and also during this time frame, we are working to separate our secure software factory completely from everything, and this is also posing some challenges. So, when we were discussing the requirements for the basically the deployment archetype, as I mentioned, we were doing Kubernetes-based deployment, so the reasonable choice was to do EKS. And for EKS, obviously, there is multiple options, but we settled on top of Battle Rocket, which is an immutable OS. If you haven't heard, definitely try it. It's much better than using Amazon Linux for security perspective. Also, we agreed that we won't have any IAM users or access keys in the environment, which can be enforced through these SCPs. So if you have the chance, please disable them, so you don't get compromised as it have been shown like a few minutes ago. On the GitOps side, I'm an avid Argo CD user for almost 3 years now. So this was a reasonable choice for on our side that why we want to do our GitOps deployment. We will use Argo CD, especially it has a nice UI that is helping the onboarding of new people on the platform. However, we also wanted to move from YAMLs to software deployment, and this is not easy if you want to do GitOps model. And to be honest, we couldn't solve it perfectly either, and we tried a lot of approaches. And as I see Victor here, don't take offense on crossplane. So yeah, I will talk about that. And also, we decided that we don't hard code any parameters, because obviously if you check into Git, then if those change, you have to update your Git repositories, which is painful, but it's not that easy as you imagine. So hopefully in like 10 minutes, we will build our own LastPass environment, at least in theory. So basically what we will need clusters, because obviously Kubernetes run on clusters. Obviously we need some AWS infrastructure, like databases, KMS keys, S3 buckets, depending on what is your environment. You need to create all these auxiliary stuff. And obviously we need to deploy the GitOps ControlPlane, which is tricky if you want to deploy it from code. So we will get there as well. And for the deployments, you could use many tools: Helm, Customize, Pure, Kubernetes Manifest, or other means to deploy. We talk about that as well. And obviously, if you want to get rid of the access keys and you want to have short-lived tokens, you need to create for those workloads IAM roles and policies, and even for the Kubernetes-based services, you need to do those as well. And unfortunately, you will definitely end up with secrets. At least if you use some traditional relational database, those are still password-based, so you have to work with them. So for our first try, we attempted to use Cluster API, which is obviously Go-based software. It's supposedly GitOps friendly, but actually it didn't work out, because when we wanted to deploy the AWS provider, it ended up using shell scripts, and a lot of issues come from that. So it's replacing environmental variables. So we had to patch it out with Customize, and it was very ugly. So the other issue that we faced, that Cluster API implementation wants to create its own network. As I mentioned, we have a centralized network account, which is with resource share, deploys a read-only configurable VPC and subnets and everything else to the accounts. You cannot modify it. So if you don't want to create cluster API based VPCs, then you must hard code it, which was against our initiative. Also, Argo CD cannot consume those cluster secrets that the cluster API creates. So there is a gap as well. And also there is always the bootstrapping problem because cluster API is a Kubernetes-based approach. So you need a Kubernetes cluster to bootstrap Kubernetes clusters, which there is a solution, but then you have to spin down the original Kubernetes cluster and move those resources. So you get into this kind of really difficult bootstrapping problem. And even if it doesn't require access keys for bootstrapping, it still complains if you didn't give it at least some dummy one. So it's not fully IAM roles for service accounts compatible, which is AWS magic for getting access to Kubernetes workloads to AWS. So what we did? We went with Crossplane for the infrastructure part because we thought that it's a good idea. But Victor probably aware that it cannot consume existing resources. That's an ongoing issue for years now. So practically, again, with the network account, we either fix the VPCs with IDs or cannot use them at all. So practically, Crossplane works great if you only use Crossplane. But that we cannot do it because obviously we have other teams to work with. We cannot enforce certain technologies to everybody. So also we could think about that we could create an EKS cluster, but as I mentioned, we wanted to move to infrastructure as software, not infrastructure as code. So that will create a couple hundred lines of YAML, which needs to be maintained. And other than that, we also run into some minor issues, like we cannot generate password with Crossplane for RDS to expose for our workloads, and that's kind of an issue. And obviously, if you want to hide all this complexity from the developers, then everybody needs to create some kind of XDRs. It needs to be versioned. So we are somewhere better, but not completely there. So how we can move forward from this? Actually, we tried CDK. CDK is obviously not GitOps, but it's also not completely bad. I mean, there is some issues with CDK, but it works. So basically, at least it's infrastructure as software, so we could use like TypeScript and write actual test for the TypeScripts. You don't write tests for YAMLs. I mean, I've never seen it really in practice anywhere where I work. Also, CDK itself gives you high-level abstractions over CloudFormation, but also we can do our best practices. So actually, we created a couple of NPM packages that is codifying like how we deploy Kubernetes clusters, publish it, and then import it as well. And also, the question is the bootstrapping. So how we managed to get to deploy then Argo CD and the secrets. So that's an interesting challenge as well. So basically, Argo CD is deployed with its Helm chart with some basic config, so it can sync from its repository where we store all the configs. Obviously, for that, we need to provide secret to pull from the Git repository. So that's stored in secret manager, and we use external secrets operator to create that secret from secret manager, so Argo CD can bootstrap itself. Also, in our case, we use Cilium, so we need to remove the AWS CNI and the kubeproxy. There is some high-level abstraction with Lambda functions to do that, so we actually do that and then deploy Cilium in a kubeproxyless mode as well. So obviously, now we solve the Kubernetes part. We have ControlPlane, but what we do about the infrastructure? So about CDK, the great is it works great with AWS, obviously. So it's easy to deploy other resources. You can read out parameters from the live accounts and things like that. But obviously, some things is not that easy. So the secrets are structured based on convention, due to the fact that if we deploy those secrets from individual stacks, then basically they get entangled and the CloudFormation deployment is very long, and obviously it doesn't have the right boundaries between the applications. So this was the way we could figure out that how we can manage the secrets part. And because of this, we can keep the stack separate, and it provides granular deployment model with a multi-stack approach. And CDK is not perfect either. So we identified a couple of gaps, like it does not support MySQL users, it does not create Kafka topics, so we created some custom Lambda functions to actually deploy those dynamically. So we got there, so we could manage our infrastructure more or less. So how our cluster is designed. So practically we use an Argo CD per environment, and that manages multiple clusters. And how we manage those clusters is that the cluster secrets is created when we create the new AKS clusters, and it's deployed into the management cluster. And we are using the labels within those cluster secrets for Argo CD application sets, so the cluster resource generator can pick them up and deploy whatever is needed based on those labels. Those are standardized with an enumeration in TypeScript and things like that. So this is how we tie them together. But obviously need to pass sometimes some parameters like role ARNs for like Carpenter. So we actually do annotations to do this. And as I mentioned, we have a dedicated Argo CD per environment. And because we are, even with we are using CDK, we are really keen on not doing anything manually. So the Argo CD web UI is read-only, even for the admin kind of people as well. And for the image updates, we write it back to Git. So this is how we try to keep everything in sync. So for the deployment, what we do is that Argo CD, as I mentioned, bootstrap itself with project, roles, SSO, so we don't have to deal with that in the CDK part. And we standardize common tooling with those application sets, so it's deployed everywhere uniquely. And because we use these cluster secrets, these application sets provide automatic enrollment of new clusters, so Argo CD and the manifest doesn't need to be aware how many clusters will be at the back end. And also we move from Helm to Customize, so we don't have templating, we don't have like these weird switches that you don't know which template you will end up with based on who configures that in which environment. So Customize makes it clean and makes it easy to actually enforce those policies in pipelines. What will be enforced upon admission, because if you use a GitOps-based deployment and the policies will deny the deployment, then you will get basically stuck with your deployments. And it's important to move those into the pipeline to actually be checked as well. And also because we standardize on our Kubernetes cluster and manage through like these labels, it's easy to enable auto scaling. We just turn on the flag and then it will deploy Carpenter, creates its roles and everything else. On the IAM roles. So practically, we use IAM-DSV to enable clusters. If you are not aware, then this is how was credit one was popped, that you can do lateral movement, like leveraging the instance profile from the underlying VM. So if you have IAM-DSV2, set it to hop limit 1, so you're not able to query the metadata server from the pods, for example. Also, obviously, the service account access is least privileged because security is obviously utmost important for us. And what keeps those IAM roles with the service accounts in sync is the naming convention, which we use like region, cluster name, service name, things like that. So you have to obviously figure out your own, but this is how we kept in sync. And as I mentioned, every single policy has to go to CDK, so that's also something that we are doing. Yeah, and the last topic, the secrets. So what you can do about that? The easiest way, if you use short-lived tokens, everything is provisioned on demand, and this is what we try to do. But as I mentioned, like our RDS doesn't support that really. There is some support, but you should not use in production. So password-based services creates their secrets on the fly and expose it through secret manager and external secrets operator. And also we have some external API keys for our third-party SaaS vendors. So those also needs to be stored in secret manager. And before I'm getting at the end, why we use external secrets operator. So first we wanted to use the Kubernetes CSI driver because storing secrets in files is more secure than environmental variables. but not all the tooling supports it. And actually, I think still the Kubernetes CSS driver doesn't support secret-only deployment. It can only deploy secrets if you deploy if you mount that file already, and then it can create a secret. Also, we realized that some of our configs require some kind of templating, and this is much more flexible. And also, if you have some workload that is requiring multi-namespace information, then you can do it from a single custom resource. And obviously, we are not finished with our work. There is still a couple of things to make. So basically, where we kind of lack, even if we deploy everything from CloudFormation, the drift detector CDK, the CloudFormation drift detection is not integrated with our pipelines, so the reconciliation is not automatic, but because we are doing from code, this is not a big pain right now. Also, I would like to have a LastPass Go SDK, so we can actually sync from our LastPass vault to AWS, those API keys, for example. And what needs to be solved is how we can integrate our observability quality gates into the release propagation. And we started to use AWS controllers for Kubernetes, which is actually kind of like CrossPlane, but just AWS. Not every service is covered, and there is some minor issues, but more or less it works. And we are planning to figure out where we can actually leverage it. We already do it for like our software factory to create ECR repositories on demand, so we don't have to create everything from CDK, and it can be easily managed from the same deployments that is doing the pipelines. And we are also considering to onboarding the higher level deployment API. So, summary. My suggestion, if you go down this route, then, and if you are in AWS, leverage CDK, because you can actually do custom reusable packages, as like we do for our NPM packages. And also you can write tests, and you can do automatic documentation generation. So you can publish it for your developers, so they can practically consume your API and libraries very easily. Also, try to keep as few secrets as possible, because they are just pain in the ass. And use just-in-time authentication, because it's more secure and easier to manage as well. And because we could not figure out what is the right toolchain, I think naming conventions are important, so try to establish something with your team. It doesn't have to be perfect, it just needs to work. So thanks for your attention, and if you have any questions, let me know.
So we are running kind of 10 minutes behind, so we have time for maybe 1 or 2 questions. If anyone has one, just pop a hand up. Yep, one at the end.
Quick one. Why do you move from Helm to Customize?
So basically, as I mentioned, that in Helm, you always do templating. And basically, that's a Turing-complete language. So we ended up one time with a 100,000 line values file and with lots of Helm template functions, and nobody could even figure out what the hell will happen when you parameterize it. So this is not an ideal state if you want to do GitOps, because then you cannot know in your pipelines what will be the release state. So if you need to enforce policies or want to use admission control, then you need to know what will be deployed. Otherwise, it just will blocked when the API server will be hit. So this is one of the big issues I see with Helm and GitOps. Thank you.
Minutes behind. Up next, we've got You've Been Holding It Wrong by Gerhard. So it's this USB connector.
That's better. We're going to go in 1 minute, less than 1 minute, so if anyone else wants to join us, now is the time. Or leave, that's fine too. That's okay. All right. If this looks like your pipeline, if you look at it, all those balls, all the code, all the services, making their way into production, staging, QA, whatever we have running, that is fairly accurate, I think. If YAML could be represented in a visual, I think this would be it. This is what I imagine. And I think many of us have something like this. Some of us have monoliths. That's okay. Things get complicated in a different way. But this is what a pipeline that I think is wrong looks like. So this is a question for you. How do you deploy to Kubernetes? What does that look like? If you think about it, if you try to imagine it, can you even visualize how your code makes it from your laptop into Kubernetes? What happens? I think most of you will struggle because there's always things changing, updating, new things. There's always a complication. And to be honest, should you really care? I think most of us shouldn't really care. So we put these machines in place. They look a bit like this. They do magic. Okay. You just sit back. There's nothing to just watch it. It's amazing. So you have GitOps. So how do you get GitOps? Can I have one, please, or two? It's magic. It works, it's great, but how do you get it? This old chestnut. You want to deploy to Kubernetes? You need Kubernetes. You can't deploy to Kubernetes. There's something else that needs to be there to orchestrate all the things. There's so much complexity, and you end up with something like this. It's fun to watch, but what happens if something goes wrong in one of those clusters? It's not your problem, right? And then there's a few brave souls that just kubectl or KubeHuddle or kubecontrol, however you want to call it. Some of us, that's just how we roll because it's easy, kind of, but you know. I'm wondering if we could encode the DevOps knowledge. Would that be possible? Maybe we share it so that people can do things in a way that it doesn't feel like magic. They can see it, they can understand it. It is code. And you can visualize what happens. This is what it looks like, in my case, to create a Kubernetes cluster. Because we're at KubeHuddle, we're using Civo, it's in our lanyards. That's what it takes to create a Kubernetes cluster. Civo, Kates, create. You provide it an API key, you give it a client, you give it a cluster name, and it just works. So can I see the implementation, please? Can I see the code? Okay. This is what the code looks like. It just uses the Civo CLI. Kates, create. It chooses a CNI. I propose that we call that the Liz CNI. That's my proposal. And there's a couple of other things happening here, but really it's just the Civo CLI. That's all it takes to get a Kubernetes cluster. So what would that look like in practice? So let's see what that would look like. So if I do dagger do Kates, the command runs. If some of you are thinking, hang on, isn't this a little bit like make? You aren't far off. So the command ran, it finished, it's trying to figure things out. Sometimes the API is slow. By the way, if there's anyone from Civo here, I would love, yeah, there you go, that's a good one. Failed to create a Kubernetes cluster, one already exists. I would like to talk to you about that. This should be cached. This action should be cached. The demo gods. This is a live demo, and what it means is that this operation should be cached. For some reason, the cache isn't there. It's a miss. And what it means is that while the cluster exists, the command, when it runs, is not idempotent. Everything is the same. It's all there. But for some reason, it's failing. That's OK. I'm not going to debug it now. What about if I want to see some info about the cluster? I can run it locally. This is what it does. It shows me the info. Sometimes it's slow, but not this time. Okay, we can see the cluster, we can see details about it. It's all local. Great. I don't have to use Dagger, by the way. I can use anything else that provisions clusters. Again, there's many valid approaches. It was just convenient for me. The other thing which I will need to do, and I wish I didn't have to, for example, I can configure DNS, I can bootstrap the cluster, so it's all self-contained. I'm going to open this. This is a link here, this emoji. The reason why I couldn't use, for example, external DNS to manage my DNS when I provision services is because there is no Civo DNS provider currently, and this is fairly recent. And my last comment was right here 2 days ago. I was saying I was missing as I was preparing for the talk. It would have been nice to use it. But that's okay. I could work around this limitation, which I didn't even know it existed. Again, with a Civo CLI, I could configure my Kate's DNS. Now, the bootstrap, I could try running it again. Let's see what happens. If I do dagger do Kate's bootstrap. This, even though it will run again, it should apply the same thing. All this runs locally, but the thing is, it doesn't have to run locally. It's just a convenience. And it applied things, it's all self-contained, everything worked. Okay. What about accessing the cluster? So I can do Kate's config, I can source, I can get my credentials, and then I can K9S, I can CLI into it. This is what it looks like if I do that. We shouldn't really need to do this. Okay, again, it's a convenience, it's easy. It's usually the people that build it, you want like a nice access, and those that are really curious, you can go there, but you shouldn't really need to do this. So what happens when you get the cluster? Well, this is again what the interface looks like. We configure the application, and that's what we're trying to get to. We're trying to give our developers a nice experience, and they really shouldn't be aware about any of this. It's there for us, and it's for those curious. This is how you can access it, this is where things are, this is how you can interact with them, but you shouldn't need to know this. Okay, so there's Argo CD, that's what the bootstrap did. By the way, it installed Argo CD and a couple of other things. This is my application configured. It's all done, everything is there. So the Kubernetes cluster really, it's ready to go. A developer would just, what do we do? What do we say to developers when there's Kubernetes? What normally happens? By the way, I would encourage you to take advantage of being here in person. You can talk to me, you can heckle me if you want, that's okay. You don't have to, but... So what do you do? What do you tell to your developers when they have Kubernetes? Do you give them? Right, yes, that happens a lot. Any other examples? Something that maybe you did if you're running, if you're an SRE, DevOps, whatever your title is, sysadmin. Okay. This is what developers want to do, and this is what they should do. Just push, okay? Something I think went wrong after the PaaS, after Heroku, when it was all a Git push. Developers shouldn't really care where their application runs. I mean, they should understand what is happening, what is in production, but all they really care about is Git push. If my tests worked, if everything looks good, this should just happen magically. All I want to know is Git push. Okay. So we have our Kubernetes cluster. We can try and understand what is happening locally. Now, we shouldn't, but as a developer, I don't really care. So how do you GitOps? There's GitHub Actions, there's Dagger, and there's Argo CD. You've already seen Argo CD. This is what the GitHub action looks like. And if you look on line 31, it just says do app. We did Dagger do Kubernetes, Dagger do this, Dagger do that. But now we're using Dagger in our CI to just get the app out there. It's all configured with GitHub Actions. By the way, it can be any CI. It doesn't have to be GitHub Actions, but it was just convenient. The code is there. And I'm wondering what happens if I run this locally. What happens if I want to test what that looks like and how that works? So if I do Dagger do app, what happens? It's pulling, it's building, it could be testing. In my case, just took 5 seconds to do it all. And there's a difference. There's a difference locally. My deployment YAML has changed. All this happened in 5 seconds. The image was built, the image was pushed, the YAML was updated. Do you see where I'm going with this? What would happen if I committed this? Any guesses? Okay. What is the last thing that happens in this GitHub action, line 37? It commits. That's it. We build the app, we commit the manifest, we're done. Okay. It runs, it takes really 15 seconds in this case, all of it. By the way, in reality, it will be slightly longer than this. I just wanted to show how easy it could be and how quick it could be. Tests can take longer. There's other things happening. But this is, at the core, what you should actually be doing. And when I say you, developers, they get push, they see this thing running, everything's good. My app should be out there. We can see the commit, the result of that action finishing. It just commits to the repo, it updates the manifest. And I think you kind of know where this is going, but how about we try it for real? How about this is the app, and by the way, this is live, so you can check it if you want, but this is what it looks like. Let's go back. This is Argo CD. This is the app. Do you remember the iPhone 4 and how you would hold it wrong? So how about we show the world how to hold your iPhone right? By the way, this is not an issue anymore, but it used to be. All right. So I'm just going to blow this change away because I don't care about it. I will, let's see. I'll go to the app. I'll go to the HTML. I'll take this one. And I think it's even here. Look at that. Right to wrong. No. Wrong to right. The other way around. Wrong to right. All right. Let's see the change. There you go. So how to hold it right. Okay. Let's commit. How to hold it right. Let's commit. I'm a developer right now. All I do is commit and push. That's me pushing right there. Okay. So what happens behind the scenes? Let's go to the GitHub repo. By the way, Gerhard KubeHuddle. That's it. If I refresh it, I can see my commit, how to hold it right. This is already running. Let's look at the details. It's building right now. Let's see what happens. The same Dagger do. We haven't seen this yet, but we will. And it's finished. That was really quick. So what happened in the build? What did the Dagger do app do? We've already seen some of this. There's a verify. We'll talk about it a bit later, what it does. And all done. It went through the changes, committed. It's all there. Okay. So if I refresh this, I can see there's a new commit. Save new app image reference. Let's have a look at Argo. What does Argo say? I'm going to refresh this. Sync OK. That was 12 hours ago. Let's see if we can prod it. Now this will automatically happen if we were to give it a little bit more a few seconds ago. Sync OK. There we have our new app instance. It's already spinning up. I just speeded things up. This would have happened automatically. I just wanted to prod it a little bit so it works a bit quicker. And if you refresh, there you go. That's how you should be holding your phone, apparently. Okay. behind the scenes, this is what actually happened when we do Dagger do. Dagger do version 0.2, and this is important. It just reads the config from some Q files, and it runs the operations in BuildKit. Some will be cached, some won't. There'll be some cache misses. But all of this is transparent. So you may be wondering, what do the Q files look like? Well, I'm glad that you asked. Let's have a look. There's a KubeHuddle queue right here. This is what this looks like. And I would like to thank David for contributing the kubectl package, kube control, kube. How do you call it? How do you pronounce it, David? You're here. Kube control. There we go. So thank you, David, for contributing kube control to the Dagger package, to the Dagger universe. And what that meant is that I use that package right down here in my application to build, to publish. Where was it? Docker build. Let's see. Where was it? Kube config. There. To bootstrap the Kubernetes cluster. So I just basically applied some manifests. There were some bootstrap manifests, which I applied. That's how I made use of that package. All of this controls not just the pipeline of how to build the app, but also how to bootstrap the cluster. And I don't have to use all those actions. I can do. I can run them locally. I can run them in CI. It doesn't really matter where they run. It's just a binary. It's a statically compiled one. Wherever it runs, the pipeline will work the same. So I say pipeline. Why do I say that? Well, there's the app action right here, which creates the app, and this does quite a few things. The first thing which it does, it pulls a base image. So this is the base for my application, and I'm using the ChainGuard Nginx image in this case. I can verify it. There's a very nice link right here. I have it open. I can check what that image looks like. It's good. I like it. It's signed. It looks safe. Great. It verifies the pipeline part of the verify step. When I do Dagger do app, it runs the verify. It's all there. And if it passes, it continues. If it fails, it will stop. It builds my image. I'm building a container image. I'm assembling just some files. I'm taking some HTML. I'm configuring Nginx. I'm changing the configuration. Then I'm publishing it. And all it is, it's a Docker push right here. That's it. And it publishes to GCR, Gerhard KubeHuddle. It configures the registry username, the registry password. And then it's the manifest. The manifest is, I would say, fairly complicated. It could be simpler. But all it does, it's using YQ to modify steps, YAML. It does an in-place change. It templates the container image. That's it. And then it exports the directory, which means that that will be written back out to the host. And that's it. Okay. The truth is that some people, they look at Q and they say, you know what, it's too much. It's too difficult for me to go from YAML or my programming language to something new. I wish there was an easier way. And for that, what we realized, what the people were asking us, they weren't asking us for YAML, they were asking us for their language. They want to declare pipelines in their language. I think we've seen this with CDK in our previous talk. Some people already use TypeScript. They're comfortable with it. Why would I need to learn a new language? That's a very good point. So this is the next version of Dagger, which allows you to declare pipelines not only in Q, Go, TypeScript, Python, whatever you're using, Ruby, anything really that you're comfortable with. And what that means is that the barrier of entry is much, much lower. Even YAML. Now, it's possible. I wouldn't say it's a good idea. It's possible. And that's why it's not here. We're not thinking of implementing it yet, but we could do it if people really want to. And the difference is that the build kit, and this is the thing which runs the operations, it's all built in. It's an implementation detail. It's a single binary. So what does that look like in practice? Well, Solomon gave a talk, I think about a month ago at VMware Explore. He introduced Project Cloak, which is the code name for Dagger version 3. And you can see a live demo of what it looks like right here. The QR code works. Otherwise, I think if you go to Dagger.io, the Twitter account, you can see it. Okay. So what does it look like to use Dagger version 3? Okay. So what I have running locally is, first of all, there was the cloak binary. I can start it again just for you to see cloak dev. And when I run it in dev, it basically provisions itself. And it provisions itself, again, it's using itself to provision itself. It's very meta. And it puts up an API endpoint, 8080. And that's exactly what I have loaded here in my browser, 8080. So in this case, what I'm doing, I'm sending instructions to Dagger for various operations, and I'm using GraphQL. I'll make that a little bit bigger. This is the GraphQL interface. So what is happening, core, that's the entry point. Obviously it's a query, it's a GraphQL query, there's core. And the first thing which I do, I want to pull down the Civo image. Now, I don't know if there is an official Civo Docker image, container image. I'm just using nixery.dev. You can assemble images on the fly really, really quickly, and images. I am running a command, I'm running an exec, and I'm telling it Civo API key save, load from env, and the env is a secret. I pre-configure this, and I'm just using a secret ID. Now there's integration with Vault, there's integration with other things, we have examples, but in this case, I just configured it once so that you don't see the API key, and then I'm just using it. And then inside, I'm taking the file system layer of that operation, and I'm running Civo k8ls. And I'm giving it a name, I'm giving it a list. This is the list operation, and this is the show operation. So if I was to run it, all of this, and we'll see it here, it runs against the same instance, and it's sending those instructions as I was telling you. It's all build kit, and it's all self-contained. Secret not found. Okay, something went wrong, but the output that we should have seen is, let's see, well, it's not there anymore. Okay, I'm not going to debug it, but the output that we should have seen, and that's why I have this, it's on the right-hand side. We would have seen the operation, would have seen the output. Okay. What if I wanted to run it not through the interface? Well, we can do cloak do, and that will very soon change to Dagger. We can give it a file, we can give it an instruction, and it would have run the same operations. Now, I could try running it, but I think it will fail with the same issue as before with image. Okay. We can see internally how it runs the command, and we can see the output, and we would have seen that on the right-hand side. Internally, by the way, this is all public. If you go to github.com dagger, there's the cloak branch. You can see diagrams to understand how it works behind the scenes. It's all seamless. They're all the steps, the pipeline is running inside Dagger. And what it means is that whoever Dagger runs, the pipeline will run the same. It doesn't matter whether you use Jenkins. You can use Jenkins. That's okay. You can use GitLab. You can use Tekton. Anything you want, it will work the same. And that's the beauty. It's the portability of the pipeline. I think of it as a Docker moment for CI/CD. You can encode the knowledge, you can share the knowledge, you can write packages, you can share the packages, and it will work the same regardless of what you're using today. I talked about the repo. All the code that you've seen me demo, it's in GitHub KubeHuddle. We've seen it here. We can see the integration, the demo, everything. And there's a couple of interesting things here, including some Aws Keys, a recording for various commands. So everything that was not working, I can promise you it works. You can play it, you don't have to run the command. It's all there. The slides that I gave are publicly available, and the talk, when it will be recorded, I'll add the link. So everything will be in this repo. Now, there's one more thing, one last thing. I talked about the verify, and I showed how that works. It's just some commands that run some steps. It's verifying that the base image that I'm pulling is exactly as it was intended. And this is really important to make sure that things that you're consuming are what you think they are. Can someone tell me what I have not done in my pipeline? Who's been paying attention and is brave enough? Yes? New Docker file. No, I mean, I'm running a Docker build, I'm pulling the image, and then I'm verifying the image, so I'm running a few Docker commands. But it's something that I'm not doing for my image, for my application image. I'm not signing it. And I'm not verifying it in Kubernetes. I should. Now, if I had more time to improve this talk, that's what I would do next. I would make sure that my images are signed. And I'm verifying them, maybe via an admission controller, before they hit my Kubernetes cluster. And that's it. That was the talk. Thank you very much.
Great. So we have time for 1 or 2 questions. If you just pop a hand up.
How do you manage your build kit agent to be auto-scalable? Because that's needed for Dagger.
So the build agent, right? That was the question. Okay. So in my case, I'm using GitHub Actions. Dagger do runs in the context of the GitHub runner. So however GitHub Actions scales, however it's configured, whether it's the free tier, whether it's self-hosted runners, that is separate from Dagger. Dagger runs in the context of a build agent. It doesn't have its own build agent. So whatever you have for your CI/CD, that's what it will use.
Yeah, but you cannot really put build kit into Kubernetes easily within secure context. So
You can't do what?
build kit agent in Kubernetes with secure context, it's really hard to
Right.
manage it.
But in this case, the build kit, it runs in the context of the GitHub Actions runner. I'm separating CI and CD. CI, all it does, it runs whatever infrastructure I have to build the artifacts. Argo CD is running in Kubernetes. It pulls down those artifacts, but there's no access between Dagger and Kubernetes. That doesn't exist. So whatever configuration I have for my CI system, Dagger runs in that context. It doesn't spin up anything new other than what I have available on my existing build agents today.
Okay, thank you.
Okay.
So we just think you've noticed the coffee break is now until 11:40. So apologies, it gives you kind of like 7-8 minutes to mad rush up, grab a coffee, and come back down. Yeah. So next talk will start at 11:40.
One thing which I forgot to mention, I have a few stickers. If there's anyone that contributes to Dagger, I have a few stickers for you too, so you can come and see me, and I can give you some stickers. Thank you very much. Thank you.
Is that on? Yeah? Hello? Right, sweet. Okay. Right, everybody, settle down. Right, good morning, everybody. My name's Rick Featherstone. I'm Head of Engineering at ControlPlane. Thank you for joining me this morning for my talk, Who Can You Really Trust? So we'll crack on, try and get some time back. So what does trust mean? We'll start off by defining trust in a way that suits the narrative of this presentation, which will just make it easier for me. So just a quick search of the internet. I found some definitions that just work in the way that I want them to. So basically we're associating trust with something or someone. We're associating trust with an identity. And that's primarily what I'm going to be talking about this morning, workload identity. So why do we need a workload identity? What's the fundamental question that we want to answer? Who are you? Who can vouch for you? What can I use to convince you who I am, that I am who I claim to be? How can you verify that I am who I say I'm going to be? When does workload identity need to prove its identity to something else? Where can a workload get that identity from? What can a workload do with its identity once it's got one? And then we'll finish out with how can we use hardware to get a stronger guarantee of identities. So let's start with some examples that we're kind of coming across regularly at work where we need a workload identity. So we'll start off with secrets management. We've got lots of different kinds of secrets, passwords, secret keys, access keys, SSH keys. We use secrets management to control and order access to those, to manage the rotation of those secrets or dynamically generate secrets. We don't want them lying around on the file system for Andy to come in and enumerate them and use them to get into things that you shouldn't be getting into. We want them to be time limited and rotated regularly. But now we've put them into a secrets management system, we need a way to access those in our workloads. And workload identity, that's our secret zero. So we need that to be able to access these secrets. Zero trust architectures. So here we've got a Kautz triangle from Frederick Kautz's talk, Economics of Zero Trust. So identity is foundational in zero trust architectures. This is our authentication. Policy, this is what can you do with that identity. This is the authorization side of things. And then control, this is how we automate things so that we can do this control at scale. So we're removing the implicit trust based on locality. So you're in this safe zone, you can talk to anything else in this safe zone, and replacing it with explicit trust based on who you are and the policy that allows you to do what you want to do. So you are X and you are or you are not allowed to talk to Y. And we also kind of want this identity to communicate securely, so TLS or mutual TLS. And then supply chain security, where all the cool kids are playing these days. I couldn't see any kind of supply chain security talks on the program, but from Dan's talk there, he kind of categorizes supply chain security threats under kind of integrity, quality, malicious maintainers. But we'll kind of focus more on integrity because it fits with the sort of workload identity side of things. And then to kind of mitigate those attacks, the ones that we're kind of most interested in are signatures, attestations, and PKI. So kind of in integrity, these are things like backdoors, malicious code from compromised build systems, compromised artifact managers, source repos, distribution systems. We don't want Andy inserting remote shells into our code. So we're using signatures to sign it so we can verify that it's been created by who said it was, who said they created it. Signatures and attestations, they prevent forgery to ensure that integrity. Attestations, they're a signature plus some additional metadata, so they're attaching context to those signatures. And PKI is just about the kind of secure distribution of the public keys. So if you're kind of downloading a package, and the package and the signature and the public key are all on the same distribution website, well, how do you kind of guarantee that that's not been tampered with? So workload identity. So we need it to access secrets, to do identity-based access control, secure communication, to perform authorization against things, to protect the integrity. So how can workloads, how can they get this identity to prove who they are? How can relying parties verify the identity so they can kind of have some trust that the workload is who it says it is? So we really want to know what are the kind of things that we need from an identity document. So well-established cryptographic protocols, they provide us with the tools for a relying party to verify an identity document. So we want it to be cryptographically verifiable. We want to make sure that the identity document only goes to the workloads that it's supposed to. And we want to make sure that they're guarded after distribution. We also want to make sure that they're short-lived and rotated regularly to prevent against them being kind of compromised. We want them to be simple for our workloads to obtain. If we're kind of regularly rotating them, we don't want it to be difficult for our workloads to get hold of their identity. And we don't want the workloads to need any secret material in order to get the identity, because how do we kind of distribute that secret material to the right place? And ideally, we don't want the workload to have to know the identity that's looking for in advance. So how can we do that? How can we represent an identity? How can we validate that identity? There's kind of two key formats of choice for identity documents: JOTs, JWTs, and X509 certificates. So with a JOT, we've got claims, which are just a set of key value pairs in the token itself. They're providing metadata about the identity encoded into the token, information about who's issued it, and the validity period of the token itself. JWS defines how we can attach a signature to that token and how we can verify that signature. Specifically the compact serialization format, which is compact and URL safe. So we can use that in HTTP authorization headers as we're passing this identity around, and that's kind of the most common way that these are sent around. If you are using JOTs as your identity, make sure that you're using TLS to prevent that token being intercepted in transport and kind of replayed. So that's a good document format for identity. But how can a third party verify that token? Well, we can use a subset of the OIDC specification to verify that document. We don't need issuer discovery, because as we'll see, the issuer itself is encoded into the token. And we don't need the authentication endpoints, because we've already said we don't want our workloads to need secret material in order to get their token. So we want some explicit method for them to be able to get it without having to authenticate and log in. So the OpenID provider configuration, sometimes called the discovery document, that provides us with metadata about the identity provider. And that includes a URL to download the JSON web key set, which allows us to reconstitute the key that was used for the signature, and then we can verify the signature. And assuming we trust the issuer, we can then trust the identity that's encoded into that JOT. X509 certificates, well established and widely used format for representing identity. So we're going to bind an identity to a public key and to metadata. So we're generating a key pair, creating a certificate signing request, signing that with the private key. We're then getting that signed by the certificate authority, who will then create the public key in the certificate, and then we can use that. But we don't really want our workloads to have to worry about that. So if we need to find a better way of kind of creating those keys and the certificates. We also don't want to be kind of binding that identity to IP addresses, because in our modern cloud-native environments, workloads are coming and going, and the IP addresses are quite dynamic. So it's not really a useful identifier. Can 10.10.1.17 talk to 10.10.1.24? I don't know. Maybe it could yesterday. Should it be able to tomorrow? So there's a lot to be said about kind of a human readable representation of identity that's easier to kind of reason about than just IP addresses. And that's where Spiffy comes in. It's this called Production Identity Framework for Everyone. It's basically a set of standards that kind of define a way of kind of dealing with identities. It's got three major components there: the Spiffy ID, the Spiffy verifiable identity document, or the SVID, or the workload API. So the Spiffy ID's got three parts there. It's a URI, uses the Spiffy scheme. We've got the trust domain there, in this example, acme.com. And then an arbitrary path there, which allows you to kind of name your workload. So in this example, billing.payments. The standard attaches no meaning to hierarchical paths. You can kind of use them as you need. But for me, this is kind of the killer feature of the Spiffy standards, is just having this machine processable identity, but also kind of human readable. So it's kind of much nicer to reason about. It's kind of decoupled from where something is running, can be processed by machines, but also read and understood by humans. The SVIDs themselves, this is how the identities are represented and kind of passed around. Three key parts to an SVID document: the Spiffy ID that we just talked about, a valid signature, and optionally a public key. So an SVID is valid if it's been signed by a certificate authority in the trust domain. They're not defining a new document standard. We're talking about the two documents that we've just been talking about, JOTs and X509s. It just kind of defines how we encode that identity into those documents. So in the JOT, we're using the subject field, and the Spiffy ID goes in there. In the X509 certificates, it's going in the URI SAN field. And then the workload API is just how do the workloads obtain their SVIDs and the trust bundles that you use to verify the signatures. So the workloads don't need any knowledge of the identity that they're getting up front. It's all kind of managed for them. There's no authentication because we're using this to bootstrap identities, and where do they get the secrets from otherwise? And there's no TLS on the workload API endpoint, because the trust bundles, the certificate bundles that you're getting from the workload API, they often form your root of trust. So that's kind of the requirements for the workload API. So we know we need a workload identity. We know what we want from a workload identity document, how to represent it. Now we want to know where our workloads are going to get those identity documents. So I'm going to go out on a limb and assume that some of you people here at KubeHuddle probably run in Kubernetes. Yeah, little chuckles there. Fairly safe assumption there. Well, if you are running in Kubernetes, you're in luck. You've already got an identity document in all of your workloads. Your service account token is a JOT. So the service account that your pod is running as, that's already got an identity managed by your Kubernetes cluster, your identity provider. So we need to just talk a little bit about bound service account tokens, sometimes called projected service account tokens because they're using the projected volume API. They're limited to a specific audience. So in this example, we've limited the audience to demo. That kind of prevents a malicious service from taking your token and impersonating you to call somebody else. And they're limited by time, 15 minutes there in this one. So they're periodically being rotated, and you don't need to do anything about that. So these are now the default for pods in Kubernetes. Previously, you would get the long-lived service account token, and you would have to manually rotate that. This is all done automatically, so it's tied to the life cycle of the pod rather than the service account. By default, the audience is the API. So where you're using these to talk to services or other workloads outside of the Kubernetes cluster, you should be configuring a bound service account token for each of these specific use cases and limiting that audience there. And you should be configuring that audience and the expiration based on that specific use case. So how does a relying party outside of your Kubernetes cluster verify your Kubernetes service account tokens? Well, the service account issuer discovery feature in Kubernetes allows you to federate Kubernetes identities with external systems. So Kubernetes cluster is your identity provider. External systems are your relying parties. And it's the same subset of the OIDC discovery spec that was just talking about. So using the discovery document and the JSON web key set to get the keys to verify those signatures. So that allows us to dynamically retrieve the keys, verify the signature. So if we're trusting the issuer, our Kubernetes cluster, we can trust the identity in that job. So we're just going to kind of walk through what this looks like. But in order to do that, we need to decode a job. So we need to know what's in there. So it's a relatively simple serialization format. 3 parts there: header, payload, signature, all separated by dots. The header and the payload are base URL encoded, base 64 URL encoded, separated by the dot, and then the signature is appended on the end. And so we can just, for the header and the payload, because it's just JSON encoded, we can pass that through JQ to have a little peek into the token and see what's going on there. We can't with the signature, but because it's not JSON, but we can just use this to have a look in the header or the payload. So there's no need to kind of copy a production jot, paste it into jwt.io and have a look and see what's in there. You can just do it nice and simple, staying in your own environment with a little bit of JQ magic. So we have a look at a token from a GKE cluster. We've got the header at the top, the payload at the bottom there. In the header, we can see the algorithm for the signature and the ID for the key that's used to sign it. And then in the payload, you've got these claims. So we've got the audience demo there. We've got some metadata about the validity period for the token itself. We can see the subject is the fully qualified service account name. The key field here is the issuer, truncated so that it fits on the slide there. So if we take that issuer and we append the well-known OpenID configuration suffix on the end of that, then we get the discovery document, and that's got some metadata about the token, some of the fields in there, what they mean and things. The key one there is that JWKS URI. So we can take that, and then we can get the key set itself. And this would kind of, as the keys are rotated over time, this will become a set. So using the ID, we can find the correct key, reconstitute the public key from the fields there, verify the signature, and because we can do this by kind of discovering all of the information we need, we just need to maintain a list of trusted issuers, and then we don't need any additional configuration. So we're just a simple protocol. We can get all the information we need in order to verify the signature and therefore trust the identity there. So Kubernetes is providing us with an identity. We can verify that from outside of the Kubernetes cluster. So what can we do with it? Well, we can do secrets management with HashiCorp Vault. It's a simplified configuration over the Kubernetes authentication method. We just need to configure the trusted issuer. Is it better than the old kind of Kubernetes authentication method? That uses the token review API. So Vault needs to be able to access the API server. So if you want your Kubernetes API server to be private, that's not going to work. You need a mount per cluster in Vault so that Vault knows which API server to talk to verify your tokens. If Vault's not running in the same cluster, then it needs a service account token in order with permissions to make that token review call. So if you're outside of the cluster, you need a long-lived service account token, put it into Vault, but then you need to periodically rotate it. With the OIDC stuff, you can configure a single mount for multiple Kubernetes clusters by removing the discovery part and just chaining the certificates together and foregoing the kind of the discovery side of things. The API server can be private, but also with the OIDC stuff, it works with any OIDC identity provider. So you could use GitHub, so your GitHub actions can authenticate to your Vault using the same method. So is this better than the old Kubernetes authentication method? Well, standard consultant response, it depends. So moving on to something a little bit more convincing, Web Identity Federation. Okay, so we're basically, we're taking service account credentials and we're exchanging those for temporary cloud provider credentials. So now we can do secrets management using cloud services, we can do PKI using KMS, we can access any cloud APIs. And it works across cloud providers, so we could use IAM roles for service accounts from AWS from a GKE cluster. So you take the mutating webhook that AWS provides, install that into your GKE cluster, annotate your Kubernetes service account with the AWS IAM role that you want to get credentials for, and then when you deploy your workload, it will automatically configure the bound service account token for you, so that's quite handy. You don't need to worry about remembering how to do that. And it will set up the environment variables needed for your client AWS client APIs to authenticate without having to worry about doing that themselves. So it's using the default credential chain in AWS. So your workloads can now just call your workloads in GKE can now just call your AWS APIs without having to worry about authentication. So that's really nice. And you can do kind of similar things working across the other cloud providers. What else can you do with it? So if you're passing these tokens around in HTTP authentication headers, you kind of you can do some OPA verification because it's just HTTP to get the information you need. You can verify the tokens. You kind of hand crank your own service mesh and do authentication that way if you want to, using your JOTs as bearer tokens. So you can get quite a long way just with Kubernetes service account tokens and the OIDC stuff. But why might you want more? So JOTs, you've not got any keys, so you can't do sign-in encryption or TLS. You've got no control over the subject. It's fixed at that fully qualified service account name. If you want to use the same identity across multiple clusters or namespaces, it becomes a bit difficult. If you've got lots of clusters or dynamic clusters, you've got to do lots of OIDC configuration. You might need to get identities for non-Kubernetes workloads. So that's where Spire comes in. And Spire is the implementation of those spiffy standards that we talked about previously. So you've got the nodes, they run an agent, and the agent will attest the nodes to the server, so the server knows exactly what nodes you're running. That exposes the workload API over a socket, so it's your workloads you'll know which host they're actually running on, and the agent will attest the workloads calling the workload API. So the workloads don't need to know about their identity. The agents will figure that out for them. So you've got specific node attestation plugins depending on where you're running. If you're running your nodes in a cloud environment, you can use cloud instance identity documents. You can use SSH certificates. In Kubernetes, you can use service account tokens or projected service account tokens. So these the node attestation kind of collects metadata, which allows you to kind of map in the registration setting there. And then the nodes run specific plugins, which will do the attestation for your workloads, depending on the type of workloads that you've got. So if you on Kubernetes, you can use things like the namespace, the service account name, the image, your pod labels to kind of map through that registration to get the identities. And then registration is just basically mapping SPIFFE ID to parent SPIFFE ID. So you're tying these identities to specific nodes that are allowed to issue these identities, and the set of selectors that identify your workloads. And so the workloads are just calling the workload API, and it's figuring out which identity to give your workloads without you having to worry about that. So there's an example of kind of doing a registration there. So when you're running on Kubernetes, you probably don't care which nodes in your cluster your workloads are running on. So you can just map the same SPIFFE ID to all of the nodes there. And then in this example, we're saying anything running in the billing namespace using the payment service account on any nodes in our cluster will get this billing payments SPIFFE ID. And then it's just a little diagram showing it all kind of hanging together. So your servers minting your SVIDs, your JOTs, or your X509s. The agents are attesting to the server and figuring out which workloads are calling the API. Workloads just getting their SVIDs, passing them on to the relying party there. There's an optional OIDC discovery provider which just exposes the endpoints to get the discovery document and the key set. And on Kubernetes, you can run, there's a CSI driver, which allows, so the workload API is exposed over a Unix socket, so that needs to be on a host path. You might have policies that say your workloads can't mount host path volumes, and so the CSI driver can remove that issue and make it easier. So there is an overhead to running a SPIFFE cluster, setting that up, managing all the configuration. What are some of the things that you might want to do, or that you can do to kind of get SVIDs? If you're happy with kind of Kubernetes service account tokens, you just want to add to that X509 certificates, you can use Istio or Console Service Mesh, and they hand out SPIFFE IDs in the X509 certificates that they issue. Problems with that is you've got two different identities. You've got the Kubernetes service account in your Kubernetes tokens, and then the SPIFFE ID in your kind of service mesh tokens, and also kind of the service mesh kind of running in a proxy, and so your workloads generally can't get access to the tokens, to the certificates that the service mesh is generating. Cert Manager has got a CSI SPIFFE driver, so you can generate X509 SVIDs and access those from your workloads. But again, you've still got these kind of different subjects. So if you want the same subject in your JOTs and your X509s, you probably want to be running Spire. And with Istio, you can now configure Spire as your external certificate authority. So you can kind of have the benefits of your mutual TLS between your workloads being managed by your kind of service mesh, but still accessing the same identity in your JOTs and your X509 certificates through the workload API. So where are we kind of going with identity, and what can we do using kind of hardware to get stronger guarantees? TPMs, those little cryptographic boxes of goodness, available in lots of machines these days. So it's a secure crypto processor, can separate from the host system. You can only go in through the specific channel. So you can do random number generation, key generation, hash generation, encryption, decryption, signing. There's kind of two key identities that are created in the TPM. So the endorsement key, that's burnt in at manufacturing time, and that identifies a specific TPM. And then you've got attestation keys, which you use for kind of identity, and you create those on demand, tied to a specific, using the identity that you want, but again, tied to that specific TPM. Now, one of the cool things about TPMs is those keys never leave the TPM unencrypted. So you have to do the the operations within the TPM. So now if you're doing things with these keys, you've got strong guarantees about where this is actually happening. And we've also got kind of platform configuration registers. These are special registers. You cannot write to them directly. They're using an extend operation. So it's a hash value, and to change that value, you extend it by taking the current value and adding the new value, and they're concatenated and hashed. So you've got an unmodifiable history of all of the values. So you've got kind of strong guarantees around those values there. So what can we do with that? So we can do TPM-based attestation. So you can guarantee a specific node that a workload is running on. So the first step is credential activation. So we create an attestation key in the TPM, share the public key for that, and the certificate for the endorsement key. Then we create a challenge, which can only be decrypted in the TPM itself, and then we send the value back. And now we know that that attestation key is definitely in the same TPM as the endorsement key. So we've tied this to a specific machine. Once we've done that, we can then do attestation. So we can periodically verify that we're talking to that specific machine. So we send a nonce in to prevent replay attacks. We will then sign a quote in that TPM, send it back, verify that signature with the nonce in there using the attestation public key, and we can now guarantee that we're talking to the node that owns those keys, because they're not available outside of the TPM. So there's a couple of plugins for SPI attestation that use this. There's a Boxboat one, which just uses the public key from the credential activation. The thinking there is that SPI won't be periodically verifying your node. You'll just do that when the node comes up. The official one uses the full attestation process with the addition of an external CA, so that you've got some more control about the identity that's in the certificate that you're generating there, which gives you more fine-grained selectors to use for assigning those identities. So we can take that a step further, and we can now attest not just which machine we're talking to, but also whether that machine is within a trusted state. So with the measured boot, we're basically loading every stage in the boot process, from firmware through the bootloader up to the kernel, loading that into memory, hashing it, and extending PCR values to record those. So the TPM's now got a record of all of these measurements. And with IMA, we can do a similar thing for software that's installed on the machine. So as that gets loaded, we can hash it, sign it, and measure it, and stick that into the IMA PCR. So now we can use the TPM to generate quotes that will verify the state of the machine, and we can guarantee that they're on that specific machine. And that's where something like Keylime comes in. So this allows us to do this kind of remote attestation and state verification using the TPM as the root of trust. So the agent sits on the machine and talks to the TPM. It creates the attestation key for the identity, creates quotes periodically in response to the verifier. It also collects things like the UEFI log and the IMA event log, and this kind of makes state attestation possible. The registrar, the agents register themselves with that, and that basically stores the endorsement public key and certificate, so that we know it's a specific TPM, and the attestation key that verifies that identity tied to that TPM. And then the verifier bootstraps the nodes into the system, and it's kind of basically periodically asking the TPM to generate these quotes and verifying that we're in the right state, and it deals with removing untrusted nodes or compromised nodes from the system. So now we can kind of continuously check the state of the machine. So we could use this to assert build systems in our supply chain security, so we know the state of that machine all the time. If it gets compromised, we can whip it out. It also allows you to kind of securely deliver data to these nodes. So it'll take it'll encrypt information, but it will split the decryption key, send one part to the agent and one part to the verifier, and the verifier will only release the second part of the key to the agent as long as it's in a trusted state. So now we can kind of use kind of keylime as another way of securely distributing secrets. So, JOTS and X5 and 9 certificates, best form of identity documents. Service account issuer discovery allows you to kind of do quite a lot of stuff just with Kubernetes as your identity provider. Personally, I think Spiffy and Spire, it's kind of the gold standard in identity, gives you a lot more on top of that. TPMs as hardware root of trust allow us to verify exactly where a workload is running and the state of the machine that workload is running on. So depending on our kind of requirements, we kind of go from Kubernetes as identity, Spire as identity, TPMs as kind of really, really strong guarantees. And that's it.
Yeah, so again, a couple of minutes for any questions. Just raise a hand if you have one.
Hi. How far did Spiffy go towards standardization efforts, RFC, ITF, all that fun stuff? Is that already there, getting there? Is that just initial?
So it's just recently graduated at the CNCF, so it's a fully fledged CNCF project. Yeah, I think the key thing is that it gives you a really nice way to represent identities. You can see kind of outside of Spiffy and Spire, you've kind of got Istio and kind of Controllers kind of taking that, at least the Spiffy ID part, and encoding that into the URI sounds. So it's quite a widely used sort of format for doing that.
But is the ambition to become a fully fledged standard, bring in the whole community? It's just early?
I don't know.
Okay. Thank you.
Any more questions, or we? Good?
Thanks for the talk. What's the like TPM support like in cloud providers? Do you have to use like a special instance type, or like a bare metal machine or something?
So there's quite a move towards kind of confidential computing in the kind of cloud space, not just kind of TPMs, but also trusted execution environments. So yeah, you have to have the right type of machine, but the support is becoming more kind of widespread.
Thanks.
Great. So no more questions. Next up, we have Denis. Apologies if I pronounce that wrong. With step-by-step observability with eBPF.
Oh, I have people leaving even before I start speaking. I don't think it's a good sign. I start to be worried. Hi, everyone. So happy to be there. I know that I am just before lunch. And as in any conference, we are a little bit late. But the good news is that I think I can probably make it on time, that we do it in 35 minutes instead of 45, and you can have a proper lunch break. I try, at least. OK, guys? So yeah, it's about me. So I'm working at the Director of Field Engineering in EMEA at Solo.io. If you don't know Solo, it has been founded by Edith Levin in 2017. We are based in Boston, focusing on application networking. So we define application networking by being a kind of a combination of the features you get in API gateways and service mesh all together as a platform, which means that we are expert on technologies like Envoy, Istio, eBPF, whatever open source technology that we need to achieve this capability to provide this application networking platform. You can enter for winning a drone, so if you want, you can just have a picture of the QR code. But also be aware that this talk will be about observability, eBPF, using eBPF to achieve observability in Kubernetes. And we have a workshop at 3:30 p.m., I think, where we are going to do the same thing, but with hands-on and so on, right? So if you are interested by what you will hear now, and you want to have like a hands-on experience on it after, then I invite you to join us there. I'm not going to define again what is eBPF. I think everyone was there on time this morning to hear about it, so I'm going to skip it, but I'll just explain quickly that there are many different use cases with eBPF. Everything like related to security, tracing, networking, observability, so many different use cases. You cannot do everything with eBPF, but you can do very interesting things. And when you can do something with eBPF, it's generally quite fast, so quite interesting. You can see in the high-level architecture that you have this kernel program that you load, and then you have this user space program. And I think if you go to this one, it's easier to understand. So basically, your user program contains the kernel program that you want to load, right? So you don't have two binaries, right? You have one binary, and this binary is your user program that contains inside the kernel program, right? So when you do launch your user program, basically it launches the kernel program, and then it can exchange some information with this kernel program using maps. And you can basically, if it's like observability use case, there will be kind of a one direction. So you get the data from the maps that is in the kernel. So I want to get data about what's going on, and I want the user space to display that to the end user, for example. If it's like networking security, that will be probably more a bidirectional. I want to tell the kernel, oh, there is this new rule that I want you to enforce. And then the kernel will enforce it, and perhaps will pass information back about what has been enforced and all these kind of things. So what's interesting is how do you use it, right? And you will see, I don't expect anyone in the room will write eBPF program in the future. I prefer to be honest with you, right? It's not like when you first heard about Docker, then you thought, okay, I will run containers, right? And everyone would say, yeah, I will run containers. With eBPF, it's a little bit different, right? You need to have a little bit of C++ skills, right? So a lot of you will use eBPF in the future. Very few of you will write eBPF program in the future. So I really want to highlight that, and probably you will see that better later. But if you want to write eBPF and use it, right, then you have different options, right? One option is to use what's called BCC, and with this approach, basically you provide your user program is a Python program. And you have, in this Python program, at some point you have a string that represents the C++ code you want to load in the kernel, right? And if I use BCC, it looks very nice because I can write the user program logic in Python, which is a lot better than in C++ for most of the users. But still, I need to write this C++ code. And this is really good for experiments, but it's not really good for production because the way it works is that it will be compiled when you will run it, right? And to compile it, you also need to have the Linux headers in your machine, which you never have in a production machine, right? So basically, don't expect to use BCC for running a program in production, right? It's nice to experiment, but it's definitely not something that you would use in production. In production, people would use normally more something like called libbpf tools and bpf core. And that means in that case, you will be able to compile everything in advance, and then you will be able to distribute the binary you compiled to your different machines. And these machines, you don't have to have these Linux headers and all the problems that you would have with BCC. So that's really nice because now I can create this portable binary that I can distribute in different machines. But that also means that now I need to write also the user space logic in C++, right? Which is not something that everyone is comfortable with doing, right? So that's really nice. That's working quite well. But in Solo, we found out that we really like to simplify the user experience whenever we can. And that's what we do with a lot of our products. And when we've seen this eBPF trend, we thought, OK, we are going to write, because as I said, we are not expecting all of you guys to write eBPF programs. But we expect vendors like us and other vendors to write eBPF programs and to add eBPF capabilities in their product. And we are going to need to write eBPF programs. So we will need tooling for that. And if we build the tooling for us, why not building this tooling for everyone, right? So that everyone else could use that, right? So the idea of this project that's called Bumblebee, that we have open sourced some time ago, is to simplify the experience when developing and deploying eBPF programs, especially all these programs that are focusing on observability, right? As I said, in observability, the user space program is mostly, I want to display the data I got from the kernel program, right? So I load something in the kernel, I want to get some metrics on whatever, and these metrics are then provided by this kernel program to my user space program, and the user space program needs to do what? Like display that, perhaps like providing metrics in Prometheus format, right? That's basically what I need, right? So in that case, why I would need to always rewrite user space program? So what we said in Bumblebee, or for all these use cases, we are going to build and the user space program on the fly for you, so you can only concentrate on the kernel program. So you will concentrate on what kind of data I want to get in the kernel program, and then I'm going to pass it to this user space program that I built for you, and you are going to be able to display that information and to publish metrics automatically for them, right? So it will not be solving all the problems that you can solve with eBPF, but it will be really focusing on these observability use cases, if it makes sense. And we always like to try to have a user experience that is kind of the same you have with Docker run, Docker build, Docker, It's something everyone understands and everyone likes, right? So we really try to take this approach with Bumblebee, as I will show you in a minute. So again, still you write the same eBPF program, is the same format as the libbpf tools. You will see just like we have a few tweaks here to be able to define how I want the user program to behave. But it's very, very small tweaks, as you will be seeing. And in this demo, the goal is not to give you an eBPF image that you can use to do Kubernetes observability, right? The idea here was to take like an example that people understand, right? Like, what can I really do with eBPF? What I can do with eBPF, I can launch a program in my laptop, and I can, send a, use a curl command, and I can show you there is a request coming from my IP to the IP of google.com, right? I could show you that, right? You would say, OK, that's good, but what's the meaning of that, right? I don't need to have eBPF for that, right? So what I was thinking with this talk is, what I'm going to do is, people really want to know what's going on in their Kubernetes cluster, which pod talk to which pod, and these kind of things, right? That's something that is very interesting, right? Having some insight about what's going on there, right? So what do I really need? I need to know what are the pod IPs talking to which service IP, right? That's what eBPF can give me, right? It can give me this very easily. It will not tell me what is the pod talking to the service. I will have to build this logic in my user program, right? But at least in the kernel, I can load this program and get this information and take advantage of that, right? So what we are going to do here, we are going to basically build a program using Bumblebee that is going to get this information, the source and target IP addresses, and is going to publish that in a Prometheus matrix format. As I said before, everything is just built automatically for you. And then I'm going to deploy Prometheus, scrap this matrix, and then I have a small program I've written, like the KeBPF, which is just a small UI that is going to get this data from the Prometheus matrix and interrogate the Kubernetes API server to know, okay, what is this pod IP meaning? What is this service IP meaning? These kind of things, right? And display you the result, right? That makes sense? So I don't know if, who is familiar with the book info application in Istio? Some of you? So for the one who are not, I will just explain quickly. It's a very commonly used application when people try out Istio, which is based on multiple microservices running in multiple different languages, developed in different languages. And you see you have this product page that talks to the review service, and then the review service talks to rating, and then the product page also talks to details. So why I use that is just because it's a distributed application, and you can see what we want to achieve, right? We want to achieve something like that, where we want to see the product page is talking to the reviews is talking to ratings. Basically, just showing in a UI like what we expect, right? And a little bit of other things, because obviously we have Prometheus running and these kind of things, right? And as you can see, I use a Kubernetes cluster with multiple nodes, just to make it a little bit more fun, right? Instead of having the program running only in one node, I'm going to run this Bumblebee program in each node so that I capture this data from these different nodes. Cool. So, demo time. So I like when it starts with connection closed. So we use Instruct for a lot of our workshop, and for the one who will join the workshop at 3:30, we are going to start a little bit before with having you trying BCC, having you trying libbpf on your own, and so on, right? But it will be basically the main idea and the main the same labs. So here, the first thing I do is that I just install Bumblebee, right? And I could use binit to get a skeleton of a program for me, but I'm going to skip that part. And what I'm going to do is that I'm going to take the program that I want to use. And this is like basically, you remember I told you about BCC, and I told you about libbpf. Basically, they are both in the same repo. It's a directory in the BCC repo. And here you can see many examples. And one example that is interesting for us is the one that's called like TCP Connect. And you can see I have a C program, which is my user space program. We don't care about it because it will be generated automatically. Otherwise, I would have to create this logic where I read my data coming from my kernel program and so on. And we have this kernel program, which is the one we care about, which is going to get this information from the kernel, right? So we take this file. I think it's just a little bit simplified version of it. And we do a diff between this file that is the one that we would normally use in when we use libbpf, and the one that we use here with Bumblebee. And you see the only difference is that we have kind of created a naming convention that normally you have these dot maps that tells that this is like a map, that we want to generate here. But if we do map.counter, that means that the matrix we want to generate wants to have this counter in it. We could have maps.print, then the user space program will be built with this idea of printing each entry one by one. If I do .count, then the .counter will be more like a matrix that will generate, like that will sum, you know, the different values, right? So very, very easily, you take a program that has been built for libbpf, you just have to add something like that, and you can now use it and compile it with Bumblebee. So let me get this file here. And you see here, like, you remember I told you the Docker build, right? So we do a B build, right? And what is nice is that I don't need any prerequisite in my machine. I don't need to install libbpf tools. I don't need to do anything, right? This is the beauty of it, because it's also using a Docker image behind the scene to get all these prerequisites. And the other thing that you can see here is that you are probably familiar with this, right? I don't know if it's big enough. Do you need to be bigger now? Yeah, sorry. Let me do that. So you see here, you are also familiar with this, right? Localhost 15,000, solo, TCP connect, right? It's like what we did is we create the binary that you can execute, but at the same time, we also create an OCI image that has this binary, and we can distribute it now in any OCI compliant registry, right? Like a Docker registry, right? And that means that now I can do a B push, like I would do a Docker push, right? It's a B push, so it's pushing my OCI image to a local registry, because here, if I look at my my system here, I am on the master node of my Kubernetes cluster. You see root at master. And in my master node, it's not the way you should run a registry in your cluster, but in my master node, I have like a Docker registry running there, and I just pushed to this Docker registry my OCI image, so that later on, I will be able in my Kubernetes cluster to get this image, okay? So I get it, and now if I just do like run this B run, again, like a little bit similar to Docker, right? Then you can see this, I would not say nice UI, like not so bad terminal UI, right? That display this information about the network communication that are currently happening with the source and destination address and the counter, right? And what you can see as well is that if you do a curl on this endpoint, when my program is running, I can now get the metrics. And you see these metrics in Prometheus format are telling me, you see, these events, right? So I have the counter that we discussed before, right? So now it's very easy for me. I can just have Prometheus scrapping these metrics from there, and I get all my data in Prometheus, okay? So I check. Fully, I did everything correct way. And the next step will be to just go through step by step, you know, on all these different, you know, setting up the daemon set and so on. So the first thing, I'm going to deploy the book info application, as I said before, right? I always forget that I need to add a tab here to display the product page things. I will try to do it before the workshop we do later. But basically, you can see here my pods, and I do -O wide, so that you also see that they are not running all in the same Kubernetes node, okay? So that should not take too long. This is what's nice with Instruct. It's not running in my laptop, so that will be a lot faster. Okay, it's running. So now I'm going to deploy Prometheus. Again, nothing really new here. And I'm just waiting also for it to run, which should be quite fast. It is supposed to be fast. It is. Okay, so -A. Okay, it's running already. Now I'm going to deploy Bumblebee. So what I've shown you before is that it's we created an OCI image that gets our program, right? Our eBPF program. It's not a Docker image that I run in Kubernetes, right? It's a very different thing, right? It's an image that has my program. What I'm going to do now, I'm going to run a daemon set in Kubernetes that has the B CLI. Is the Docker image of it is the one that has the B CLI, right? And I will give the option of it. I say I want to run the command B, which is the command we've seen before, right? Run with the where do I find my OCI image, right? It's on my registry, right? So I'm not running this OCI image directly, right? I'm running an image that has the B CLI, and the B CLI will start and will get its eBPF image through the OCI registry, right? So you can distribute through the OCI registry your different eBPF images, but then I just run them normally with the B CLI. And I will show you after that we are adding something quite nice in the near future here. So right now, just create this daemon set and waiting for it to run. So it is here, it's running, and I'm going to generate some traffic. That's where it's not very nice for you guys. I should have added like a product page tab and I could show you the product page, but instead it's just a for loop that goes to the product page, right? So, or in fact, I remember why I didn't do it, but that's a different story. Okay, so I generate some traffic. So what's going on now, right? So we have this B CLI running in each node because I have a daemon set. It has loaded my program, so it's now exposing my metrics, right? So this program, each of the pods is exposing these metrics. So there is one thing I think I missed here. No, I think I do it after. Yeah, it's here. I think I didn't do this one, right? So let me create that. So the only thing I missed is doing this, creating this pod monitor, so that basically it tells Prometheus that it has to scrap the metrics from this daemon set. Okay, again on the port 90 whatever, but yeah, the port name that is indicated here, which is HTTP monitoring, right? So this is now that I should generate traffic. If I go in the right order, that will be better. So I have now if everything goes well in the demo, that means that now I have my metrics in Prometheus telling me which service talk together, like product page talk to reviews, reviews talk to rating, you know, all this information should already be in Prometheus. But I need a program to take advantage of this data, right? So I'm going to run this program here, but you can see, and again, don't do that in production. I could have been very fine-grained, but here I give like full control to my Kubernetes API server to the program I'm going to load that now so that it's able to interrogate the Kubernetes API server, okay? So the program that I'm going to load now, it's going to read all the data from Prometheus, all the metrics, and for each metric, it will interrogate the Kubernetes API server to know what this IP means. What is the pod, what is the service, and also what it will find a service looking at the labels to find out what are the pods that are attached to this service, if you want, right? So it's kind of it's not a very complex program, just basic logic, but at least it shows you that in a graphical way. So I just need to wait a little bit for it to be there, and it's already there, right? So that's quite cool. You can see here, I have like my product page talking to details and to reviews, and reviews talking to ratings, right? And what's funny is that if I refresh again here, then you can even see the KeBPF program that is this UI becomes part of the picture as well, because you can see the KeBPF program is also talking to Prometheus on one side and to the Kubernetes API server on the other side to get its data, right? So again, the idea is I'm not telling you write C++ program to observe your Kubernetes cluster, right? What I'm telling you is this is the kind of thing that you can get with eBPF, and this is why it's interesting, because then you can load this program in your cluster and get all this data, but you have a lot of tooling that already provide that for you, right? Using eBPF, right? But I wanted also to show you that basically we have this Bumblebee project that allows you to play a little bit with eBPF, create your program, and so on. And because everything in the OCI format, then these programs can be created by some of you guys, some vendors or whatever, and then can be distributed and shared, right? Like a registry, like a hub we have in Docker, right? This is something I don't know if some people follow us since some time, right? But we did the same with WASM, for example. I don't know if you are familiar with WebAssembly, but if you are, I encourage you to have a look at what we did in that world as well. We created the same thing, like a WASME, it's called WASME, so WASME build, WASME run, WASME deploy, so you can build your WebAssembly program and distribute them and so on. So we kind of took the same approach with this. So as I said, we have a workshop coming this afternoon. I think it's at 3:30 p.m. And it's kind of the same thing you've seen here. We just spend more time explaining a little bit more the concept, and you have like each of you will have access to the Instruct environment, and you will be able to go through the hands-on labs. I have my colleague Christian at the end of the room that also started to build the second workshop on that. So we have another one that's going to be ready at the end of the month, where we are going to go more deeper on for the one who will be interested in developing these applications, these eBPF programs, getting some more knowledge about what are the different steps to do that. And also we have something very interesting coming with the Bumblebee project. You've seen that right now I had to create a daemon set, and then I had to tell it where is this program in my registry. That also means that if I have 12 programs, I will have 12 daemon sets, right? So what we are building like an operator for Bumblebee, so that basically you'll be able to run this operator, and you'll be able to create like a CRD like this one, like the probe one you see here, and you will say, okay, I want to run this eBPF program, and this is the image for it, and it will automatically create the daemon set for you. And we also improve the way it works so that you will be able to run multiple programs in the same daemon set. So you will not have to have multiple daemon sets. So, and if you want to get rid of one of the programs, then you just need to remove your CRD. The operator will find it and will remove it and so on. Right? So that's an interesting next steps. If you want to discuss more with us about this, or Envoy or Istio or whatever, right? We are always on Slack, right? So just please reach out to us on Slack, and we'll be happy to discuss more there. As I said, we have the workshop this afternoon. We have many other sessions. I have one of my colleagues also doing like an Envoy workshop before, if you are more interested on the Envoy side. So thanks everyone. I kept 5 minutes for the questions. So if you guys have questions, feel free to ask them. Thanks.
Yep. So again, any questions? Raise a hand.
I think everyone is so hungry that will be difficult.
Okay, the workshop it will be out here on the left in the glass room. I think that's where they all are.
I was even before time. Imagine.
5
it's
minutes
good.
Yeah, so it's lunchtime now, I think. They'll resume in an hour and a bit then. So back in this room then. Cheers.
Thank you. Thanks.
We'll take no offense if anyone wants to leave. I have got a photographic memory, so if I see you at the social, then I will remember you for life. So yeah, no pressure. Hello, and thank you everyone for joining. We're on stage today talking about a project that we've been working on to migrate from our singular Kubernetes cluster that we've been running for a really long time to managed Kubernetes. Now, we've been running Kubernetes for over 6 years now. It's been a pretty smooth journey, all in all, but we've gotten to the point where the work we do on Kubernetes is pretty vanilla. We run, basically most of the features that came out early on, and yeah, all of it is pretty vanilla. We gain a lot of benefits and time saved if we let the control plane go. So, hi, I'm Sahel, and I'm joined by the wonderful Miles today. We're both engineers at Monzo, and we spend our time working on the underlying platform powering the bank. We think about all of the complexities of scaling our infrastructure so that other engineers in other teams can focus on building and operating the bank. So we take care of our Kubernetes infrastructure. That's what we're here to talk about, as well as our monitoring stack, our logging stack, and all the other databases and queue-level technologies that engineers will need in order to build reliable and resilient applications. For those who haven't heard about Monzo, we are a fully licensed and regulated UK bank with no physical branches. You manage all of your money via the app. We also have HTTP endpoints for those who are so inclined. And at Monzo, our goal is to make money work for everyone. We deal with the complexity of making money management easy for all of our customers. As I'm sure many will attest, banking is a really, really complex industry, and we undertake the complexity in our systems to give customers a really wonderful and delightful experience. Banking shouldn't be a pain. We also have these really nice hot coral cards, which you may have seen around. They do glow under UV light. And yeah, they are very nice. We also have some really nice neon ones, but unfortunately we're not giving them out anymore, which is a bit of a shame. So we weren't kidding on our title slide when we said we have over 2,000 microservices. Running a bank is really, really complicated with a lot of integrations. That above is an illustration of different components talking to each other over the network. There are, if you speak to a lot of other banking institutions, they don't publish their headline numbers, but it's in the tens of thousands of applications. So yeah, we feel like we're lagging a little bit behind, but it makes for a nice headline number. Now, 6 years ago, we actually talked about an infrastructure migration on our blog from Mesos to Kubernetes. We had around 100 services at the time. We were still running like a pre-paid card program, and it was the wild west of the Kubernetes 1.3 days. And for those who don't remember, like me, I actually had to look it up. The Kubernetes changelog is hidden through 6 layers of Kubernetes API documentation. It's quite hard to find. But at that point, Kubernetes was still awaiting support for things like daemon sets and pod security policies, things we take for granted nowadays. Now, our philosophy is to provide a platform for all of our other engineers to be able to run and deploy their services. And this frees up our product teams to really focus on building features rather than worrying about their infrastructure. It also makes things like company-wide auditing and compliance much, much easier. We've been running the same Kubernetes cluster since 2016, naturally upgrading it over time. We've scaled it out so that we're running thousands of deployments on top of it for all of our different microservices and tens of thousands of pods encompassing those deployments and growing on a day-to-day basis. Quite literally, as we're speaking, folks are deploying onto this cluster. These services don't really rely on state that lives within the cluster, which is one of the big benefits we have. It makes our management life so much easier on that side. We do run some stateful components on the cluster, however, things like Prometheus and Kafka and Elasticsearch for our monitoring and logging and queue-based technologies. And as part of this migration, these are things that we want to seamlessly migrate over, ideally without losing any data. Now, we've been able to manage this sort of process overall because we don't need to give the vast majority of engineers access to Kubernetes. Early on, we built our own deployment and release tooling to manage the Kubernetes deployment lifecycle as part of our deployment pipeline for our microservices. one of the key steps is to generate the Kubernetes manifest for microservices. So essentially, we have a cookie cutter manifest that is embedded within the services, and the deployment pipeline handles the deployment process. And this means that engineers themselves don't need direct access to Kubernetes. It also means that we've been able to enforce a lot of control, in what engineers can actually deploy to the cluster, significantly reducing our variance at the surface level. This seamless tooling means that engineers deploy hundreds of times per day and not have to worry about what's going on at the Kubernetes layer. It is just seen as a platform level abstraction. My goal personally is to have a product engineer join Monzo and spend their entire career without ever having to look at a line of Kubernetes YAML. Now, it's sometimes really easy to forget, but we work within a highly regulated environment. And anyone who's done a PCI DSS assessment will know exactly what one of these is. It's very funny when your assessor comes down and says, please take me to your data center, and you basically circle all of Ireland, and you say, well, the data center's there, speak to AWS, and they might give you the keys if you pay enough money. But yeah, they want to go to the data center, and they want to see one of these appliances, which is an F5 firewall. Now, I was going to add a joke that you can't really kubectl apply a firewall appliance, but actually I did some Googling, and it turns out you can. You can connect your F5 firewall with Calico BGP. So yeah, it is true. You have a Kubernetes resource for everything. Now, our approach is a little bit more dynamic. We also have, we need to follow the spirit of the compliance and the regulation, right? So we also want to restrict service-to-service communication to protect our microservices and systems. A service that is serving our website, or the funny branches API that you saw on a couple of sites earlier, doesn't need to directly interact with our core banking systems like our ledger. We use features that are native to Kubernetes, things like pod security policies and Kubernetes network policies, with our own custom tooling to manage service-to-service communication and make sure only things that are allowed listed can talk to each other. Now, under the hood, each service gets its own network policy, only allowing traffic by other services which have a particular label expecting egress. Under the hood, we use Calico. So Calico enforces the network policy by generating a bunch of IP tables roles. It's pretty seamless and dynamic as workloads move in and out and engineers add new hops to their services. All of that is fully automated. The policies themselves are all auto-generated as part of one of the steps in our deployment tooling, which is really quite nice. It means that engineers you don't end up in situations where engineers forget to add an egress, and naturally their system sort of gets black-holed. Now, the Kubernetes team have done a lot of incredible work in increasing the ceiling where, lots of Kubernetes resources have a performance impact at a cluster level. However, when we were doing, for example, cluster upgrades, or we added too many watches to our cluster and things like that, a Kubernetes cluster can experience starvation or a particular bug or something that we were changing. And the impact was essentially company-wide because we have this singular cluster. Whilst running workloads wouldn't have suffered so much, we were inherently blocking engineers from deploying onto the cluster and making scaling changes and things like that, because our deployment tooling does abstract away the Kubernetes layer, but at the end of the day, it does need to talk to the Kubernetes layer, which we need to keep highly available. So whilst we're always striving for improvement in the changes that we make, our target is not to tie down our capabilities to the success and availability of this singular cluster. Now, a strong motivation for us is to be in a position where our clusters are a lot more ephemeral. Skyscanner have done a really incredible talk about this, and it's a model that we want to achieve as well. Our desire is to be in a position where we are spreading our workloads across lots of different clusters and spread those clusters across lots of different regions. We like to think of it as a little bit closer to cell-based architecture. If you follow a lot of the AWS-based guidance, a failure of one cell or one cluster in this setup shouldn't cause binary failure across the board for our engineers. If something goes bad, we can quite literally afford to throw the entire cluster away and move our workloads to other clusters. We can, for example, canary a change on a cluster that is running less important services and graduate that across clusters, across different levels of criticality. this is is not only something that we're looking at within Kubernetes. This is like a principled way of thinking for us across many of our different platform components at Monzo. Now, one of the things we considered, is that we just continue running our own clusters, just more of them, sharding our workloads across clusters. And right now, we've got a lot of benefit with tooling like COPS and, KubeADM and, there's CDK, which I'm not actually sure whether it allows you to spin up your own clusters, but yeah, there's a lot of great tooling nowadays. We didn't have that when we started, but yeah, we could take advantage of that tooling. However, the thing that we were trying to optimize for is the constant management overhead. Day one operations are relatively easy to get up and running. Day 100 operations are the things that take toll over time. And making sure that it's performant and secure and taken care of are things that we need to manage. Additionally, the process of actually managing and updating clusters is tedious. It's very well documented. I think the Kubernetes team does a fantastic job at this, but it is tedious. All of the components within Kubernetes can withstand that disruption. So rolling upgrades are really, really smooth. It's fantastic. But each release brings things that you need to tune and manage. You need to go through the deprecation list, make sure you're not using any deprecated features and things like that. And that is toil, essentially, for us. And that operational overhead really does accumulate. As with most organizations, we've got all of our infrastructure defined as code, but we've got a lot going on to manage this single cluster, this single source of success. So each change comes with a level of fragility. Now, we actually gave a talk at KubeCon Virtual in 2020 where we talked about the ups and downs of managing your own cluster and whether we would do the same again. Our conclusion, after evaluating a bunch of the managed offerings, is that we were confident that self-managed clusters, if you're running, the most, the basic stuff within Kubernetes, doesn't really add a lot in terms of value. Unless you have a really super niche setup or custom requirements, it's better to let a provider just take care of it for you. Many providers actually give you a lot in terms of customization and flexibility. At the time, our desire is to migrate our existing setup to a managed variant was aspirational. Today, that aspiration is pretty much our reality. So we've been following the evolution of EKS, which is Amazon's managed Kubernetes offering. We're a really heavy AWS shop, and some of the cool integrations you get, like Fargate and Spot instances and IAM and the VPC CNI and stuff like that, are quite nice. It's a nice layer integrating AWS services that we do use and Kubernetes. We could actually maintain or enhance some of our existing security practices by using some of the native AWS features, which is also quite nice. But ultimately, the biggest benefit is the cost of not having to manage your own control plane, both in terms of instances. You don't need to manage your own etcd and all of these control plane nodes and things like that, and also the operational overhead. A lot of the tooling is pretty well designed and easy to operate. Now, I don't know if our AWS TAMs are listening on the wide stream. Hopefully this satisfies the We Love AWS quota. Now, this isn't our first foray into the world of EKS. We've been running it for actually quite some time for JSON workloads, like our build automation environment with software like Concourse. So we've seen and experienced all of the benefits that and foibles that EKS can give you. We've had quite an easy ride because we have all of this Kubernetes experience. We've been into the code, we've fixed bugs and things like that, and we knew exactly what we wanted to achieve and set up in our target world. There's really good experiences both from us and also from many other people that we've spoken to about the maturity and consistency of the release cycle and how these providers follow that level of maturity and testing. And yeah, other people say the same. So we decided, we're going to be undertaking this work. And one of the options we seriously considered was to essentially clone our existing cluster and shift traffic over. Essentially spin up all the identical workloads. Most of them are stateless, so that would be relatively easy. And also figure out strategies for migrating our stateful data over and shift the traffic over. Now, this is a totally valid strategy and one that many folks have told us has been really, really successful for them. The big benefit benefit is that we don't need to join these two clusters together. We don't need to interoperate them. It allows us to accelerate our plans and get to that benefit of reduced management overhead and cost far, far quicker. Now, the big drawback for this is that it's essentially a big bang migration. You basically get one shot, one opportunity. And for our stateful components, that it's a migration that might be pretty hard to reverse. We would need to block deployments to get essentially a snapshot, a point in time that we could actually migrate over. So that may involve a day or multiple days of disruption, and that would be quite painful for our engineers. Now, as you can imagine, a big bang migration comes with a lot of inherent risk. TSB, which is one of the banks here in the UK, attempted to do this with one of their replatforming migrations in 2018 and suffered multiple weeks of significant issues for customers. And it took them, I think, nearly 6 months to actually get to full resolution. There's a really fantastic report, an independent report by Slaughter and May, where they go through all of the different steps and both the technological and human factors involved with migrations like these. I strongly recommend giving it a read. It's quite an eye-opening report with a lot of known and unknown edge cases, which took multiple weeks and months to tease out. Now, as a result, direct and indirect, within the financial services industry, big bang migrations are always taken with a significant amount of risk from the eyes of the regulator. They're met with a lot of scrutiny. Any time we would have saved from a technology perspective, taking the shortcut would have been paid in the risk and compliance aspects of doing big bang migrations. And also, we wouldn't really be solving for getting to multi-cluster in the future. We needed to, the biggest thing that we needed to do was to unblock this seamless communication and movement of services and workloads between clusters to de-risk this migration. And we decided to pay that investment up front, looking at our strong motivation from our platform perspective to have multiple clusters and workloads sharded across them. What we wanted is a strategy to be where we could run some of our services and systems in our existing production cluster and other services and systems within new clusters, ideally running within EKS. That would actually be much more progress towards our end goal of not having a singular cluster and not having a singular source of success.
So we told you about why we want to migrate and how we don't want to migrate, but let's talk about how we actually want to do the migration. So first of all, when you undertake something like this, really good to think about the constraints that you have and the trade-offs of your particular environment. And for us, one of the big things was that we wanted to minimize the amount of downtime. Now, this seems like a really obvious point, but in many environments, it's fine you can get away with downtime. Like, for example, if you're running a cluster with ephemeral batch workloads, the quickest way to migrate would be to just tear the cluster down, spin a new one up. And actually, a subset of our system at Monzo is kind of lower criticality services that might run some small kind of back office function. And if we take those down, that's not really going to cause any problems. But there's another subset of services at Monzo which are really, really critical that handle things like money movement and interactions of our payment schemes. And if we take those services down, people can't pay their bills. It's not just a kind of like a financial and reputational risk for Monzo. It has actual kind of real human impact as well. So that means that like unplanned downtime is kind of out of the window for us, and we also want to minimize the amount of planned downtime is out of the window, and we want to minimize the amount of unplanned downtime. The other benefit of this is we can work on the migration during working hours instead of having people stay up late on a Saturday night to look at something, which means you've got more people around if something goes wrong. Now, to make this easier, we also wanted our migration to be very easy to reverse. So if we migrate a part of the system and something goes wrong, the easier it is to roll back and get the system back into the previous state means we can minimize downtime as much as we can. And finally, as Hale's kind of explained, we wanted to really avoid doing a big bang migration and to work on this iteratively, piece by piece. This lets us kind of spot issues much earlier on by migrating kind of individual services and observing them, making sure they're working. This also lets us learn from running services on EKS much earlier because we can do that as soon as we can unblock kind of service migration. So a strategy for making changes that I imagine a lot of you have probably heard of or have used before is blue-green deployments. And the basic concept here is that if you have a version of your current version of your code running in one environment, let's say the blue environment, and you want to roll out a new version of your code, you deploy that to the green environment, and you make some load balancer or a routing change and switch all your traffic over to the other environment. And the great advantage of this is that it's very easy and quick to roll back because you can just reconfigure the load balancer back to the original environment. And this is actually something we do at Monzo for most service deployments. One of our colleagues actually did a talk recently at ArgoCon where they explain how we rolled this approach out. But we thought, why don't we use a similar kind of model for our migration as well? So how would this actually work in practice? So let's say we've got our old cluster on the left and our new cluster on the right. And I've taken kind of 3 services from our system here. We've got our internal banking ledger that stores all of our kind of entries, and a couple of services that interact with MasterCard, a card processor, and faster payments, which is UK bank transfers. So some pretty important services here. So let's say we want to migrate the ledger. What does that look like? Well, first of all, we deploy it over to the new cluster. And we let the service start up, and we can see at this point whether we're missing any kind of critical starting dependencies. Maybe there's a Kubernetes secret or config map or something that we forgot to configure. And once we're confident with that, we can start shifting across some traffic, like a small proportion of traffic to start with. We can monitor for errors, and once we're confident, we can start shifting all of the traffic across. And we can leave it running for a bit. Continue monitoring for errors. Once we're happy, we can remove the service from the old cluster. So this kind of meets our goals for migration in terms of being iterative, because we can do this a service at a time. It's also very easy to reverse, because at any point we can just go back to a previous step. And we can do this online without any downtime. So for a lot of organizations, kind of environments where you're doing these large migrations, it's pretty common to kind of get the teams that run the services to do the migrations, particularly in organizations where teams have more kind of direct access to infrastructure, or perhaps even own a bit of infrastructure themselves. We have more of a kind of platform as a service approach at Monzo, where we look after, we try and abstract away all of the kind of messy details of the underlying infrastructure. So for us, we could go out and try and convince 40+ engineering teams that doing this migration is kind of more important than their work, or like where to fit it into their roadmaps, and probably spend a few months kind of chasing people up and trying to make that happen. Or we have the option of just doing it all for them under the hood without anyone noticing or needing to be aware. And the other point to consider as well is we have so many services. These steps are going to take a fair amount of time in isolation. We're probably going to want to spend at least 5-10 minutes each stage making sure there aren't any errors. Maybe for more critical services, we want to leave them running in kind of mid-migration stage for a few hours. So it's going to take a lot of time. And if you have a human running kind of commands to do these migration steps with 2,000 or so services, you are going to make some errors. So we decided to automate the entire process, build some services which would actually just perform the migration for us, and just kind of run them in the background. So actually kind of thinking about actually thinking about how the migration works is one thing, but there was a bunch of other stuff we needed to do to actually get services running in EKS. So we needed to actually kind of spin up EKS itself, play around with it. We needed to figure out our networking layout, subnets, IP allocations. When we get into a world where we're running more than one cluster in production, these are slightly kind of easier to kind of change. But for the moment, these are like slightly harder to reverse decisions. So we wanted to try and get these right to begin with. There's also a lot of support infrastructure that you need when running services, your observability, security stuff, deployment pipeline, and of course a service mesh. And even then, services need access to external databases and meta queues, and we need to make sure that all of that would work. But there's still one piece that we realized was missing, and that is our service mesh, which previously didn't support routing requests between multiple clusters, and also shifting traffic between different endpoints. So let's talk about service mesh stuff. So you might notice this is Service Mesh 3.0. Our current Service Mesh is 2.0. I'm not going to talk about 1.0. Ask me if you're kind of interested in it, but that was a few years back. So this is a fairly standard, I'd say, custom envoy setup where we have a bunch of services. Each service has a sidecar proxy, and we have written a custom control plane which just connects to the Kubernetes API. It receives updates about pods and endpoints, and then just translates that into envoy config, which then gets pushed out to the sidecars. So a couple of the key problems we needed to solve in the service mesh to dive into a bit more detail. As Sahil mentioned earlier, we really need to control traffic between services. And we were doing this with network policies operated with Calico. And in Calico, Calico basically manages sets of IPs and firewall rules at a very low level using IP tables, and it's constantly updating those IPs as you deploy new pods and change the system. In a multi-cluster world, this doesn't work so well because either you need to have one big network which covers all of your clusters, which defeats a lot of the point of what we wanted to achieve by kind of isolating and having different clusters. You've got a very, very big blast radius. Or you have separate networks, and Calico somehow sees the entire network and has to know about IPs from different networks. And it's still a very, very big blast radius. So there are a few different ways to get away from doing kind of enforcement at the network layer. And the way we chose was to move to using mutual TLS, where you have services have their own kind of key pairs and TLS certificates, and then both ends of the service-to-service connection can kind of verify each other, and we can have quite granular authorization policies. There's a number of other benefits. We now have the capability with this to do Layer 7 enforcement, so we can block on HTTP, we can lock down by HTTP paths and methods. The other nice benefit of this is with network policies, the identity that you're essentially authorizing against is the pod IP. And in this world, we can have a much more structured and rich, secure structured identity format. We can embed things like the pod name, the region, the cluster, and much better than just having an IP. And of course, you have encryption in transit, which is a nice side benefit. We also wanted to, as I said, route requests across clusters, and we wanted to do this while keeping the networks quite isolated, which leans more towards having a sort of ingress gateway approach. So at this point, you might be wondering, we spent a lot of time talking about how operating Kubernetes ourselves is a bit of a pain, and how moving to a managed service is going to have a lot of benefit. So a very reasonable question you might ask is, why the hell are you running your own service mesh? Like, why don't you just go and use one of these nice open source projects or managed projects? And there are a lot of options out there that already provide all of the features that I just talked about: MTLS, cross-cluster routing. This is just a selection from the CNCF landscape. There are lots more than this. There are lots more managed options. So we did actually have a serious look at whether Istio would work for us, and looking at different kind of architectures and migration strategies. And we got to a proof of concept, and we think it could have worked pretty well. One of the nice things about Istio is it uses Envoy, so there's already a lot of Envoy knowledge we could transfer across. But we found there was also a lot of complexity in Istio that we would need to learn about. Istio is very, very complex for very good reason, because it has a lot of features, has a lot of flexibility. And getting a proof of concept of it running on day one is one thing, but again, getting to day 100, we'd need to have the confidence that we could operate this, we could fix any issues that come up with it quickly, we could learn about all of the kind of intricacies of Istio. And even though we're reusing some of the same elements like Envoy, we would pretty much still have to learn a completely new technology from scratch. Now, some of the benefits we'd get from that, some of the features we could use would almost definitely be worth it, but it'd be a significant investment in time, which doesn't really get us closer towards our goal of actually migrating to EKS. And we were just a bit worried it would be too much of a distraction from the migration itself. So in this case, we decided to build rather than buy, and we came up with version 3. The previous control plane that we'd written, we'd been operating for about 3 years, accrued quite a bit of technical debt. We've been adding some new features to it. And we weren't very confident we could kind of extend it without a lot of pain or issues. So we took this opportunity to rewrite it with some of the lessons we learned from the previous version, upgrading some of our versions of libraries and Envoy, moving to admission controller to inject sidecars. This took a bit of time, but it was worth it, and I'm confident it is a lot quicker than trying to learn Istio. And this gave us a really good base to build on. So the state we've got to with this is where we've been able to unblock the migration with MTLS kind of end-to-end and ingress gateways. And we're basically able to control the amount of traffic going across cluster, and we're able to start migrating services. So we've also been thinking a bit about what the post-migration world looks like, because we don't want to just do a kind of simple lift and shift and not take the opportunity to try and improve, like work on our kind of strategy and improve the kind of future state of things. So the work we've done of our service mesh has made it much easier to run multiple clusters in future with ingress gateways. So we said we'd share a few kind of lessons and learnings from this. So let's wrap up with a few of those. So we talked a bit about at the beginning of the talk about our goal to have ephemeral clusters. By kind of thinking about our constraints and our future kind of strategy and what we wanted to achieve, we can choose to prioritize and optimize for those things as part of the migration. And we can choose to, like, we identified the service mesh as being a kind of key blocker to some of the things we wanted to do. We've also discussed build or buy quite a bit as part of this, and it's not always a kind of like binary, you should build everything yourself or buy everything. You have to look at the constraints and the trade-offs of various options. And in the case of EKS, moving to a managed offering lets us achieve our strategy and reduce toil. But in the case of the service mesh, building lets us get to that state quicker. And finally, as I said, we don't want to just do a quick kind of lift and shift. We want to think about our kind of long-term state. But the interesting thing about this is if you fixate on it too much, you end up doing a really complex, massive re-platforming project, and you never kind of really get anywhere with the original goal. So you need to consider the end state, but not kind of get too fixated on it. And that's everything. Thank you so much for coming.
They've stolen our microphone, so Q&A will have to be from here. I guess I'll repeat the question, so hands up if you've got questions. Yeah, or you can try and shout. Like, feel free to shout over and we'll try and hear it.
Okay, so you say you have 1,500 microservices. Wikipedia lists you as having 1,551 employees. How are you dealing with that? And did you think about scaling down the microservices instead of complexifying your requirements?
hopefully everyone heard the question. It's more around the ratio of microservices to employees. I used to say, so we have 1,500 employees, but the vast majority of that is like in all of our other functions as well. We have about 200 plus engineers, last time I recall. And, I used to joke that, you join Monzo and, you'd get your 10 allocated microservices and it was your job to tend to them and garden them and making sure that they're all healthy and everything. But no, that is not true in reality. It's actually been something that we've been asking ourselves, and actually we see a lot of benefits in how Monzo has grown over time. So different services have been spliced and diced in lots of different organizations. It's become quite a complex mess because the organization has changed differently to how services are structured. So you end up in situations where you have some part of the system, for example, like the banking ledger, which has lots of different integrations and it's being managed by 10 different teams. To actually get something done becomes organizationally much more complex. With our microservices-based approach, we've struck quite a nice balance between having an individual unit of work and having this layer of isolation, a layer of isolation that we can independently scale and deploy and things like that. And we're able to move it between different organizational units. When a lot of these systems were built, we were like 5 or 6 teams. When I joined Monzo, I think there were like 6 or 7 teams, and now we're 40 plus teams with hundreds of engineers. And microservices have moved between engineers. We've been able to retain the context. Each microservice is context bound from a technical point of view, but we've been able to share that technical context as microservices have moved into different units and onto different individuals within the organization. So from a technical point of view, it probably would be an easier path, but there's a lot of things that we do behind the scenes to make it so that the actual management of microservices is really, really easy. Each of our microservices are all coded on the same language, follow the exact same design patterns, follow the exact same deployment philosophy. You could come in, you could learn one area of the business, and I pretty much guarantee that you'll be able to translate that to 99.9% of the rest of the organization and all the other microservices that we have. And we have folks contribute, cross-team all of the time because all of these microservices look the same. You haven't got, for example, the book application that was demonstrated earlier. We got, the reviews bit written in Python and the ratings bit written in Ruby and some other bit written in Go and some Java sprinkled in there.
Can I add something quickly? Yeah. So a really nice example I saw of this recently was that we have a small service called service.bankholiday whose sole function is to, you give it a date and it will tell you if it's a bank holiday or not. And that's very useful in lots of different areas of the business. For example, I believe we don't charge interest on bank holidays and things like that. So obviously we had a bank holiday announced fairly in September at very, very short notice. And for a lot of banks, that would be a massive operation of trying to find all of the different places where they use bank holidays. We were able to just update the service and deploy it, and that pretty much worked across our entire system.
More questions?
Hi, thanks for your talk. You stated that one of your goals was a multi-cluster strategy with perhaps ephemeral throwaway clusters. Earlier this year, we heard from Mercedes-Benz, who successfully migrated using Cluster API to thousands of clusters. But today we heard from an engineer from LastPass, and they had some frictions with trying to deploy multiple clusters using Cluster API. Was that did you look at Cluster API, and was there anything else you looked at before you decided to stick with EKS?
So I've been keeping an eye on Cluster API and various ways of making it easier to manage lots and lots of clusters. And so if I understand the question correctly, you're asking about kind of how we manage lots of different clusters. Yeah. I think with 2, maybe 3, 4 clusters, what we're doing at the moment, we're managing it through Terraform, is okay. It's probably fine. I think once we get past that level, we want to start looking at automating that more, whether that's through Cluster API or other things.
Any more questions?
Hi.
How did you structure the team for the migration? Did you create a separate team to plan the migration, or is the same platform team? And what's the number of people? How big it is? Thanks.
Yeah, good question. It's all the same team kind of planning and doing the migration. Currently with 7 people responsible for the Kubernetes and service mesh side of things. We're not the only team that will have to do kind of work as part of this. There are other teams that manage our kind of database and message queues and our deployment tooling, and we need to work with them to kind of work on those bits. But the vast majority of the work is 7 people.
One more question at the end there.
Hi. You'd said you'd kind of centralize on like a single language for all of your services. In terms of sort of exposing sort of access to common features and so on, do you provide like a standard sort of process for bootstrapping new services, like a library, images, etc.?
Yeah. So the question was more around cookie cutter templates for service generation and things like that. Yeah, I mean that's one of the benefits that we have with standardizing on a singular language. We've spent a lot of time having a set of really well-defined libraries and strong API contracts that are highly resilient and reliable that we expect engineers to use. And we've got a lot of service generation tooling. We've got a lot of tooling for code that writes code. So when you get started, you don't face that sort of like blank cursor problem, which is like, where do I get started with this particular thing? We haven't got a lot of different integrations with like 10 different Go web servers and things like that. Everything looks the same, which also makes things like, patching security issues and vulnerabilities really, really easy because we could say, okay, right, we've tested it with this massive test suite that we've invested heavily on, and we know that every service will comply because this is part of the API contract and spec. One of the other big benefits is, especially during like CI and CD to a large amount of extent, when I showed our deployment tooling, part of it was to do authorization, authentication checks, and running a bunch of static analysis tooling to make sure that the code that engineers have written, even though it is being peer reviewed for like the business level logic, still follows like our security best practices. If you're exposing something, there's going to be public facing. Make sure that you've got even simple things like proper authorization and authentication scopes and things like that. These are things that we need to enforce at a very high level to make sure that bugs, simple things like having too broad access, don't make their way to production. And by standardizing on a common set of tooling and service structure for all of our components, getting that wrong for engineers is pretty much a non-issue. We like to call it the paved road strategy. And if you want to stray away from the paved road, we make it intentionally difficult. But we've made the paved road flexible enough to encompass pretty much the entire function of the bank. It is extremely rare that we see situations where folks want to deviate from the paved road intentionally.
Great. Any more questions? Nope. Cheers.
The one at the front.
You mentioned about a tool that abstracts application devs from Kubernetes. Do you have any thoughts around making it open source? It seems interesting. If no, why not?
It's a great question. So the question was whether we'd be open sourcing our deployment tooling. We've talked significantly about it. If you go to monzo.com/blog, small plug, you'll be able to see like with plenty of screenshots and things like that with how it works. And I've given plenty of talks about it in the past if you want to go look those up. The only barrier to open sourcing is that it calls within a lot of our own internal logic, so our own authentication systems and authorization systems and things like that, which is really the only big barrier to entry, because a lot of that is sort of centrally defined within our organization. A lot of it is sort of tightly coupled in its implementation with a lot of the stuff that we do at Monzo, because it's not just the Kubernetes aspect. We could open source that, but a lot of that would be pretty simple, manipulate Kubernetes manifest using Go stuff, stuff that there's plenty of examples about. But if there's a particular area you want to see, I'd love to have a chat afterwards. And yeah, there might be something that we could do or we could publicize.
So last call for questions. No? Okay, great. So the next talk is in 3 minutes. How to protect your Kubernetes cluster using CrowdSec by Hamza and Sebastian.
Thank you.
Perfect, you get those questions. Yeah, no, it's good. That means people are listening. Yeah.
Okay, hello everyone. My name is Hamza, and this is my colleague Sebastian. And today we're going to introduce you CrowdSec, explain how it works, and show you how you can protect our Kubernetes cluster using it. So, why CrowdSec was created? Basically, we made a simple observation that cybersecurity is not a problem of means. As you can see in all those big companies, the logos that are here have dedicated amount in the for the cybersecurity budget. Sorry, they have security teams, but they get still hacked. And we think that because of the approach of they want to protect alone against all the attackers, and our approach is to say why we cannot collaborate all together to protect ourselves against those attackers. So, how CrowdSec works? Basically, it has multiple components. The first one is what we call the agent. It can collect your logs. So basically, it can read flat file. It can act as a syslog, so receive syslog input. On the cloud side, it can also read from Kinesis or CloudTrail. It's also able to read Docker logs. Also, you can plug it into your Kafka. And of course, we have another available data sources. Once those logs are collected, they are parsed. And then here where the community part takes place, we have a hub, like Docker Hub or Ansible Galaxy, where we share the scenarios. So those are rules to detect bad behaviors from your logs. So you can write your own scenarios, share them with the community, and it's already the case. We have a lot of users that are participating in this community. You can also write your own parser and keep it from you, only for you, sorry, because it will sometimes respond to a specific use case on your business side. Once this behavior is detected, we have the other component, which is the IPS, what we call the bouncers. So the bouncer is here to take the decision automatically. So if you have, for example, a simple VPS, you will install the firewall bouncer if you want to remedy at the network level, so ban the IP basically. We can also have the, for example, the Nginx bouncer, where you will remedy at the application level with, for example, return a 403 response, or more smart way to remedy is to present a CAPTCHA, for example. And also we have other bouncers that also are available in the hub. So for example, we have a bouncer that is able to push the IPs that are detected with CrowdSec to your firewall appliances automatically. And of course, we have a custom bouncer that will be able to run your own scripts. So if you have a specific way to remedy, you will be able to do it. And once those remediation is done, you will share your sightings with the community. So we collect all the signals, we create them, and we share them with the community. So you are protecting yourself and protecting the community, and in return, you benefit from the community sightings. So CrowdSec already deal with most common attacks, like web scans, port scans, SQLi, and more complicated attacks like L7 DDoS, for example, which are distributed attacks. And more business-specific attacks like credit card stuffing. So for example, credit card stuffing is when an attacker buys some credit cards in a shady website and wants to validate those credit cards in your e-commerce, for example. You will be able to detect this. And of course, if there is a behavior that is present in your application logs or your on your logs, too simply, you will be able to detect it. So with those behaviors, we are building our real-time map and kinda trying to be like the ways of the cybersecurity. So so what is the advantage of using our advantage, sorry, which is the number? So basically, we are just killing all the attackers' IP addresses pools, because we already know that it's the only limited resource that attackers use to attack us.
Okay, now we will dig a bit deeper into CrowdSec itself. So first of all, CrowdSec is free and open source. It will be forever. It's MIT license, so you can take the code, do whatever you want with it. So you can audit the code. In the company, pretty much everyone has a security background, so we take security very seriously. We do third-party audits on both CrowdSec and our server-side component quite regularly. So it's free. We do not plan to, and we don't want to monetize anything that is in the open source part. The only thing we monetize is the access to the data if you don't want to share your information with us. And of course, being open source, you can contribute to it, so whether it be code or scenarios or parsers for new applications. So we do, because you are sending us signals about the IP that you see attacking you, we collect the absolute strict minimum of data. So what does it mean? This means that when you detect an attack, you will only send us the offending IP, the type of attacks that was detected, so for example, SSH brute force or port scan, and the time at which the attack happened. And that's it. All your logs are processed locally. They will never leave the CodeSec agent that is running on your server. You only send us metadata about the attack. And for the data you send to us, we keep it for the least amount of time possible. So, for example, we keep the raw data for 3 months. After 3 months. After those 3 months, we will reduce the precision of the IP that was reported and the timestamp. So basically, we would remove the last byte of the IP and reduce the timestamp to something like 1 hour precision. And after 6 months, we will reduce even further the timestamp so that we only have the day of the attack. And afterwards, after 9 months, we completely delete the data. Because an attack that was made by an IP 9 months ago is probably meaningless by now, because the IP is most certainly clean now. So, because we get signals from the committee, we need to have a way to validate those signals. Because if we trusted the data that is sent to us by anyone, this could mean that someone could send us a message telling us, okay, so I saw 1.1.1.1 doing a SSH brute force on my server. Well, this is obviously not going to happen. So what we have a system that we call a consensus. So basically, every report that is made by the committee is going into a database that we call smoke. Then each member of the CodeSec committee has a score. The score represents how much we trust this particular user. So if you are starting, if you just install CodeSec, basically your score will be 0 because you never reported anything to us. You are new in the network, so we don't know you. We don't know how much we can trust you. But the more and more report you send us, and the more we are able to validate those reports with other reports made by other committee members, your score will slowly increase over time, as long as you keep reporting trustful report. So, for example, if someone that is very new to the network sends us an information, we will basically pretty much discard it in our decision pipeline, because we don't know if we can trust you. But if enough users in the committee report us the same IP and those users are trusted enough, well, the IP could be redistributed to the committee. We also run some honeypots. Originally, it was used to bootstrap the consensus system, because when we had no user at the beginning, we needed a way to be able to validate what was sent to us by the first users. So we use this honeypot network, and nowadays they are still used to create a report from other users, and also those are the only machines where we have access to the attack logs, because we control those machines. Because when you use CodeSec, you do not send us any log, so we only have the metadata, and the honeypot allows us to gain some more insight into some attacks. We also have a canary system, so this means that if you report an IP that is belonging to a known good range, so for example, CDN provider, Googlebot, or anything like this, your report will be automatically discarded, because it's pretty obvious that Cloudflare is not going to try to brute force SSH on your server. And we also have some smarter algorithms that take a look at the bigger picture to avoid any issue. For example, if IPs belonging in the same ranges are reported massively by a few users, this is probably something we want to have a look, because it could be just a new ranges that was just compromised, or maybe someone is trying to poison our database. And in addition to that, we also have some more thresholds. So this means that we need enough users with enough trust to report an IP, but those users also need to be distributed in various hosting provider or organization. So if you spawn, I don't know, 1,000 CrowdSec running in AWS, well, it won't be enough to try to poison the database, because it's only one provider. And so we don't have any diversity at this level. And when in the end we do validate an IP, it goes into what we call the Fire database. This database is automatically consumed by CrowdSec that is running on your server, so it will get the new IPs that should be bind because they attacked enough members in the community, and you will automatically apply those decisions that you receive based on which bouncers you are currently running. So we are pretty strict on what we redistribute to the community. So currently in our database, we have something like 7 million IPs that were reported by the community. So those reports could be just one report because of a misconfiguration from the sysadmin, because someone tested CrowdSec, or could be legitimate reports. And out of those 7 million IPs, we currently redistribute only around 21,000 IP. So it's not much, but a few months back, we did a small experiment where we spawned 2 identical VPS in the same hosting provider, exposing the exact same set of services. So basically, it was just an Nginx web server and SSH server. And the only difference between those 2 servers were how CrowdSec was configured on them. On one side, CrowdSec was using the community block list. On the other one, it was not. And what we saw, and we were quite surprised by the result, because we expected to see some difference, but not by that much. On the servers that was using the community block list, we saw 92% less alerts on this one, because the malicious IP were blocked even before they were able to attack the server. So obviously, this number will change depending on where you are hosted, what kind of services you expose, but this is what we saw. And also something important to note is that we are not a firewall replacement. We are not a SOAR, EDR, CM, whatever fancy word you want to use, but we can complete them, we can reinforce them. For example, let's assume that you have a firewall that is emitting log when when it is dropping packets. Well, you can configure CrowdSec to read those logs and automatically ban IPs that try to access too many close ports. Let's assume that your security team is subscribing to a cyber threat intelligence feed. So they get the IP, they can use it for their analysis, but it's not really actionable. And so you can use CrowdSec, you can just import this list of IP into CrowdSec, and CrowdSec will take care of redistributing this to your bouncers, and you will be able to use the data from your thread feed. Okay, now before we show you a demo of CrowdSec in Kubernetes, we just wanted to have a deeper dive into the CrowdSec architecture. So basically, on the client side, you have 3 components. The first one is the agent. So this is the one that is responsible for reading your logs and parsing them and matching them against your scenarios. When the agent detects a malicious behavior, it will generate what we call an alert and will send it to another component of CrowdSec locally that we call the local API. This API will get the alert and then we'll transform it into what we call a decision. So a decision, for example, will be, I want to ban this IP for 2 hours. In turn, when the decision has been generated, the local API can send a notification to, for example, Slack, your CM, Elasticsearch, or any HTTP webhook that you want. And if it is not supported, it's quite easy to add support for a new notification provider. The local API will also send us the information about the attack so that we can analyze it and potentially redistribute this to the community. And lastly, your bouncers will also query the local API to get the list of IP that they need to block. And so with this architecture, this means that you can have your agent running basically anywhere, your local API running somewhere else, and you can have your bouncer running anywhere else you want. Now, so what we want to show you for the demo. So we will be running a very simple Kubernetes cluster. It will only have one node because we are running locally on the laptop. But basically, we will have one agent that is reading the logs from the Nginx ingress controller, a local API that will be used by the agent to send the alert. And on the Nginx ingress, we will have our Nginx bouncer. So this means that the ingress will periodically pull the list of IPs that are banned from the local API. And now Hamza will show you.
Yes, thank you. So let's get to our cluster. So as he said, as Sebastian said, we have only a simple cluster deployed in kind. So it's a very simple cluster locally with one node. So here you can see our control plane. And so we already have the cluster running. We have the ingress controller and also a small app which is a web server that's returning a 200 HTTP response with the hello world. So if and of course I modified my etc host to point directly with this domain name to my local cluster. So here we can see that we have our hello world. What we will do now is to install CrowdSec. So it will basically install an agent as a daemon set in the node, and also in the namespace the CrowdSec local API. And the agent will start to read the ingress Nginx logs to detect some behaviors. So here we have our, let me find them, our values here. So it's we released a Helm chart that will allow you to install CrowdSec in a Kubernetes. So basically, those are the parameters for the agent on this small example, where we will, because we are dealing with private IPs, we are disabling this parser. It's kind of whitelists. And also, we are installing this collection. So a collection in CrowdSec means a bundle of parsers and scenarios. So here we have the parser that parse the ingress Nginx logs, and also all the common web attacks in the scenarios. And here in the local API, we have what we call the enrollment key. So yeah, what I will do is to show you that we have a fancy console here where you can manage your instances, see all your alerts, etc. So here, you just need, this is for an example, you don't have to show this private key, but me, it's just an example, it will be deleted after. So here is my key. I just need to put it here. So when I will install my Helm chart, I will have this instance that will pop in my console account. So I will validate it, and we will see later what's going on. And also this bouncer key. So the bouncer key here is just, we basically tell to the Helm chart to add automatically a bouncer in the local API. So we will use this key after when we will patch our ingress controller. So let's install our CrowdSec. So here I just say to Helm to install the CrowdSec Helm chart, and the name of the deployment is CrowdSec. I use my values in the namespace of CrowdSec, and of course, if the namespace doesn't exist, create it. Okay, so then I just need to watch. Here we can see that the LAPIs start creating, and then when the local API will be available, the agent will run as a daemon set. So we can already go to the console, and we will see that we have our new instance that popped here. So I have to accept it, the enrollment. So it will be available here, and I will be able to see all my alerts later. Okay, the agent take a little bit time to up. Let's go, buddy. Demo effect. Okay. I don't know what's going on. I don't want to trouble this. Okay. Let's. I'm sorry. I don't know why. Wait, what I will do is we'll try something else. Up. Simply uninstall it and install it again because, yeah, I don't want to spend time troubleshooting this. So let's remove this and go again. So let's hope that this time will work. Okay. Okay, let's accept our instance. And yeah. Okay. It's still not working. Okay, wait. Hmm? Hmm? Yeah, sorry for that. We did the demo for like many times and always worked, but now, yeah, we are not lucky today. So, okay. Shall I retry now? Pray with me, please. Okay, let's go. Told you. Thank you, guys. Okay, so now we have our agent and local API running. We will just, maybe first here, need to accept my instance. Do it many times. Okay, so now what we'll do is to monitor the agent logs. And here, what we'll do is to launch Nikto, which is a common and known web scanner tool. So let's just launch our attack. And here we can see that it immediately detects some behaviors. So for example, here we can see that it detects the scenario HTTP bad user agent. So basically when, for example, Nikto has used a known user agent. So we have this scenario that detects a lot of bad user agent. Sorry, here also we have the crawl non-static. So basically when you are trying very fastly to access multiple resources that are not allowed or not existing. Also sensitive files, path traversal, and another behaviors. So now we are detecting, but if we go and try to access again to our website, we are still available. It's still available, and we are not blocked. So what we'll do now is to patch our ingress controller. So it will install the CrowdSec bouncer, which is a Lua plugin that will pull the IPs from the local API and block them. So we are doing some remediation at the application level. So here, what we'll do is I will show you the bouncer values. So here, basically, we are upgrading the Helm deployment of the ingress Nginx. Sorry. Here you can see the parameters, which are the URL of the CrowdSec local API, the API key, the one we asked in the CrowdSec values to create, and also those environment variables that are the one that will be allow us, to apply another type of remediation than simply banning. So let's upgrade our deployment. So here we are just saying to Helm to upgrade the ingress Nginx with the first values and then the new values, and using this Helm chart. And of course, because it's a simple cluster with a simple node, the application will not be available. So of course, you don't have to do that in a real production environment. So here we can see that it's there is a pod initialization. Sorry. We're waiting for. Okay. So now we have our ingress that is ready, almost. Okay. Now, if we are trying to access to our web app, we can see that I will not do more like that. We can see that we have 403 and no anymore 200. So if we go to our browser and try this, we can see that we are blocked by the CrowdSec bouncer. So now what I will do is to go to CrowdSec and pop a shell. Not in the agent, sorry. It's in the local API. So And with the CLI, I will list my decisions. And we can see that we have this IP, which is my local IP, this is the last behavior that detected, but we have already 6 events on it. So now what I will do is to delete the decision, this decision. Okay. And now we can see that we are able again to access to our web application. Another thing that I want to show you is we can modify the CrowdSec configuration to say when there is this behavior and this behavior that are detected, please don't ban the IP, but apply a captcha. I will not do it here, but I will just manually add a decision. Here, and I will add the type of the action, which is captcha. And when I go here and try to access again to my website, we can see that we have a captcha. So in this example, in this use case, we can, for example, talk about the e-commerce stuff where you don't want to block IPs because you have a critical business behind your website. So you will just apply a captcha to block all the bots and let humans access to your website. So now we are done with this, and we can go back to our console where we can show you some fancy stuff. So here we have our instances. We can go to the alerts, and we will see, so it's my IP with all the stuff that detected. You can see your alerts here, do some reports. We also have other premium stuffs, which are the CTI. So for example, if you are not using the software, but you are more a security team and you are like you have your own CM or etc., you want to enrich the IPs to have some context on them, you can use the CTI. And of course, other premium stuff that are available and that are coming soon also. So now I will let my colleague show you another cool stuff that we did with CrowdSec just before coming in this conference. So let's go. And you can
Okay, so for the last part of the demo, so we saw how we could use CrowdSec to protect an application that was running in your Kubernetes cluster. But something that would be good would be to also be able to protect the cluster itself. Because as we saw in some talks this morning, so it's if you allow some misconfiguration in your cluster, for example, you allow people to create pod running in privilege mode, or to mount pass sensitive folder from the node itself, this can lead to a complete cluster compromise. So very recently, I think it was last week, so we added support for Kubernetes audit log, because Kubernetes, you can configure it to basically log anything that is happening in your cluster. So those logs are JSON, and CrowdSec knows how to pass JSON. So what we did, we just created a new data source to make things a bit easier, and then just some very simple scenarios to match content in those JSON logs to be able, for example, to detect if a privileged pod is running on your cluster, if someone has just tried to or has just exec into a container, and so on. So here, I'm not running CrowdSec. I won't be running CrowdSec in the Kubernetes cluster because this is still in a development branch. We don't publish development containers, so it will be a bit harder to run CrowdSec in the cluster, but it's basically the same thing. So here, I already have, sorry. I already have CrowdSec configured with Kubernetes audit collections. So this means that we have the parser and the various scenarios. In the CrowdSec acquisition configuration, so we can see that we expose HTTP server for Kubernetes to push the webhook, the events directly to CrowdSec. Obviously, Kubernetes can also log those events to a file. So if you run CrowdSec, for example, in your control plane, you could just as easily just point CrowdSec to those log files and parse this instead of using the webhook. Oh, and before, I'm just going to update CrowdSec configuration because we do want some notification. Because those scenarios are not designed to ban the IPs. It would be maybe a bit overkill to ban an IP just because a developer has, by mistake, created a privileged pod or something like this. So here we just want to have some notification. So. First of all, I'm just going to update quickly the CrowdSec configuration to tell it that for the Kubernetes audit scenarios, we only want to have notification. We don't want to take a decision. So I'm just going to copy this. So here, what we tell CrowdSec is, if you see an alert without a remediation and that the scenario that triggered the alert begins with CrowdSecurity/Kubernetes audit, then you will send a notification, but you will not take a decision. Because if you compare with the default configuration, here we have a decision, and here we don't. So CrowdSec will just leave the alert as is. And next, I'm just going to configure our Slack plugin. So notification configuration is quite easy. Basically, CrowdSec will send to the notification plugin an object which contains the alert that was triggered, and then you can format the message however you want with some Go templating. So here we have a small template that will show you the scenario, the source IP, the username, the namespace, and so on. Basically anything that is present in the Kubernetes audit event. And I'm just going to need my webhook. No, we're just going to start CrowdSec. Okay. Okay. We don't care about this. Because plugins in CrowdSec are binaries that are started by CrowdSec. We try to restrict them as much as possible to avoid just something dropping a binary in your configuration directory, and then this binary is getting exec by CrowdSec. Okay, perfect. So now CrowdSec is running. It's listening for Kubernetes audit event logs. And so I'm just going to deploy a privileged container in the cluster, and we'll see that CrowdSec will generate an alert. Okay, so here this file is just a very simple file that will create a new pod that is sleeping forever. And here, if we... Okay, so this is in development, so there's still a bit of debug going on. But let's just show you... Okay, so this is a previous alert. By default, Kubernetes will buffer the audit logs for up to 30 seconds. So we may need to wait a bit. But if you want to see, in any case, so CrowdStrike saw that before, during the demo, we exec into a pod, so it generated an alert for that. Oh, I think I know why. Let's try it like this. Really not a good day for the demo. Yeah, or we're just going to exec again in the shell. This is still work in progress. Obviously, this is something we just added last week, so it mostly works. But as you can see, sometimes it can be a bit finicky. But yeah, okay. So I've again exec into a pod, and here, okay. So we can see that yeah, CrowdStrike saw the exec, and in theory we should have received a Slack notification, but I don't think Slack is running. Okay. Oops. Sorry. And here you can see that CrowdStrike sends a notification to Slack with all the information that we wanted in the event. In the notification, sorry. And that's it for us.
Great. Just 4 questions. There is a workshop, eBPF, with Denis. We saw that earlier. They're doing it in the classroom just there. That's starting now. But for now, any questions?
Hi, thanks for the chat. The local API, is that all egress out to your web endpoint, or is there any ingress that would need to be handled from public into private network?
No, so the local API, so yes, it's the agent will push data to the local API. So if you want to expose it outside your cluster, yes, you will need to have an ingress. But if it's only inside your cluster, just a service will do the trick.
But all the network traffic to your web console is all egress?
Yeah,
okay.
It's egress, yeah.
Great. Any more questions? 1, 2, right.
Hi. What ingress controllers do you support? You've seen Ingress Nginx there, but are there any other ones that work within cluster or all of them?
Yeah, so currently we only support Ingress Nginx because this is what our users have been asking for. I think, for example, that and also, yeah, we also have traffic. But adding support for more ingress controller, I don't think it will be that hard. For example, if you take something like Kong, that is also based on OpenResty, it also had Lua support, so we could, with a bit of luck, using the exact same code. And then for the other ingress controller, well, we'll need to see if they do support plugins or not.
Great. I know we had one more question, but we're starting to run behind a bit. So if you wouldn't mind just asking them directly.
Yeah.
I can remember. Brilliant. But thank you very much for the talk.
Don't hesitate to ask us if you have more questions. And we also have some stickers, so don't hesitate. See ya. Thank you.
Hello everyone, my name is Henry. I'm a cloud native security engineer at ControlPlane. I'm sure you've heard a lot about us already. I was meant to be doing this today with Rowan as well, who's our head of security, but unfortunately he got COVID about a week ago, so he's had to stay home. But anyway, we'll press on without him. So yeah, anyway, today I'm going to be sort of discussing some pain points we've seen around configuring infrastructure securely across a large organization, and how we think using cloud controllers and policy controllers in conjunction could attempt to address some of these issues. So I think the question we'll hear a lot is, I'm a developer and I want to know how to sort of, securely deploy my application, and that's quickly becoming a more and more complex question to answer. But how do we get here? Well, over the last sort of decade or so, maybe even longer, teams have gone from having monolithic apps running as VMs and having their database and everything else bundled all together in that VM, and now we have fleets of microservices deployed as containers across.
Could you full screen your slides?
Yep. So.
Just the 3 lines on the right-hand side.
No problem. Cool. Yeah, and so as the number of microservices and other infrastructure you have increases, you've got this sort of exponential number of connections that you're trying to manage. And then at the same time, we've also started to move from having teams where you have segregated development and operations teams, and now you're probably in some sort of DevOps type team where it's a flavor of you build it and you run it. So devs are now not only expected to know how to code their app, but they've also got to be aware of, how to make a container, how to triage security tools, Kubernetes config, infrastructure, whatever. This was obviously come along for good reasons, like it makes things easier to operate because the devs are now closer to operations, so they wrote the app, they're probably in the best place to know how to fix it when things go wrong. So, services are more resilient to failures, you can scale more easily to meet load, and you can deploy changes more quickly and frequently. But obviously this has increased the complexity and breadth of knowledge that developers are required to have, and this is before you've even started to figure out how to do all this with security in mind. And so, it depends on how your team is organized, and it's largely between one of two extremes. So on one hand, you could just have full self-service where development teams have just direct access to cloud APIs and they're responsible for everything. They just spin up whatever they want on whatever they need, and so you've got no reuse across your organization. You've got lots of duplication of effort across dev teams, and lots of unique infrastructure and stuff for developers to maintain, and this is adding risk and operational complexity. And this can probably work for really small teams and with only a few products where if you've got 10 people in a team and you've got one or two platform people, it's probably a pretty manageable situation. But obviously in larger organizations this really doesn't scale, and security controls only generally come in via centralized alerting from your cloud platform. And so you'll have the operations team trying to find out what's caused this alert, trying to get the team that developed it to actually fix it, and it really becomes quite complex. So on the other end of the spectrum, you'll just have everything done by a centralized platform team, and you get no autonomy or flexibility for the development teams, but you get really consistent application and best practices, really consistent application of best practices and security controls across your infrastructure. But this will obviously frustrate dev teams and really slow down iteration time and that sort of thing. So, likely you're not at one end of these spectrums. You're sort of probably somewhere in between. And how you're organized will depend on the size and distribution of your organization, and also you need to think about what your risk appetite is versus getting features out quickly. And we've seen a few principles that start to emerge regardless of how you're organized, and we think that we're going to show how cloud controllers and policy can kind of fit in and give you a bit of the best of both worlds. So, you're still going to have a platform team, unless you're a really small organization. I don't think you can go away from it. And so they're the ones that will largely be sort of using and implementing what we're showing today. So they'll have the right idea about what abstractions are right for your organization, and they'll help reduce repeated effort and act as a force multiplier for your application teams. But you also need to provide self-service for your application teams. So without it, platform teams just won't be able to scale to meet the demands of an increasing number of developers and different unique use cases. And then also you kind of start maybe getting across time zones and that sort of thing, and it just really becomes quite unmanageable quite quickly. Obviously this requires more upfront effort to provide a sort of a good abstraction that's flexible enough to be customized by developers versus, say, a standardized solution. As you have to make sure it's well documented and is also hardened against misuse. And there's not really an easy way to define what's the right amount of self-service versus sort of standardized processes. Once again, depending on the structure of your organization and your cloud maturity. So, how do you actually provide these abstractions? And it will probably be through one of two methods, which is, there's one of two ways for platform teams to let developers consume infrastructure. One is through abstractions, which will follow a sort of allow list type approach, where they'll only expose a specific subset of the cloud APIs. And so this makes it really easy for developers to get started, because they'll have, probably some very minimal resource that they can create. Like there'll be a standard S3 module that they can consume, and they don't really need to put any configuration in it at all. But then obviously, depending on how much of the underlying API you've abstracted away, if you've got anything that goes beyond the very basic use case, you'll often, the application teams will not feel catered to, and will then have to go back to the platform team and say, we've got this use case, we need you to add in this option for us. And so then you're back in this sort of slow iteration cycle. So the other end of the spectrum is to use policy, where you're going through a sort of block list type approach, where you're just explicitly saying, you cannot do this with this bit of infrastructure, which gives teams a lot more flexibility in what they can deploy. But obviously now development teams need to know a lot more what they're doing, because otherwise, they're going to try and create this S3 bucket and immediately get blocked on the policy stuff saying, no, you can't do that because of this, this, and this rule. So you're trying to get somewhere where we have both of these aspects is what we're trying to get to. So this is where cloud controllers come in. They basically provide a new way for you to declaratively define your infrastructure. So it runs as an operator within a Kubernetes cluster. We'll create a bunch of custom resource definitions, and then developers just fill in the custom resource, and the operator will go back to the cloud provider and create your infrastructure for you. And so CRDs then give developers who are already deploying to Kubernetes a familiar interface, which is obviously YAML, instead of having to learn something new like Terraform. And then you also are now able to take advantage of any existing infrastructure you have for deployment. So that could be some GitOps, it could be some scanning stuff you have in your pipeline, whatever. You're kind of getting able to reuse all of that stuff you already have. And cloud controllers are not really a new concept, because we've had services of type load balancer in standard Kubernetes for a long time, and people use these to go and provision load balancers from their cloud provider. And really, cloud controllers are just extending this concept to the rest of your cloud provider's API. And so, what's out there? We've got ACK, which is Amazon controllers for Kubernetes, and they're planning to eventually release 40 controllers. At the moment, they have 16, of which 12 are considered GA. These must be manually installed. They're not part of EKS or any other offering. And you get one controller per service, which is good for restricting the permissions you're giving out to these controllers. And you can also combine them with Ursa, so you can quite easily map AWS permissions to the service account that the controller is running as. And you can also now deploy these either cluster-wide or per namespace for a further level of granularity on the permissions front. So similarly, Google has Google Config Connector, and they support 49 of their services. So as opposed to the Amazon ones, these can also be installed as a GKE cluster add-on, so you don't even have to think about managing Helm charts and stuff to get the controllers installed in your cluster. And then, again, these integrate with workload identity and can also be split as either a cluster level resource or across namespaces. And then the other big one is CrossPlane, which provides which has providers for multiple cloud platforms. This one does, you have one controller per cloud platform, so you've got a little bit more risk in terms of the amount of permissions you'd have to give to this to the controller. But it also has some nice features like composite resources that allow platform teams to group multiple resources together to provide another layer of abstraction that platform teams can or cannot use. And there are some other nice features in CrossPlane that I'll show later in the demos. But yeah, so why are these things not more adopted at the moment? I think it's largely a timing thing. So the prerequisites for these controllers only became GA in the last few years. So like CRDs only came GA at the sort of the end of 2019, and then workload identity was sort of a similar sort of time, maybe a little bit after that, and then obviously then these cloud controllers came out into GA. So they're relatively new, and other infrastructure as code solutions have been around for quite a bit longer. So organizations probably already have quite a bit of infrastructure as code pipelines, and maybe, probably quite reluctant to just throw all that away straight away, so. And then also this will, for quite a lot of large regulated organizations, the platform, having this sort of Sentinel style, Terraform Sentinel style model where all infrastructure must be defined as Terraform and then has to go through Sentinel policies before being applied, really kind of satisfies the sort of C-suite and auditors, and so you kind of don't want to have then this second way of defining infrastructure. But then this kind of brings in complexities where, we already have the controller that can provision load balancers in Kubernetes, and so this kind of thing is normally not permitted, and it kind of frustrates dev teams where they can't use standard Kubernetes features. You also have the cluster zero problem, where obviously you already need the cluster running before you can use it to provision further resources. So how are you getting that first cluster? That's something you still need to figure out. And then also they're still quite immature, where not all of the cloud services are provided. So even if you were motivated to migrate your infrastructure over to this, you might not necessarily be able to move everything over yet. So they're in a bit of a chicken and the egg situation where, the effort required to adopt them is quite high, and you'll be replacing a lot of existing work, and you might not even be able to move everything over. And on their own, they don't necessarily reduce developer complexity much either. And so few people are using them, which means that there's also not a lot of effort being put into making them support more services, making them more stable. And so we were kind of thinking, like, what would we need to put in place to make them more viable and make it easier for teams to adopt, and then how can we make them even better than existing infrastructure as code tools? And so we're going to combine them with other features and patterns in Kubernetes that give us reusable patterns and controls for provisioning infrastructure, to make it easy for developers to use without sacrificing security or obfuscating lots of the underlying API. And so this will reduce the barrier for adoption and sort of encourage more people to use them and speed up their maturity. And so, yeah, as I've been kind of hinting at quite a lot, it's interested around using policy controllers along with the cloud controllers. And so the combination of validating and mutating webhooks can be used to enforce security requirements and also provide sensible defaults. And then we're also going to produce a library of policies that follow the CLNS benchmarks, and then also a sort of further level of sort of control plane opinionated policies that also make use of generation features to create extra supplementary resources. And so as our sort of proof of concept, we've got some stuff for S3 and RDS on for ACK and crossplane, and currently the repo is still private, and I'm going to blame that on Rowan being ill. And so just a quick primer on policy controllers. So they're primarily a webhook installed within your cluster, and then Kubernetes will be configured to forward every API request to this webhook. So validating webhooks will simply send back a yes or no answer, which will then allow or prevent the resource from being created. Mutating webhooks will send back a set of JSON patches, which will then change change the object being created in place. And so this gives us a single point of enforcement for everything that's being admitted into the cluster. And so now with cloud controllers, you can not only use this single point for your containerized applications, but also the rest of your infrastructure as well. And so some policy controllers also have a generating function which allows you to, as the name suggests, generate more resources when you're creating, when the initial one comes in. And so we think if we can use these properly, we can create a way that makes it simple for developers to provision infrastructure by not requiring them to have too much configuration in there by default, but they're still able to override all the API options as long as they don't breach explicit security policies. And this obviously helps prevent insecure configuration being deployed into your cloud platforms. And so what policy controller did we decide to use? Well, I've used Gatekeeper for a couple of years, and Rago, which is the language used to define the policies, is extremely powerful, much more so than Kubernetes for validation and that sort of thing. Because you've got a pretty sizable standard library that allows you to do all sorts of things like making HTTP requests and parsing JSON and all sorts. So there's a lot of things that you can check with Gatekeeper that I don't think are even possible with Kubernetes. However, most of the stuff that you're actually checking in Kubernetes is really only using simple logic, and the mutation and capabilities in Kubernetes are a lot more mature than what's in Gatekeeper, and in my opinion, a bit easier to get started with. And it also has this generation feature that Gatekeeper doesn't have. So that's why we've gone with Kubernetes for this demo. And so, yeah, basically, you're going to have the three types of controller. You have the validating one where, for example, here I'm trying to create a S3 bucket, and it's explicitly set blocking public ACLs to false, and so we don't want our S3 buckets to be public. So Kubernetes will block this. Whereas with the mutation, if I'm just creating a bucket, all I have to do is specify the name of the bucket I want, and then, Kubernetes, we have a policy that makes sure all the public access stuff is set to true, and so Kubernetes will come in and mutate and add those properties in before committing it to the Kubernetes API, and the developer doesn't really have to think about it beforehand. But they go back and check their resource later on, that they'll be able to see that that's been applied. But, consuming a cloud API is often not done in isolation. If you're creating an S3 bucket, it's not just the bucket itself. You also need to think about IAM, what keys you're using, if you're connecting to it through a VPC endpoint, how are you setting up ACLs and that sort of thing. And so a cloud controller alone is not going to eliminate this kind of complexity. They're just exposing a different set of APIs, but you still need to kind of know how all the pieces fit together. But with the generating stuff, we can start to reduce some of this complexity by creating some of the supplementary resources on behalf of the developers. And so, for example, here where we're creating an S3 bucket, and then Kubernetes will additionally generate roles and policies that allow, say, like read-write access only to this specific bucket, and then create a role that could only be assumed by a service account in the same cluster and namespace as the bucket that we just created. Okay, so we're on to the first demo. So, I'm going to show. So this is going to show some of the ACK stuff, and so these are the S3 validating and mutating policies we have at the moment, and so some of them, obviously, you see have crosses against them, and so that there are still like some limitations around what you can and can't do with these, like MFA. Setting any of the MFA delete stuff is just not supported at all by ACK. Some of this is still like a manual step, this 2.1.4. and then also validating that bucket policy is set to deny plain text connections. While we could do it quite easily with the mutation, the validating stuff is more complicated, and we'll get onto that after the demo. But yeah, so for now, I think just okay, cool. And as all good, I've recorded some demos earlier, so I don't fall foul to the demo gods. Okay, cool. So it's just going to clear out the cluster of all the old resources. And so, yeah, I'm just going to create a bucket with the sort of bare minimum config. And we'll just let that go through. And obviously, that was all fine. Bucket is created. And so we'll get rid of that. And now we're going to put some policies in place. So, yep, this is the policy that makes sure that all the public ACL stuff is set properly on the bucket. So we install this policy into our cluster. And then when we try and apply the bucket, obviously, we get a bunch of errors back because we haven't set up a bucket with the proper config. And obviously, this will be quite frustrating for developers. So, we can put in a mutating policy as well. So now we've got two policies, one to mutate and one to validate. And so when we try and apply our bucket again, it will get created without any errors. And if we just check what's been created, we can see there that it's had this public access block inserted into it. Cool. So that was easy. Okay, cool. And back to this. And so now I'm going to show some of the generation stuff. So this one is going to be looking at creating the role and policy and a service account that our application can use. So go back here. Again, we're just clearing up the cluster, and we're going to go through and we're going to be creating a minimal config bucket. And so if we create this bucket, we haven't got any policies installed at the moment. So we've got the bucket installed, and if we get policies, roles, and service account, we've got no policies or roles, and we've got only the default service account in this namespace. So we'll get rid of that. So we'll create a pod now, and what this is going to do is it's going to try and list all the objects in that bucket that we've just created. So we create this in the cluster, and it's ready. So if we check the logs from it, we'll get an access denied error, which is what we expect. Cool, okay. So we'll get rid of that. We'll get rid of the pod. And we will install our generation policy now. And so when we create our bucket again, and now check the policies and the roles and the service account, we've got these new policy and role and service account created for us. And we didn't have to do anything. We just, again, applied our bucket the same way we normally would. And so now I have an updated container, and so this one's going to create a file, upload it to the bucket, and then delete it. And so the only difference on that is that it's now using this service account, which is able to assume that role that we just created. So if we create it, and then check the logs, we get logs of it doing what we intended to do. So yeah, so we've got you know, a couple of demos of going from, you know, taking just a really bare minimum bucket configuration and using all the sort of automation features to just inject everything else that we need without the developer having to change what they're trying to create. They just have to think, I've got an app, I want to put stuff in a bucket, it's got it all for me. Brilliant. And now I'm going to look at crossplane, and so I'm going to try and sort of highlight some of the difficulties that we ran into with trying to write policies for some other scenarios, and you also see, again, we've got 213 and 214 without with crosses because the MFA is not supported. Again, the other ones are sort of manual check, but we have got bucket policy. We have been able to write a validating policy for that, and so that's actually due to the way crossplane configures bucket policies that makes what we're trying to do quite easy, and so it would be interesting to see this kind of thing adopted by ACK as well. So again, this is the crossplane version of a sort of minimal bucket, and we're just going through the sort of the process of applying it and checking that it gets created, which it did. And so now we're going to go and install some policies. So this time we've got the public access, which is the same as what we had with ACK. We've also got one that enforces that encryption is enabled on the bucket, and then we have these two as well. So we've got so the way that crossplane differs from ACK, and in fact the AWS API itself, is normally when you want to define a bucket policy, it's just defined as a JSON string in the configuration. Crossplane actually pulls that out to a separate object, and so and then you basically point that bucket policy at the bucket you want it to apply to, and crossplane figures the rest out for you. And because now you've defined this bucket policy as an object rather than a string, it gives you a lot more. It's a lot easier for you to kind of introspect and check values within it. And so yeah, we'll just go through and we will apply the policies, and then obviously we select installed, and then if we try and create the bucket again, it will get blocked as we expected with a bunch of errors. Cool, okay. Well, that's fine, we're doing what we were doing last time. Let's make some mutating policies to put all the default configuration in for us so that it passes. So again, we've got the two for blocking public access and adding encryption. And then our third one is a generating policy, which generates a bucket policy. And so in theory now this should deploy without issue. But all right, so we put our policies in, and then we try and apply the bucket, and oh, it failed. Why is that? So it's saying, oh, you haven't got a bucket policy. That's strange. We've got a policy that's going to generate our bucket policy for us, but the issue comes where the generation stuff doesn't run until after the validation step. So if you've got resources that depend on other resources to exist, it basically makes it impossible to validate at deploy time, where you're like, okay, I've got something that depends on something else, so I've got to wait for them to be created, and sort of setting up dependencies is it's still not something we've really figured out how to do elegantly. So to make this particular case work, we'll basically modify the policy that checks that a bucket policy exists for a bucket to only run as a auditing one, so it won't block when the thing gets applied. But if a bucket gets created with that, and then that doesn't have a bucket policy, later on you'll get an alert where this thing has gone and scanned through what's in the cluster, and you'll find out that way. And so as long as you've got the generating policy as well, you can be kind of confident enough that that you'll have a bucket policy that you want, but you're kind of starting to now having to relax some of your security things to get other things to work. And so this is the bucket policy that got generated for that bucket, just as to look at it. So yeah, so that's kind of what we've gone through. So I'm gonna kind of dive more into some of the limitations and stuff now. So yeah, what I was saying about buckets and bucket policies here is a concept I'm calling additive configuration, where it's on the left you have the ACK version of a bucket, and we're defining the bucket policy as a string there. Whereas the middle and the right one, that's for crossplane. So in the middle you have the bucket itself, and on the right you have the bucket policy. And then underneath where it says the region, you've got a bucket name reference, and so that's how that policy gets linked to that bucket. And so when we're writing validating policies, we can the statements is now like a list of objects, and we can check that there is a statement that exists that has this deny as long as HTTP as long as secure transport is false. And yeah, this is something that doesn't exist in the AWS API. In AWS itself, that bucket policy is not a separate thing. This is something that CrossPlane have basically laid on top of the AWS API through their own API. And I think it would be cool because there are other things like VPC endpoint that have a similar construct to this that they haven't done. So kind of expanding this concept is something that would be quite cool if that could happen. And so similarly, again with ACK, the way that you apply policies to roles is when you define the role, you name all the policies you want attached to it in this list. And so it makes the situation where, for example, if I want to deploy a new app, register like a new app in the cluster, ideally what I would do is when that app is created, I would then create a role for that app, and then as it requires new permissions over time, so like say initially it came and it just needs to go to S3, we create it and then we attach the S3 policy to it. Later down the line, I want to just attach a new policy to allow it to go to RDS. And so now I have to go back and like modify this role to add the new policies in. Whereas if you have, as with in fact in AWS, what you have is you have a role, and then you have like a role policy binding, which is just a reference to the role and the policy that you want to marry together. And so that allows you to, over time, generate new policies as new resources are created along with your app, and then just add the policies to its existing role. And so yeah, this is again, it's something that I think that could be improved with ACK. It does exist. Again, CrossPlane does have this sort of disconnect between roles and policies that makes it easier to kind of just add new policies over time. And so the other thing is kind of going back to this cluster zero problem, where you have to have the cluster before you can use the controller to create new resources. But then that cluster, in case of EKS, will be running in a VPC. So you also have to have created the VPC to put the cluster in. And then if you want to then create resources that need to know about this VPC, like for example a VPC endpoint, you need to give it a VPC ID and a root table ID for it to be created. And so I was to get some things to work, I'd have to manually install, like you can create a config map with this data, and then Governo can can pull that data in, but I'm still having to, like, not necessarily manually, like it's in my Terraform, but it's another gap where it kind of exasperates that cluster zero problem. So what would be a good feature, I think, would be essentially having, much like data in Terraform, where you can just create a sync object and say, like, okay, go and read all the data about this particular VPC from the API and just populate it within my cluster so other things can reference it. And when it changes, you know, that'll get updated. And you don't have to worry about that. Yeah, I think that's about it for me. If anyone's got questions, yeah.
Any questions? Just raise a hand. No, everyone knows it's break time, don't you? So it is break time. Yeah, okay. It is break time till past. If you kind of want to stick for questions, feel free. If not.
Thank you. Hi,
Hey.
thanks for the talk. I have a question. I would like to know your thoughts about the mutating and the generation of new resources and GitOps. Doesn't that break GitOps in that in Git the state is no longer the state of the cluster?
I'd say no, because, okay, so for example, if you create a deployment in your GitOps thing and then that's creating pods, you don't have the pods themselves in your GitOps because you know the controller is responsible for taking what you've applied and turning that into more state. And that's similar to what you would expect with these controllers and the policies, is that even if you know, spun up a new cluster and just copied all the YAML you had defined, the policies and the controllers should work in such a way that you'd always end up in the same state from that.
Any more questions? No, brilliant. So it's break time until past for the next talk.
Can you understand what I'm saying though? No. What? All right, sounds good, good, good. Thanks for coming. Thanks for coming to Scotland as well. Hands up, please, who's not from Scotland, who's travelled to Scotland here. And could keep your hands up as your first time in Scotland as well. Excellent. All right, awesome. I hope you have a great time. All right. Thanks for coming to this talk over the other one. Obviously, this one's going to be way, way better, in my opinion. So you made a great choice. My talk is in 3 sections, basically. The talk is titled The Future of Continuous Delivery. And so we're going to take a brief look through of the past, i.e. to give you a little bit of a context of where we are today and how we got here and why we're here specifically, rather than just being a ball in space and we're just flying around. And there's methodical reasons why we are where we are today, and there's some key factors that were in play. And then we're going to talk about the present, which is how we got where we are, where we are today, and like what things are available to be aware of, or things you may not be aware of that you'll see today. And then ultimately looking forward into the future, what's going to be coming across your computers and screens and businesses in the next 12 months or the next 2 years. And so it's also to keep an eye out for that as well, because as technologists, we're always looking for opportunities to stay ahead of the curve and things to learn in advance of it becoming, say, mainstream. For example, Kubernetes, people who are early adopters of Kubernetes are now very, very senior people in big organizations because they got in early and they started. So it's also your opportunities to kind of look out for things, and that's that. I also, I'm an open source contributor. Hands up, has anyone met me before or seen me, just so I know who's familiar? Okay, last night, yeah, at the bar, that was good. So for those of you who haven't met me, I'm Paul, I'm from Scotland. I'm an open source contributor. I'm part of the PHP teams, PHP Fig, which is the standards body, and Jenkins teams. I'm also part of the CD Foundation, which is part of the Linux Foundation, like the CNCF. Hands up, who's heard of the CD Foundation before? Okay, good, maybe about 40% of people. I'm also a conference organizer in this building for Scotland PHP. We've done that for 5 years. David, the organizer of this conference, was an organizer of that conference, so it's all good. I'm also a speaker, trainer, and I do consulting and have done this, I suppose, in my career in all these various different random parts. And these are things I do. So top from engineering to the top, left to right, across, up and down. But I specialise specifically in CI/CD because I found that the most enjoyable, because you can have great software, great infrastructure, and great tests. But if your CI/CD systems, the central point where we all flow in and out of on a daily basis, if that is not good, what's the point? And so that's where I went into companies, from company to company, and transformed their legacy stuff to modern stuff, or even just taking really badly Jenkins systems and putting best practices in place and making them the best on the market that you can get. So really making an impact that way. That's why I'm so passionate over the past, say, 10 years or in 8 years, specifically speaking and teaching and contributing to CI/CD solutions. And that's ultimately why I joined the CD Foundation and why I'm here today. Despite all that, I still feel like this every single day. And I hope you do too. And if you're not, then you're not learning enough. But I hung all that up, and I hung my boots up and said, I'm going to start up my own company, as you do, and which is effectively Draconis Technologies, and we are the sponsor of this company. We sponsored the social last night, so it's good to see you there. And it's basically an end-to-end engineering-led solution for hiring. And our engineering team doesn't build products. Our engineering team takes the pressure off of your engineering teams when you need to hire specialists. So if your company in the future is thinking, oh, let's use a recruitment agency, an external company, tell them to stop and just say, hey, give these guys a shout and see what we can do, right? The CD Foundation is basically part of the Linux Foundation, so you've heard of the CNCF. For those who haven't, it's basically like a sister team, sister project. It's part of the Linux Foundation, but we specifically focus on cloud-native technologies in the cloud-native space, but how that specifically is influenced within the CD, continuous delivery, sub-ecosystem, I suppose. The CNCF has projects like this, Captain and Flux, which I'll talk about in this talk. You've obviously heard of Kubernetes. And the CD Foundation is things like Detecton, Jenkins X, Spinnaker, and loads and loads of others, right? So on to the talk. That was the intro. This is what we've had for the past 20, 30, 40 years, software, largely, right? There's a few exceptions, but ultimately, this is what it looked like. Would you agree? Okay. And when it comes to CI and CD, it was easy, right? Jenkins was, 80%, 90% of the world when it came to CI and CD solutions and automation, right? And it was a great tool. It was built by us, open source. It was built by us, for the needs that we have every day. But then something happened. So at that point, life was great. Let's go to, say, 10 years ago, right? 2012. But then something happens. Globally, software companies started having to deliver more software at a higher scale than ever before. This created unprecedented challenges and demands on us as technologists to keep up and cope with that demand. And specifically when there was a demand, the example is smartphones, right? Smartphones are now in the hands of every people. Prior to the smartphone era, the things that you were building and the things that you were deploying onto the web had a limited amount of traffic. But then, of course, when consumers facing and apps and tablets and all that took off, ultimately the amount of people on the internet went exponentially. And therefore, we had to react because our systems couldn't cope, they couldn't scale, they couldn't be managed effectively because it was just one big monolithic system. So this is what happened, actually. So because of the normal people in the world needing smartphones and access to the internet, and we put that stuff there, this is the fundamental shift. This is not a new invention. It's called distributed systems. It's been around since the 80s and 90s, right? And it's been distributed systems are used a lot in other fields, maybe not web related, because the web wasn't really ready for it. But then when it matured, that we started bringing in distributed systems architecture into web-facing systems. And so, in essence, CI/CD pipelines kind of went from this to like this, right? It's also a dual purpose slide because it's a bit of a joke. Someone says, hey, let's build a very simple CI system, but it's not actually like that because CIs and CD should be a reflection of your organization and how it's structured and flowed. So this is a meme, a bit of a joke, but it's also a reality of how complex things get. And this is an example of a pipeline that I built for companies, say 6, 7 years ago, for the government, when they had a pipeline that took 1.5 hours to run, and I came in and re-architected it, and that done 12 minutes, right? So this is the kind of stuff that we do, that I did, and like what we do is consulting. So the challenges that ultimately happened when we transitioned from mono to micro is pipeline development became very complex because there was no like loads and loads of tools and blog posts and ways and training and community adoption. What is the standardized best way to build not one pipeline anymore, but 10 or 20 or 30? And how do they integrate? And are there dependencies between each of the pipelines? And ultimately, it was such a hard thing. There was no rules, which became, we entered the wild, wild west of CI/CD, which we hit about 7 or 8 years ago, right, ultimately. Everybody's just doing their own thing, venturing, trying things out, and trying to take tools, for example, Jenkins, which are traditionally not designed by us to suffice all this new complexity. And so ultimately it would take years for that Jenkins stuff to catch up. Meanwhile, private companies took the lead. Companies like Weaveworks and CodeFresh, they published big articles and went to conferences and say, hey, we had like one big app, now we've got 300 of them. And this is how we're doing our CI/CD, whether it's Jenkins and we're Docker. And Docker was also kind of curving up at the same time. So they're like, oh, we're Dockerizing stuff as well as breaking things up into small pieces. So now trying to manage. So there's big companies that led the way in terms of this is how we've done it, and this is kind of be seen as a good example. However, those companies are like massive, like multi-billion-dollar companies or whatever. The majority of us do not work at those companies. So they're shining the light. This is how you do it, but in reality, it didn't quite pan out because you're building stuff for very different types of scales and different organizations. And so that was a good thing, but also created some problems. We're still in the West, Wild West. And then ultimately what happened is private companies led the way, which is companies like Circle CI, GitLab and Bitbucket. Again, the private sector using money, monetary, corporate capitalism has its benefits sometimes, and they're driving innovations and tools into us to try to help us, deal with the managed complexity. The problem is they're primitive, they're closed source, and they're proprietary, and they're general purpose tools, right? You can configure them, but you can only configure what they allow you to do, and that's it. You've got a YAML file, right? And that's it. You can only put in what values it lets you. It doesn't really reflect the organics and the nature of your organization and how your team or teams all interconnect and flow like we had before. We had systems that worked well and we liked them, but now we're having to change. So now what happens is problem is that you have to model your organization's processes and stuff around what these tools can let you do and not do. Because when I go in from company to company to company as a CI/CD specialist, We're seeing this. We're seeing people transitioning away from, say, Jenkins over to like Bitbucket or whatever. But Bitbucket can only do a small portion of the things that they had before. So now they're changing things. Oh, we can't do that because the software doesn't let us, or we can't do that because it's weird, or it's, you know, right? And so that creates an organizational problem, right? They're good for small and simple things, but you can get mid or large size companies, especially the not tech-first companies like governments, right, and banks and stuff. They're not usually tech-first companies, so they have all these procedures and teams and stuff, people to sign off, additional sign-off, etc., etc. So they don't really work at that scale, right? It's surprising if I go into a bank and I do not see Jenkins running in that bank, not because it's old, because it's the tool that they need to give them 100% full control, because that's the right type of tool for that company. Example. So that's the first section of the talk, kind of how we got here, right? The scale, the transition, and some problems that occurred. But then about 7 years ago, 6 years ago, there was a trigger of innovation that happened. The innovation was already happening under our feet, and we didn't realize it, which is actually the cloud native space, which we're all here today and we're all in, which ultimately Kubernetes is leading that. You've got things like Docker and containerization and all these innovations that are happening. But the tooling and all the CI and the CD stuff was built and created not specifically for cloud native systems, and it was created before that. So we're in two different worlds. And we're all trying to get to the new world, but our tooling is in the old world, right? And so Tekton triggered something. Maybe it's more than 4 or 5 years ago. Okay, hands up, who's heard of Tekton? Good, okay, about 60%. Tekton, for those who haven't heard of it, it's basically like a generic pipeline tool, creation tool that you just write YAML files for, lots and lots and lots and lots of YAMLs, hundreds of thousands of lines of YAML, to create an agnostic pipeline that you could then throw onto any cluster. And it does basic things like this. This is Tekton. You've got a big pipeline on the left, the top, and then you'd run it on the left, and then you've got pods and then containers, and these are the tasks. So we said, hey, we've always did this stuff in like Jenkins syntax and other type of syntaxes, but really we can think about this as not about Java, not about Groovy, not about anything, but just cloud native stuff that can be put onto any cluster and any company on any cloud hosting provider, and you'll have it. You can move it between company to company. It's great. That's ultimately one of the generic USPs of cloud nativeness. But specifically within CI/CD, this happened. And it really showed everybody that while the private companies, people were trying to transition to private companies, or they're trying to use them for the general purpose tooling, it made us think and go, actually, you know what? This is actually a solid idea. And this new cloud native tech that's coming out, we could actually use this to our advantage in the CI/CD context. And that's what Tekton did. And fair play to them for doing it, right? It's not an ideal tool. It's bare bones. It's not really something you build every day. It's more of like you maybe use Tekton to build an easier solution, and then with that solution you can configure things, right? It's very bare bones, so I don't recommend it if you're just like, needing something urgently. But then after Tekton, we had all these new things that popped up. Same, more in the same direction. So now we've got things like Argo, Flux, we've got Jenkins X, which is what Jenkins wasn't, and we all drifted away as a community. And now obviously Jenkins X and the open source community are working on that, which again will give us full control, right? Which we once had. We've got Captain on the right. Spinnaker is actually not really too much cloud native. It's always there, but people adopted it and then quickly started to shift across to more native cloud techs. And in the bottom right, one of the latest things is GitOps. Who's heard of GitOps? Okay, everybody almost. That's good. I'm going to skip this slide then. So Jenkins X. So Jenkins X, who's heard of Jenkins X? Okay, maybe like 30% of people. Who's used it? Some brave souls. Used it in production?
It was a nightmare.
Okay, how long ago was that?
I did on a stream about 6 months ago.
Fair enough. It's an out-of-the-box solution. It's opinionated. It gives you all the tools you need, and you basically turn things off. It's awesome, right? It's powerful, but it's not mature as other options you have right now. Right now, we're actually living in the future, and that's kind of what the fallacies of this talk is. You've got the future from now, but you've also got what we have right now. If we went back like 2 years ago, right, what we have right now is literally the future, because we didn't have it 2 years ago and 4 years ago. And so right now, there's so much that we can take advantage of and capitalize on. And again, Jenkins is getting there, right? Again, now, it has something out of the box, which I used for customers when Jenkins X Alpha was released, to give them something for free, which is preview environments, which ultimately is it takes your apps, app and apps together as an entity, and they'll deploy it. But it's all just done for you. So if I create a pull request and push it, and I get a pipeline that kicks off, while my pipeline's kicking off, it's also creating a preview environment for me, and it's doing ingress. Remember, it's now cloud native. So the Jenkins X is integrated into the cluster where your apps run. It can create ingress rules, which is like URLs. So now you can have like pull request 1.company.com or .preview.company, pull request 2.preview.company.com. They're called UAT environments, right? User acceptance testing. So literally, if you push code to a pipeline right now, typically you wait for the pipeline to finish, and if it's okay, then you maybe deploy it somewhere and trying to get it deployed so that testers and stakeholders and managers can actually have access to to that environment to test it manually and play around. So Jenkins X gives you it for free straight away. Where when I push, while it's building my code and testing it, in parallel it's actually creating an environment. And when it does so, it takes the URL for that environment and puts it onto the pull request as well, automatically. So I can go to the pull request, and then the Jenkins X bot will come onto the pull request and make a comment and say, hey, your preview environment is now ready for use. Click it, boom, your app's there, like magic. Like I didn't have to do anything, zero configuration for that to happen. And then it can go in Slack and post. So there's one USP that you can get from any cloud native CD solution. And Jenkins X, that's one of the many, many cool things that it gives you straight away. All right. It can be installed on any Kubernetes cluster. If you've got a cluster where your apps are running right now, you could be running other things as well, like other CD tooling. It will not interfere unless you're actually, it's like taking over. And you can just say go and point it at that cluster. Or it can actually create the cluster for you. Because if you don't have a Kubernetes cluster, you can tell Jenkins X, hey, I don't have a cluster. And it goes, cool, I'll make one for you. And you just give it your Amazon credentials or Google Cloud or Azure credentials, and it just goes and makes the cluster for you and then puts itself on that cluster. So it's kind of like a fully out-of-the-box tool that it's kind of more user-friendliness now with the ability to control and configure everything, but not the bare bones Jenkins it once was before, right? So that's what I've got to say on that tool. Effectively, this is kind of how it works. On the left-hand side is user interfaces, and you can have multiples, you see. The legacy Jenkins was just one interface. Now it's a decoupled system. The Jenkins X engine is actually like a back-end thing. It's pods and it's things, autoscalers and replica sets. They're all running inside of the cluster in a reserved, Jenkins X namespace. Kind of like Cube system, but then we have one called Jenkins X, and that's where it lives. It's the brain. And then it can have just, API access, command line access, or user interface. And so people have built excellent user interfaces, and they're iterating on that, similar to the user interfaces you get from Flux and Google Cloud and all these other things. So people just take that stuff and they just build it, and we get it. So now open sourceness is kind of coming back again full circle from, when we had that trigger, when we had that shift. That's preview environments. I talked about it already, so I don't need to. But when you merge it, and it'll delete the preview environment for you, and it's all configurable, like leave it, don't leave it, all these things. Next, we're going to go on to Flux. Flux, I'm not going to spend too much time talking about. Flux is a very, very solid option. Who's here has heard of Flux? Okay, keep your hands up if you're using Flux. Okay, a couple of people, but say half of you have heard of Flux. The reason, for those of you who haven't heard of Flux, this is a tool. You can use it now. It's ready to rock on your cloud native, Dockerized, containerized projects, right? But it's deeply integrated into Kubernetes. It understands it. It's very close to the way the mechanics of Kubernetes itself runs in terms of like hosting your applications and hosting your stuff. It's very, very similar, and it feels very natural and very intuitive to be able to build stuff and therefore configure things, create your own custom kind of things that allow the system, the behavior of the CD system, to behave more like a reflection of your organization, which is better, right? Rather than general purpose tools that are kind of, it's cloud and you just throw money at it. This one will let you take that control, and so you just say, this is how our organization works, let's do it. And all these they're all quirks in your companies. And so this is an example of a tool that lets you bake in custom behavior to reflect the organization, so it knows how to ask questions and stuff. The one I'm going to spend more time on is Argo instead. So Flux and Argo are similar, but they're different. And there's more, Flux is more lightweight, in my opinion. Argo's not as lightweight. It's great, but it's just got more things, right? Flux is very light. It's got one thing that does it really well. Argo's different. Who's heard of Argo? Good. Who's using Argo, though? Okay, about 10 people. So right now, my company, we're doing a kind of modernization program of work for a customer in Switzerland, and we're using Argo for that. And they've got Jenkins, like legacy Jenkins right now, and we're modernizing it and taking them through their journey. And so we picked Argo over Flux for that, just because it had more, right? Argo itself is not just a pipeline tool, it's an umbrella of projects. And it's got multiple things going on. They've got Argo work, so now, who's using GitHub Actions? People using GitHub. So in that, they call that workflows, right? A workflow file. It's the same. So we're now evolving as a community from the word pipeline to the word workflow, and there's a good reason for it, and it'll make more sense in the third part of my talk when I cover this. So the pipelines are called workflows, but they also have this cool thing called events. Again, that's the future. I'll talk about that in a sec. And it's a fully blown solution, and it's got GitOps, but other best practices. Argo is a great example of a team, a company, a team, an entity that are really encouraging best practices from day one. Like if you install Argo, it says, hey, this runs on GitOps, by the way. You know, good luck trying to like turn that off and make it not work like GitOps. That's an example of good stuff that's came out that are embedding straight away. And there are an example of best practices in other things, not GitOps, but just across the board. So if you're unsure and you're venturing into a new world, a new CDE landscape, or you've got new projects kicking off, highly recommend looking at Argo CD as a starting point to see like what easy stuff. And it's relatively straightforward to install. Again, it's all runs in the cluster. It's all fully cloud native, so should be the same. The next thing I'm going to talk about is Captain. Who's heard of Captain? Maybe like 10 people. Anyone using Captain? Nobody? Okay, cool. So I meet with the Captain core team and the other core, like Jenkins X and other that, to understand from someone from the CD Foundation, like what are they working on, what are their objectives, what's coming up. That allows me to then publish talks about stuff that's not mainstream yet, right? The Captain project is awesome and it's new. It's a new thing. It's not yet another CD tool. It's not a Flux and an Argo. It can do the same job as them, but it's coming at a different angle, a more mature angle than I actually considered in the past. And I was like, this is blowing my mind. So this is, again, not as mainstream, not as mature, but it comes from a very, very mature company called Dynatrace. All right, if you've heard of Dynatrace, they do other great products and are very well respected. And so arguably should respect them for what they're doing here because it's really, really cutting edge. Captain is a control plane for your environments. It's not a CD tool. It can do things that CD tools do, but it's not what it is. And it does full lifecycle management for your applications and services. Lifecycle just means from the point where you have a pull request, or you have a project, you have a pull request, all the way through to the different environments you have, all the way up to production, right? That's what lifecycle means, end to end. Sometimes you can go forward, sometimes you have to come back, sometimes you have to do some weird shit in the middle. But when I say it's a control plane, what I mean is it's an umbrella around other tooling, and that's when it starts to get interesting, and that's when it starts to change. And it does that by integrating other systems into a central place. So rather than trying to be a tool that does one thing, like they're the same, it's allowing other tools to do what they are strong at and kind of harmoniously bring things into a central place. And another good example of that is monitoring and observability tooling integration, which is new, right? I don't see this done as well as other tools. This is a screenshot from Captain. It's just showing you what one of your environments looks like. But as you can see here, it's got some greens and reds and oranges. That's actually monitoring stuff. It's a staging environment, but it could be production. It could be a pre-prod or a stress testing or load testing, security testing environment, right? It could be any environment you want. And on the bottom left, you can see it says like 97% score. Don't know if you can see that at the back. It's a little bit low. But it also understands the health of an environment. You know, if you go to Bitbucket Actions, GitHub Actions or something like that, whatever you're using, it doesn't know anything about production. It has no idea. It's just a general purpose tool. You press it, it does a thing, and then it triggers other things, right? So this is different. And this is where it gets interesting. So it says bring your own tools. So you've got Helm, which we have and we need as a package manager to move all our things around. There's Argo, Jenkins, Prometheus. I think the next one is Dynatrace. And then after that, it looks like Apache. And then, I don't know, the other one's Datadog and stuff like that, and Slack. So if you think about it, you've already got stuff in your companies. and maybe Argo is your new tool for choice, right? You've taken over and you're fully Argo. But with Captain, there's actually a level above all your tools, all your Jenkins and pipelines and stuff. There's a level above that, and that's the Captain space, right? Here's an example of a life cycle, a life cycle of an app getting deployed, right? In the top left, it's just like we've pushed some changes, right? On the right-hand side, this is where it gets cool. So number 5, you're deploying stuff, right? That's cool, that's normal. GitOps, right? I want this on this environment. But on the right, very, very right-hand side, it says monitoring provider. So it integrates with your Prometheus or your Datadogs and your New Relics or whatever you're using. And it has defaults, but it allows you as the person in charge to actually create custom configurations and custom events and or things, or when Captain recognizes something is happening, you tell it what you want it to do. Whether it's, sound the alarms and freak out, or be doing intelligent stuff, right? So it's intelligence, like a brain, effectively, right? Now, ultimately, if you look at number 8, it does a deployment. Number 9, it got bad feedback. That's, again, the cool part. And then, ultimately, when you get bad feedback, depending on what that feedback looks like, you can then do stuff. So that's going to do a rollback. Number 11, it recognizes something went wrong. The machines are doing this for us, right? And that's, right now, when we're not using tools like Captain that are deeply integrating other systems, we have all the Prometheus and we have all our New Relic and our logging systems that are monitoring our live environments. And we have all these alerts, and that's the focus, right? SRE, focus, alerts, logging metrics. But when those things are bad, then what? The humans have to take over and go, look at that and go, what is went wrong? And then decide, what do we want to do with that? And then you might go manually over to your CD system and start rolling back the deploys you did, because that's how we work. With this, there is no separate system, it's one system, right? And so ultimately, you can, if it's automatic rollback, you can say things like, basically, if my environment starts slowing down 2% latency on all API calls, or something like that, 5 minutes or 10 minutes after I last deployed, then we would roll it back, right? And so it's got like time graphs. These are not new things, because this is how our alerting and monitoring systems already work, right? We create rules over time, but now you can integrate them into CD, and it will do stuff. So I hope that makes sense. This is why it's cool, right? Can you tell me what time we're on? How long have we got left? Okay, so awesome, good. And now onto the cool stuff, right? So inside the CD Foundation, there's SIG groups. Who's familiar with what the SIG group is? Okay, so SIG stands for Special Interest Group. The CNCF themselves and the Linux Foundation in general, that's what they do, and they have people, specialists. So like the Kubernetes, the cloud native ecosystem, they've got security people, storage people, networking specialists, and they kind of go into the little working groups, kind of like a standards body, similar to that. So the CD Foundation is no different, and we're just going to roll back a little bit. So basically, what to expect in the future now is, this is a kind of recap, right? So what we're getting from the future of today is we're driving forward more towards unopinionated tools that are facilitating things delivery, that we can configure, that we control, that we maybe host, right? Argo CDs is driving us into an event-driven, a future of event-driven pipelines. Haven't talked about that yet, because I'm going to talk about it next, right? But there's a cool shift that's happening. Captain is becoming a control plane for the integration of all the tools and the cool tools. Maybe you have so half the stuff is in Jenkins and half the stuff is in Flux, right? And you've got half and half, things like that. Bring it in, right? It's free, it's open source, right? And there's a thing that's being developed right now called Flux Subsystem for Argo, which I won't go into too much detail, but it's allowing you to take Flux and put it into Argo. And there's benefits of that, right? Like right tool, right job. Maybe Flux is better at certain things because it's deeply integrated in other tools. So you can use the right tool for the right job, and it isn't one of the. It's no longer as a ecosystem. It's no longer like one tool or the other, right? It must be all Jenkins or it's all Bitbucket, right? That's not where we're moving towards. And so this is another example. It's not released yet, right? We're months and months away from this being released, being worked on. But that's a good example where 2 projects are working together in collaboration. But it gets interesting, because how do you collaborate between tools? Different programming languages, different everything's. That's where the CD Foundation are working on, right? Interoperability SIG, which is the cross-communication between systems, allows them to talk to each other, right? Like a protocol, standardizing that. And then the event SIG as well, which is standardizing CD systems, but for event-based systems. So you've got 2 here. And this stuff is being worked on, and it's not actively in use yet. But under the hood, it will start being implemented inside the projects themselves, the Argo, the Flux, the everything else. And so eventually, maybe in the next 12 months, you're going to see more standardized, so you can create a pipeline one time. And that pipeline that you made, you can just copy and paste it, and it will run it in Flux and Argo and Jenkins X and etc. All the ones that adopt the standard, then you use between projects and companies. And does that make sense? The value in being able to build something once now and then move it around. That, for me, that's true interoperability, and it's being sort of worked on and studied and analysed right now. ML Ops SIG, I'm not involved too much in that. I don't know much about it. But ultimately, if you're working in data science or AI or ML companies, the things you're doing in CI and CD and sort of the deployments, we treat them as boxes. You know, it's like there's an app there, there's a thing. But whereas when it comes to machine learning, it's a little bit different because they're kind of aggregating one larger picture, but they're doing little small bits, and they need to understand, you know, above, below, left and right, and trees and stuff, complicated things, way above my head. But it's like first-class citizens, so it's kind of like information that comes out of the little parts and stuff. So standardizing that would be good, but it's not something I'm particularly like involved in. Right? This is where it's changing, the innovation of pipelines. Okay, so pipelines were traditionally webhook-based, and they were one single unit. It's one pipeline. That's in our mind still. That's the way we still think. We think a pipeline is something, you know, you turn a tap on and water goes through it, and at the end, right? But we're now on the edge of reinventing what pipelines are, and for good reasons. And so what's happening, and we're going to see happening more and more and more, is many granular pipelines. But we're not going to call them pipelines. We're going to call them events. And these events, either, you know, they're listening for an event, and then they'll take over, and then they'll emit an event. So if you think about that, we did that in software architecture. It's event-driven based systems, you know, event sourcing or event-based architectures, and we've got all these queues and Kafka's queues and all that mad stuff. So, and these are the innovations that have happened over the past, say, 5 to 10 years in the software world, and these innovations are now making their way across to the CD world, basically, because we're learning, and we're like, well, why can't we have that in CD, right, or in deployments? And as such, a pipeline, at the moment, pipelines run a piece of code, and it could be like Ansible, Go, or Helm, apply, blah, blah, blah. When they become event-based, they're not actually going to do that command. They're going to emit an event. And there'll be another thing, listen for that, and that'll take over. What that means is true, like a context-agnostic sections, like we do with code. You know, we do dependency injection, we inject things into our code. Dependency inversion. Right, we invert the dependency, so you don't know what the outside looks like, but you'll do your little part, and that's what pipeline is going to happen. That's going to get the interoperability drive really, really good, and the interoperability and the taking things with you type thing. Right, you might want to make a code. Earlier, right at the beginning of the talk, I was showing an example whereby when it was the wild, wild west, and we started transitioning over. We had one pipeline, then we have 20. How do we share code? How do I maintain that central piece of thing? And either people are copying and pasting it, or they're doing really terrible things, right? I don't want to speak of, not Groovy, I'm looking at you, Groovy. But, so that's, so the breaking down of things and making them events that flow together, then that solves that problem. And so now you'll be able to just build something once, and it's done. And then later, it's just figuring out what workflow or what context that will actually fit into. But it's completely reusable because it's agnostic. This is how software engineering works, and it's coming to CD, basically. There's also something called CD events, which is part of it's like a project, part of the CD Foundation. Like Jenkins X or Tecton, it's called CD events, effectively. And that's basically the project and the team that are understanding and focusing and standardizing all the different events that occur. Like test started, test passed, or like deployed. There's all these standardized events, and all these, as such, what you're going to see in the next six months and more is a lot of these projects adopting these events, the event standard, and what the events are. So like every system will be able to say, understand what it means that the test suite has failed, right, or the deploy has passed, or or this environment is unhealthy, or we're going to do a rollback. And so you'll be able to have multiple systems actually communicating and actually working together rather than working in opposition, right? Because they will understand, like, this guy's emitting an event, so that's my event, I want that. And there won't be any barriers, so kind of breaking down those barriers, right? And that's that. This is an example of an event-based architecture. It's probably bad examples, because, I'm terrible at naming things, but you can see where you go with that. You push an image, you scan the image. If it fails, you do something in your workflow. If it passes, you do something else. You keep going. And all these different things and outs and conditions. So it gets very complex. But it's about managing that complexity is the skill of a good tool and a good kind of design. And that's what we have and what we're getting. And so it'll become so natural and so easy for DevOps, like SRE, ops people to help build this stuff, and also the devs. But it's a little bit language as well. So you don't have to speak like, oh, the CD system doesn't work like that, and you're talking to a project manager and they just like glaze over. I look at you like, I don't know what you're saying, right? So this stuff also helps with language, ubiquitous language. You create your own events that make sense in your company. Like Joe Blogs has signed off on this, and this guy hasn't yet, or something like that. So you name the events that are actually or first-class citizens to your business. This is coming from the BDD world, behavioral-driven development, and DDD, which is ubiquitous language. So, and that's got a lot of strengths to it. Again, because we're innovating in CD, we're taking all these the best things from the software worlds and the testing worlds and all that, and they're kind of influencing the architectural, I suppose, landscape that's in front of us. That's it from me. I'm here to do questions, and I've got social tonight, and I'll see you tomorrow. That's it.
Awesome. So any questions, just raise a hand. I'll
take the mic as well, if you want.
Yeah. No?
I know that was a lot of information. Yeah. And I'm happy that it's just me. I'm like, between me is the pub. So appreciate if you want to hold your questions to the pub.
I've got one. So within networking, you have telemetry brokers, which kind of do the same thing, where they'll collect events and then push events into the relative sources. It seems like CD stuff is going in that direction. Do you know if that was like on purpose that it kind of picked up that tech, or it was just naturally kind of evolved into this?
I think probably both. I think people have good ideas and they're like, this is a smart idea, let's do it. And then on the other side, there's other smart people saying this is also a good idea, and we're doing it in telemetry space, events like, environment unhealthy or there's a problem. But ultimately, they've kind of one-up that and go, hey, let's not isolate that. Let's make it central to, integral to, the CD and things like that.
I guess that's it then.
We got one. Oh. You can shout if you want. I'll repeat the question. I think the question, I didn't hear the very beginning, but I think the question was around, have I used Captain, and if so, how would I recommend people to get started with it? I played around with it, but we haven't yet used it with customer projects yet, because ultimately we're busy getting them onto Cloud Native and onto things like Argo right now. The next natural step after we've got a stable CD system will be to bring in Captain and to allow Captain to absorb the Argo pipe workflows and trigger them, right? And you can do what you normally do, but there's like a level above. So I'm about to embark on that journey myself. In terms of advice, I'd probably say, well, you've always got the Captain site, the blogs, the community places. There's also the team, the Dynatrace team. They're very community focused, they're very engaging. So finding who those people are and going on Twitter and following them, and maybe LinkedIn as well, you'll start to see what they're publishing. Their job is to make it easy for people to understand and adopt it. So those are the people to probably watch as well. And that's how I personally would see things. And then I'd message them and say, hey, what's about this, and talk back. So, go for it.
Can you elaborate on the Flux subsystem for Argo?
So, no, because I don't know. So the question is the FSA, this new thing, the Flux subsystem for Argo. Can I elaborate on it? Not too much. I haven't deep dived it yet. I keep going to do it and then walking away. Like I don't have so I should be looking at this. So, but there's a lot. It's very obvious what it does. If you go to type in like FSA, Flux FSA, and you'll see the GitHub page, you understand it, and you'll be like, what problem is it solving? And I'll try to articulate that. I was saying like Flux is better at certain things than others. Argo is good for workflows and like bigger things. Flux has got its own dedicated USPs, so it's like use that and bring it in, or you flip it. But I don't think I'm wrong on that. I think it's Flux it into Argo, but you never know, right? My head's a bit mushy right now, so I could be getting it backwards. But it's pretty cool, and that's why I want to highlight it so you can go and research it yourself and let me know what you think. Cool, thank you.
So next talk is building operators for legacy software or running Minecraft on Kubernetes by James.
Cheers, mate.
Sure.
Yeah. Just because I think the live stream we get people to tune in.
Yeah, it works. I'll do it one minute. Sure.
Is it 10 5 minutes?
Yeah, if you could.
They're really insulting.
Oh yeah, great. Love it. Love it. Don't hear me clear? Cool. All right. Thank you everyone for coming. My name is James Laverack. I am a staff solutions engineer at Jetstack, and I'm going to talk about running Minecraft, which is always extremely fun. So just a little bit of background. Jetstack, if you haven't heard of us, is a Kubernetes cloud native company, mostly focused on consultancy and training and some software. I have stickers, by the way, if people want stickers later. I have Cert Manager stickers. That's probably where you've heard of us from. We originated Cert Manager, which is the big thing. Outside of Jetstack, I also work upstream on Kubernetes. I was release lead for Kubernetes 124 earlier this year, and I'm just a general SIG release busybody more than anything else. Yeah, okay. So what I'm going to talk about with this talk is me running Minecraft and why I eventually decided to build an operator to do that, and how you might approach the same kind of problems with your software that you're running. Most of you probably won't want to run Minecraft, but the idea is that the lessons here are relatively transferable and generic, and more importantly, not covered by NDA, which is true of most of the things we do at JazzDac. So, you know, that's nice. Before we begin, I do have a couple of quick disclaimers. This isn't an official Minecraft project. Minecraft is owned by a company called Mojang, who are owned by Microsoft. This is not endorsed by them. They don't know I exist, probably, hopefully. Be nice to me, basically. So this is completely unofficial. Please do not take it as the correct way to run Minecraft by any means. Also, this is not an official JetStack product. This is actually something I did in my spare time. So it is open source. You can get to it, but please don't think there's going to be any support from JetStack. Don't come to us to help you running your Minecraft server. We probably won't be able to help you. The code is open source, is here. I'm not going to go through any specific code examples. I don't have a demo or anything like that. I'm going to be talking about design decisions and things like that later on. But if you want to take a look at the code, you can. I would charitably describe it as alpha in quality, so be a little bit careful. Right, okay. I have a little bit of assumed knowledge. I assume you know what Kubernetes is. Pretty good bet. I assume you have a vague idea of what an operator is. So this is some piece of software which will typically run in cluster and typically manage other things that run in clusters. Not always, but typically. I assume you know what Minecraft is. It's a video game. It's pretty popular. It came out about, I don't know, 10, 15 years ago or something. I'm specifically talking about Java edition. There are a bunch of other random editions. I'm only really focused on Java here. It looks like this. I built that. People who are way better at Minecraft can build things like that. I didn't do that. So yeah, the other thing I want to quickly address is the word legacy. A lot of people in this community consider legacy to be a negative term. Am I calling Minecraft legacy software? Not really. What I really mean is it was never intended to be run on Kubernetes. No one at Mojang, I presume, ever thought that it would be run on Kubernetes, mostly because Kubernetes didn't exist when they made it, but you know. So, but this is true of a lot of software. A lot of software was never designed with this as a actual design goal. So, okay. With all that in mind, let's start at the beginning. I wanted to run a Minecraft server. Minecraft has a pretty standard client-server architecture. I wanted to run a private server for me and my friends to mess around in. How are you supposed to start doing this? Well, Minecraft, you can just download it from the web. It's a paid game, but you can just get the server jar, because Java edition isn't run on Java, from my website. They give you some running instructions, pretty simple. You execute it, and then it tells you need to agree to the end-user license agreement. But we can do that just by writing EUL equals true to a text file, and then we run it, and done. You can see it's bound to a port. You can see it's defaulted some settings. It's made a config file, done some other stuff, and the server runs. Everything is fine. And if you look in the directory you ran it from, you get a whole bunch of stuff. You have some config files. You have that world directory, which has actually got the world save data in it, and a bunch of other things. There we go. So you can imagine this was intended to be run like this. You know, some init system, a systemd unit, whatever, your Java runtime of choice, server jar, some config files on disk. Everything's fine. So why did I want to run it in Kubernetes in the first place? Why bother? Well, I run everything in Kubernetes. I'm a Kubernetes developer. I have a Kubernetes cluster at home. A cluster is one node. And to simplify my management overhead, I wanted to put it in Kubernetes alongside everything else. I was like, okay, how hard can it be? Those of you who are familiar with Kubernetes probably were thinking this or something like it. You know, we have solutions built into Kubernetes to do a lot of this stuff. We have stateful sets and config maps and PVCs and services and all the rest of it. So what's wrong with this? Well, there's a few problems. Problem number one, do you remember that end user license agreement that I agreed to earlier? We should probably look at that. First thing it says, do not redistribute our stuff, which is entirely reasonable, to be clear. I mean, Mojang don't want people taking like random patched versions of a jar and distributing it to people on their behalf. They want to maintain that ownership of a distribution mechanism. Fair enough. But I bet you were thinking we could do this. We could just download the jar and put it in a Java container And that's fine until we push it to a public repo of a next distribution, and I want Mojang to like me, so I can't do that. So what are my options? I could put it in a private registry or a local registry, which would be fine, because as long as it's not publicly accessible, it's fine. Or I could just not put the jar in the container image. I'm running on my home cluster, so I didn't have the first two, and I couldn't be bothered to run the local one. So I just put it on disk, and was fine. But now every time I want to change the Minecraft version, I have to go fiddle with some files in a PVC, which is annoying, I guess. But even if I had a private registry, I'd still need some kind of deployment, build, pipeline, workflow, something to make the new image, which would kind of suck. So, you know. Next problem, remember that config file that it's generated? It looks like this. It has a whole bunch of information in here. It's kind of a mixture of game settings, so like whether to spawn monsters or what the render distance is and things like this, and server settings, so like the IP, the bound IP and the port and things like this. And Minecraft expects this to be writable, and in some versions will actually error if it isn't. But we mounted it from a config map, so of course config maps will actually write new changes that are detected into the pod, but the reverse is not true. So how could this trip us up? Well, if we do some defaulting when Minecraft starts, which it does, then we could lose those defaults if we change the config map while the server is running. And more to a point, you can actually modify some of these settings from inside Minecraft. You can log into the game and modify a setting if you're an administrator and this kind of thing. And it will write that back to the file and expect that will be persisted, which of course it won't be if the pod restarts, because it will never get picked up back into the config map. So we can just not do that. You know, if you can consider this to be a run book, just like a couple of post-it notes saying don't do these things. That's fine, but I have to remember to do a lot of things, and I'm probably going to forget that. So it's a bit of a gotcha. What about backups? Even better. So Minecraft, at least this version of Minecraft, does not have atomic file system rights. So you actually have to tell it to stop saving automatically and flush all changes to disk, and then make the file system back up, and then turn saving back on. Because I'm in a home cluster as well, I don't have PV snapshotting. So I actually have to just copy it straight out. So this was my backup process for a while, which was fine, but slow and error prone. I mean, I didn't back it up quite as often as I'd like to. Thankfully, I haven't had a disk failure or anything, but you know, it's going to happen. And then my problems get far worse. There is a massive modding community to Minecraft, and this is something I'm really only going to touch on the surface of. But in essence, people like modifying Minecraft to do extra weird stuff. You've probably seen various examples of this. There's some built-in support with a feature called data packs, but most of the real fun stuff is in stuff called plugins and mods that you do stuff. I'm mostly interested in plugins because I don't want to have to explain to my friends how to connect to a modded server using a modded client. So I just mostly do plugins where you don't need a modded client. But there's no official APIs for those outside of data packs, so people made their own, and in fact people forked from the ones that made their own, so there's a whole generations of it. And I run paper at the bottom there, and there's actually a whole bigger set of things where if you start thinking about modded servers and people are trying to combine it, it's a mess. So even your choice of which version of a Minecraft server to run is a complicated operational choice. So why do I want plugins in the first place? Why do I even want to bother? Well, someone made a Prometheus exporter as a plugin. That was really useful. I want that. The other real cool one is Dynamap. So this is it creates a Google Maps style map of your Minecraft server. But this one is really interesting because it's actually live updating. It's actually hosted from the Minecraft process. And so if you place and remove blocks in game, it will update the map within a couple of seconds using like a WebSocket connection to your browser and stuff. It's really clever and it's really cool and I like it. And I want it. These are kind of quality of life improvements I want to have. So now I'm running paper to get plugins, and now I have some plugins files to manage as well. So this is the state we're in now, so it's fine. Some of you are probably thinking, how do these modded plugins and servers work with that end-user license agreement I was talking about? It says you can't modify, so you can't distribute the server, included in modded versions. Well, the answer is they don't. What they do is they distribute a jar which has got a Java bytecode decompiler and some Java code patches and the Java compiler, and then startup, they'll go to Mojang and download the Minecraft server jar, unpack it, patch it, compile it again, and run it, which is great. There's some caching there, which makes it not slow, but it's still an interesting thing to think about. But it does have a nice advantage of now we can actually put these modded jars into a container again. So that's not so bad, because they're just like GPL or MIT or whatever license. There's no problem with distribution in the same way, so that's okay. So, to recap, I have a bunch of problems that are kind of annoying, but I can't really be able to do anything about it. It's good enough. Then I started thinking, has anyone else made this easier? Surely someone must have done something. And there are lots of like manage your Minecraft server products, or not products, or some of them products, out there, but not really very many focused on Kubernetes, which is what I was trying to do, if you remember. There is this, which is actually excellent. So this is, someone has packaged a container which is designed to run Minecraft in Docker. I actually did use this for a while. It takes the idea that you could configure everything through environment variables. What plugins to load, what settings to use, everything. And this was really, really good. The only problem was, because it presumed that you had just had Docker, it did everything itself, which is great if you're running in Docker, and if any of you want to run Minecraft in Docker, do recommend. But now that I have Kubernetes, I have all these other tools to use, which I'm not taking full advantage of. So I took a bit of a step back from using this, but I did run it for a while. And then my real problems began. My wife asked me to run a second server. She said, oh, you're running one. Can we run another one? I was like, well, okay. Copy all the config over, copy the files, do that. It's okay. Now I have twice the problems. And then, inevitably, our nephews are getting into Minecraft. Can we make a server for them too? It's like, yes. Now I have 3 times the problems. And that's when I decided to write an operator. This is decided I'd had enough, and I wanted to do something about it. So, that is kind of a story of what it took for me to decide that writing some software was a good solution. So what did I want? I actually started by writing a short list of requirements for myself, like what did I think I was going to need, and why did I want it? So this was kind of that short list. I don't think I ever formally wrote this down, but this was kind of in my head of what I wanted, because it's only me working on this, right? There's no other people. I also wrote some YAML to be like what I would want that YAML to look like. What would I actually want to manage the server like? And this is kind of what I came up with. I wanted to have claims. I wanted to have most of the config in here. This is a shortened version, but you get the idea. Then I have this idea. So now I know that I want to put things in YAML, and I want a microserver at the end of it, and there's some magic that happens in the middle. So how does this work? Well, I started out by thinking of resources. And this is when I made my first design decision, was actually that service. So I thought for a while, well, maybe I don't need to make the service. I can just, with the operator, I can just make the service separately and use a well-defined series of labels in order to address the service onto the pod later. But I actually didn't do that because it felt really fiddly, like it would only be half a solution. I wanted it to actually be batteries included, so to speak. But that meant I had to include a bunch of information about the kind of service it needed to make in my CRD. I don't right now have a full service spec, but I probably will sooner or later once I need to change this again. Right now I'm only using node ports, so it's not so bad. So that's one thing. The other thing that I really decided on early on was to use replica sets instead of pods directly. This was, one, it meant that if my operator wasn't running for some reason, then the core Kubernetes reconciler loops would keep the pod back up just from the replica set. Also, and the main reason was just that reconciling a replica set was easier, because when you make a pod, a bunch of changes get made to its fields, and trying to reconcile that was a pain. So that doesn't really happen to a replica set as much, so it was a bit easier. The other decision I made, and if you remember, I said I didn't want to have object stores or image registries or anything else going on. So in order to actually get everything that I needed, all of these plugins, all of the other information, I just used a bunch of init containers. And this means that startup time is horrendous, but I don't actually restart it all that often. Most of the time, it just runs. I only restart it when I need to do an upgrade or something. So it's kind of okay if the startup time is 30 seconds. I mean, it's Java, it takes ages anyway. So I had a bunch of init containers that go and download all these things and validate them and put them in the correct places. I also stole an idea from that Docker container, which is I moved the config to a working directory. So the version that's mounted into the pod is not the same version that Minecraft actually reads from, which solves the problem if you change it, it can't see the changes that you've made, which solves half of the kind of config problem. I also decided that I didn't want to make like a generic plugin loader. I could have done. I could have, just pointed at a URL and said download this, put a config file in the correct place. I made a very specific one, which just dealt with the plugins that I cared about. The main reason for this was because I didn't want to try to make a generic system before I had to. For example, with Dynamap, that means I need to expose port 80 from the container. So I need to run a new service and an ingress and things like this. And trying to do that in a generic way just sounded horrendous, so I didn't. In terms of actual implementation, I just use Go with ControlGen and Controller Runtime. It's because I'm very familiar with those tools. I didn't use KubeBuilder, largely because I'm not particularly fond of its defaults, but KubeBuilder is also great. I'm not really going to go into too much detail on this. At JetStack, we actually teach like a full day-long course about how to use these tools, so I definitely got fit in 20 minutes. But go look at the example code, it's great, or the KubeBuilder book is great. I thought briefly about using Rust or something, but I decided that I just couldn't be bothered, so Go was easier. All right, so what about backups? This, of course, was one of the biggest pain points we were doing it before, so how did I solve this? Well, there is a little saving grace in Minecraft, which is something called Archon, which is like a remote RPC thing built on top of TCP, and this is built into vanilla Minecraft itself. So you can actually execute those commands like over a TCP connection. So that saved me having to like patch into stdin or something like that. So I'm able to execute those commands and then I can do the backup. The other decision was to use a separate CRD for this, a separate resource. So I make a resource to say that I want a backup to exist, and then it can go and make it. And I point at the server and I point at another PVC to back up into as a zip file. And then do this horrendous looking process. So I make a Minecraft backup, that makes a job, that makes a pod. The first thing it does is acquire a lease. So I was worried that if I ran two of these at the same time by accident, they would clobber over each other, and one of them would, turn saving back on while the other one was trying to copy files out, and I get a quick backup out and potentially not know, which would be awful. So the way I do this is that they have permissions to write the Minecraft server resource they're dealing with, and they put annotations on the pod, and using update that can be optimistically concurrent, so I can ensure that I can get a lease for a certain amount of time by putting a timestamp in a annotation, and this works pretty well. It shows only one of them can get it, and then it just uses Archon with an extra service I've made in order to issue the commands it needs to turn off saving, and then it just mounts the PVC. The PVCs for my cluster are read-write once, which means that they can be mounted read-write to one node. So as long as this pod ends up on the same node as the server, they can both mount the same world PVC, so it can copy the data out, which works pretty well. This, of course, means that they have to be on the same node. Thankfully, I only have one node. That's pretty easy. But, of course, you would need some kind of way to manage this in a bigger cluster. And then it just turns saving back on. So that's how I'm doing backups. Okay. Did this solve my problems? Well, it's now easy to make new servers. I can do upgrades via a CRD, including plugins. The config management is all in the CRD, so the allow lists, everything else. And I can do backups in CRDs as well. I still have some to-dos. I haven't really addressed the config sync problem. It turns out this is actually a really complicated problem, purely from a reconciliation point of view, because of course, if you change a setting in the game, how does a level-based system understand which one is the correct one to use? So that's a problem I haven't solved yet, and I'm thinking about. Right now I've still got the mental post-it note of just don't manage it in Minecraft. Archon isn't secure. As I said, it's implemented over TCP. There's no encryption. There is a password, but that's sent plain text. So the presumption is that nothing will have the password, and the fact I've set it to password hard-coded doesn't help. And there's no encryption of any kind, so I need to do something to protect that. So maybe a service mesh, maybe some kind of other proxy. Something needs to be done because this isn't great. There's also supply chain concerns. Just last week, it turned out a whole bunch of plugins hosted on like a central Minecraft plugin repository were infected with malware because a bunch of developers lost their credentials and had a bunch of botnet stuff plugged in them. So a bunch of people's Minecraft servers became botnets for a while. So, you know, the same problems we see elsewhere in the industry affecting Minecraft as well. Not sure how we're going to solve that. That's going to be interesting. The other one is modded, because I think my wife wants to play modded Minecraft on the server, so I need to figure that out. And of course, that's an entire separate problem of where do I get the mods from? How do I deal with that? How do I deal with distribution? Another set of issues. So, will an operator solve your problems? Maybe. I think my main kind of more generic takeaways, and this is true of talking to my colleagues who have worked building operators or things very much like operators for other, let's call them legacy, my definition of legacy software, is it helps if you set out to solve a specific problem. So I had a series of gripes that I wanted to deal with, and I set out to deal with those, and I feel I kind of have on most of them. So I'm pretty happy with that. I also use the features available to me through Kubernetes, like, for example, doing the whole leases thing in order to make sure I only ran one backup at once using annotation changes. That's just something that because Kubernetes runs on etcd, I can do, so I just did. I can see what else ever out there, what else is already out there. I looked at other options. I looked at that Docker Minecraft container, because that was really useful. And I stole ideas from it when they were really good. So, yeah, there's lots out there already. And I also really try to avoid making things too generic. I could have built that generic mod loader. I'd probably still be building it. It's, you know, generic solutions are hard, so I dealt with specific ones first and then moved on to generic ones. All right, that's all I have. Thank you very much, everyone.
Quick notice, we have been asked to stay in this room, and they'll give us more details about what's happening tonight. I suppose if you're not going to the social, you don't have to kind of get locked in the room with everyone else. But yeah, brilliant talk. Any questions? Again, just raise a hand. Can probably be Minecraft orientated as well. Okay, brilliant. Yeah, so I suppose if you're not going to the social, I presume you can leave. Not in a sense that you have to stay here if you are going to a social, but they have said, you know, stay here and the details will follow. I think they're going to live stream it, but yeah, we'll see.
Cool, thank you.
You're going to get loads of requests now. Can you host a wildcard? You don't plug in, are you?
No, I didn't bother.